Good morning, everyone. And good morning to those of you who are online with us today. We know that some of you are because we're getting messages. It's after 8 o'clock, you need to be starting. Which is very, very cool considering they're not even on Eastern time. So they're well aware of what time it is. So first of all, I want to welcome you to Woods Hole, either in person or virtually. And if you're only here virtually, at some point we might actually find a way to take a picture of the outdoors and what our weather is like today because it's fairly nice. We picked June for a reason. And so again, thank you all for coming to our Whither the GulfStream workshop. And I was reminded this morning that it was Malcolm Roberts who came up with that title. So I'll just say, if you haven't looked up the meaning of the word whither, the meaning of the word whither is to what place or state. And that is what we are talking about with the GulfStream. Where is it going? How is it impacting things? That is the goal of the discussions of our workshop. So just some logistical things, and then I'm going to turn it over to the co-chair for our scientific organizing committee. And I should say, rides, people are here, so I think you've made it, but there are definitely people at various hotels around, and if you did not have a ride in this morning and had to do something else, let us know, because there's plenty of ways for you to come in. I want to say thank you to US Clyvar. It's such a joy having Clyvar do your workshop for you because they do everything. They're just amazing. And then as part of that as well, a thank you to the agencies who funded this, which would be all four, correct? It was just three. Oh, who do I leave off? NASA, NOAA, and National Science. And they're right there. Okay, NASA, NOAA, and the National Science Foundation. So thank you to those. And we do have several program managers on virtually. So you can see this, the all-important piece of information is the Wi-Fi password. If you have EduRoam, that's actually better to use. So go ahead and use that. But if you do not, then we do have a WHOI guest. The bathrooms, if you haven't found them yet, they're just back here. Breakout rooms. So a lot of this workshop is really meant to be discussion, where we come together and we talk about how to plan and what to do. The talks are meant to be a sort of a framing and give us some things to think about. So when we get in the breakout rooms, we're not all just looking at each other. We are assigning people to various breakout rooms. Before the breakout rooms, the list will be either here, or if you're on virtually, you'll be assigned into a breakout room. And we're doing that just to make sure that we get a lot of cross thinking. So you will be switching out from break room to break room. So you will not always have the same people in your break room with you. Again, we have a number of people who are on the workshop virtually, and so they cannot hear any questions that are discussion on the floor unless you're using a microphone. So we've got a number of microphones that will be passing out. So if it's just a witty quip, that's fine. But if you actually want to contribute in such a way that those online can hear you as well, then the mic is key. For the talks this morning and this afternoon and so forth, we've asked them to have about a 25-minute talk with about 5 minutes for just some follow-on clarifying questions. We have open discussion times a little later, so the questions at the end of the talks should not be like really open-ended questions, but a good question that can be answered in just a minute or two. So we will ask people who are online, if you have a question of a speaker, to put it in the chat, and we'll pull that in, and if we have time, we'll make sure to get that. When we move to an actual discussion, we have the capability for people online to raise hands and show them and so forth, but we'll hold off for that for the actual discussion when there's going to be a lot of things. So again, if you're online and you have just a question for a speaker, chat, and then we'll have then you've got the ability to raise hands and be on the overhead screen for the actual discussion times. And I think that was all of the questions. We anticipated people using portrait for the posters. So we've kind of run out of room for the posters that are there. So we are probably going to take, we have a discussion about taking one of the poster boards and putting it right here in the doorway so we can have both sides to get a little bit more poster space. So if you have posters and you haven't been able to put it up yet, chat with us. And we will also have remote posters as well. So with that said, I believe that I am going to turn, I should say, all the members of the Scientific Organizing Committee who are here, please raise your hands so people know. So we've got Larry, good. And we have at least 3 online. Dujuan is in China, unable to get back. She was back home, and her town was actually on severe lockdown for 2 straight months. So, yeah, that's been tough for her. And Elizabeth Thompson is also on our committee, and she is online. And Roger Samuelson is also on our committee, organizing committee, and he is online as well. And Justin Small is on our organizing committee, and he is at the CESM workshop this week in Boulder. So but he will be online with us as well. So with that, I'm just going to say if we have a few talks this morning and then discussions and breakout rooms, but first I'm going to turn it over to my co-chair, which is Nathan, who is going to talk about the goal and of the meeting and what we hope to accomplish.
Thank you very much, Carol Ann. So good morning. Thank you all for being here or wherever you are and participating remotely. My name is Nathan Laxague. I am co-chair of the Scientific Organizing Committee, working with Carol Ann and the rest of the committee to help plan and sketch out this workshop. As you saw on our flyer and what's right there, the workshop does have a subtitle, Air-Sea Interactions at Multiple Scales and a Bite-Sized Description, a workshop for elucidating the role of the Gulf Stream in weather and climate. So compared with many workshops of this size, the participants here and joining us remotely have a pretty broad range of interests and specialties. Physical oceanography, obviously, atmospheric science, of course, geophysical fluid dynamics at planetary scale to Kolmogorov microscale, so modeling from climatic eras to ocean surface wave breaking, really a range of scales and topics that we have to distill into a single, aligned workshop. So this distribution of interest and approach will be essential, I think, for our task, which is elucidating the role of the Gulf Stream in weather and climate. So over the next 3 days, we'll be talking quite a bit about the Gulf Stream. First, identifying the outstanding questions in Gulf Stream research. Secondly, enumerating the main science issues with respect to the Gulf Stream connection to weather and climate. Discussing the characteristics of the field observational program that would be best suited to advancing our modeling capabilities, and exploring the observational and modeling tools at our disposal in this effort. So 8 presenters will offer a fairly broad view of these topics, while poster and lightning presentations will help us to get into the gritty details. So both the broad and the particular will be really essential, I think, to this discussion here. So the centerpiece of this workshop will, as Carol Ann mentioned, be the discussion. This will happen in large group, one-on-one around the posters, and during breakout sessions that will shuffle and rotate to get maximum churn and introduce people to as many different perspectives as possible. Everyone here does have a voice, and we do want to make sure that that's included in our final synthesis of the workshop. At the conclusion of the workshop, we will synthesize our discussion and summaries into an overall impression. And the plan is to submit the workshop summary to venues such as EOS or BAMS, and to generate a white paper that outlines our proposed roadmap for future Gulf Stream studies. And speaking as a member of the committee, really the genuine hope is that this workshop is going to be the foundation for the next large-scale endeavor to study the multi-scale dynamics of the Gulf Stream as they pertain to climate. That may take the form of a large-scale field campaign. I'm an observationalist, but we will see what the next 2.5 days have in store for us. So the form of that endeavor is for us to decide, and I really do look forward to working with all of you between here and Friday. So thank you. So it is my, I guess, should I introduce Jim, you think? Okay. So we are going to get right started with our invited speakers. Leading off is Dr. Jim Edson, joining us from down the road. He will be giving a presentation titled "From Climate to OOI: Observational Challenges and Some Solutions," which is important, for the Gulf Stream region. Thank you, Jim.
All right. Is this working? Yeah, very good.
And I think you can advance with the mouse.
Yeah. Oops. And the mouse itself, I just click. Yeah. All right, before I click, oh, thanks for dimming the lights. That's very helpful. So I am Jim Edson, though. I am going to be focusing today's talk on observations, all right? I'm not going to dig too much into the science that we've already conducted with some of these observations over the Gulf Stream, but to give you some idea of the assets and maybe some of the methodology we use to make the most of these measurements. But I'm really looking forward to the discussion of the posters and then breakouts about once you've heard all of these invited talks. Are we still good?
Yeah, my phone.
I have a hard time standing behind the podium, so, but I'll try. How's that? This opening slide is useful. I'm a senior scientist in the Applied Ocean Physics and Engineering department here at Woods Hole. I've also recently stepped into, oh, that's great. Thank you. I'll just come over here. So I have recently stepped into the big shoes of John Trowbridge as the PI of the OOI Program Management Office. And for those of you who don't know what OOI is, it's the Ocean Observatories Initiative. And I'll talk a little bit about that today, but let's move on. Can I make this? That won't work. That's a little too fancy, perhaps. Right here, okay. So I thought it would be useful to put together this slide because I love the Gulf Stream. It is the most amazing natural laboratory for many things, but in particular, air-sea interaction and coupled boundary layer research. You can't beat it, okay? And so, but the thing is, of course, with that comes some challenges. And in this case, these research opportunities have to overcome things like strong currents and shear. Not everywhere, but current shear is an issue. Strong winds from coastal storms. I know people may be talking about nor'easters later on today. Large waves, but ultimately these waves are fetch limited, right? They're generally from the southwest, northeast, and so if you look at the Gulf Stream relative to landmass, it's not infinite fetch, but it's really cool because those waves are generally remain fairly well coupled. They're just big wind waves in this region, at least, for the most part. And of course, air mass advection, which is a really cool thing about this region, that we have a continent and an ocean next to each other, and we often have these cold air outbreaks, which are absolutely amazing. So we have met many of these observational challenges in recent field programs. I'm just going to mention three: Climate, OOI, and Peach. And so here's sort of three boxes showing where those three experiments took place. Climate is the oldest of it. Climate was a CLIVAR supported project to look at mode water formation in this region, and in particular 18-degree mode water formation, of which air-sea interaction plays a huge role in maintaining that mode water at 18 degrees. I use this. And you can kind of look down here at my color bar. The yellow is 18.5 degrees, or there's about, and so you can see this, it's really at the edge of the northern wall of the Gulf Stream is where you find that 18-degree water. We managed to keep a buoy out here. It was mainly in, but in this particular figure was sometimes out of the Gulf Stream due to the meanders, which is really interesting because we were using the meanders to look at spatial correlations and things like that in one of our papers. So I'm going to be focusing on climate. I just wanted to say a few words about the OOI Pioneer Array. And it was designed to look at cross-shelf exchange. And what I think was unexpected was the robust interaction between the Gulf Stream itself and the continental shelf. So we were seeing eddies being shed off, impacting all sorts of things up on the continental shelf. So even though it was at the cross-shelf front, the Gulf Stream itself played a big role in a lot of the science that's come out of that program. And likewise, this is the most recent one, is Peach. And it's, a very interesting spot. I'll have a schematic later on, where the Gulf Stream moves from being sort of coastally trapped here to having sort of a free wave form out here. I'll say a little bit about Peach, but in the interest of time, I'm really going to focus on the Climode experiment and a bunch of other things. And I think this is easiest. All right, so here we go. This was Climode, and an amazing experiment, really was. I was so glad to be, happy to be a part of Climode. And so you can see the various assets, and I'm going to talk about these in general. We were really hoping to keep the surface mooring out all the way from 2005, November of 2005, to November of 2007. Well, we kept it out for 15 months, a whole year, and then we turned it around, and it made it about halfway through the winter before the combination of that strong current and the stress on the mooring line and surface waves pumping that buoy up and down caused it to break free, and we did recover it, got all the data back. But it just says something about how energetic this region is for air-sea interaction studies. So the white down there is the only thing that didn't quite work out the way we wanted it to. And come on, there we go. So again, this is one of the really amazing things about the Gulf Stream. So we're typically have, say, 14 degrees Celsius shelf water adjacent to 22 degrees Celsius Gulf Stream water. And what we often have in the case of a nor'easter like this is cold air outbreaks. And the convection is so intense. And I actually, during the pilot experiment, we were out there when the 0-degree isotherm reached the ship, and we were in the middle of the Gulf Stream. So that's a delta T of 22 degrees Celsius. And under those sorts of conditions, it's so advective, even though it's in the middle of the winter, we saw water spouts out over the Gulf Stream, right? So that was Al Pluteman took that picture during his leg. So that's one thing, and just in general. Did that work? Yeah, it did. Very good. Just in general, the net winter heat loss in that region is the largest of anywhere on the planet, right? It averages 400 watts per meter squared. That's incredible. That's half the solar, a third the solar constant, all the time, cooling the ocean in this region. And of course, this is just to show you the drastic changes that we experience when you're out over the Gulf. So I'm out over the Gulf Stream in the middle of January, launching a balloon there. I'm in my shorts, and it was very comfortable in my shorts. I remember a few hours later, it was snowing there. And so I then had my Mustang suit on to launch balloons. So things got very different very quickly. But you can kind of just see in the background, it's like you're in this incredibly convective region, but it's the middle of the winter. So again, just a great natural lab. I think that's it for that slide. Yes. So I'm going to just talk a little bit about these assets. The big three on this one is the air-sea interaction spar, or ACES, which we deployed down here. The ships, we used two ships, the Atlantis and the Nor, for the two experiments. We had a pilot experiment, and then the main experiment in 2006 was the pilot. The main experiment was in 2007. So it did a lot of these transects you're seeing here. The numbers are CTD casts. So they were busy doing CTDs. And then, because the star of the show was this central mooring, which again in this picture was outside the Gulf Stream. Believe me when I say it was generally inside the Gulf Stream, probably 2/3 of the time it was in, 1/3 out, right? So you can see here just in this graph, this green line here is the track that ACES took. It was freely drifting. We tried to put it at the core of the stream here because there is minimal shear at that location, and there's lots of shear on either side. And then, well, one more thing I was going to say. I think that's enough because I'm going to show you a kind of cool graph. Now, I'm going to explain this just a little bit. All right, so these are the CTD locations that were shown on that map, okay? I'm showing 1, 2, and a third will pop up shortly. This is the location, and this is the trajectory of ACES. Right? This blue circle, I believe, has a radius of 10 kilometers. And if and when the ship got within that 10-kilometer circle, we could talk to the ACES directly with a high-frequency radar and download tons of data and make sure that it was working. Okay, so you'll notice a brief moment when the ship is inside that circle, and we were able to download data. The green is where the ship was, and you'll see every time it does a CTD, it'll drift slightly and make a little notch in the trajectory that it takes. So I'm going to run this little movie I made. Here it goes. All right, so you can watch the ship is doing CTDs. And watch right there. So I think we had like an hour that we were within that radius, and we were able to download quite a bit of data in that island because it was a high bandwidth way of getting data off. So a very nice thing about ACES is that where we put it, it stayed in the region of the least amount of shear, but also sort of at the maximum of the temperature. I'm going to show you why that is of use. Oh, I must be off this. It's a little, for those of you giving talks, you'll see there's an arrow that you should hit. All right, so here again is that figure showing where the ship was. It is sometimes hard to see. So here's the trajectories here, and it's sometimes hard to see some of the these features. So I'm going to actually number them. So and these are the 4 times that we went through the Gulf Stream northern wall and into the cooler shelf water. There's 1, 2, 3, and 4. Now, what I wanted to sort of point out here is this is the ACES temperature. And remember, we're losing 400 watts per meter squared of heat, and so the Gulf Stream was slowly cooling during this deployment. You can see that there. And the other thing is kind of neat, is because we put it in the maximum, right? That's as warm as the ship was seeing. So the solid here is the sea temperature measured by the ship. And what's kind of interesting is, so here we're going all the way down into that cold shelf water, right? We're getting down here around 14 degrees Celsius. And then back we go across the Gulf Stream to that maximum. And then actually what's happening here is you cross over the maximum, right? The temperature goes down a little bit as you go past that maximum. You hang out there for a little while, now we start our transect back towards the cold water, hit the maximum where ACES was, and then again we see this big drop in temperature, right? And so a key to these huge fluxes that we see is the following. So here is an image. I'm just going to talk to it, and I'm going to draw lines across where the means are. So that's the mean and the wind speed. 15 meters per second, mean. So 30 knot mean. I mean, you're lucky sometimes on these field programs to see 30 knots. We saw it on average, and as a result, you're kind of beat up on the ship. You're banging into walls all the time, but it's worth it, right? Because we're collecting this amazing data. There we go. And so the minimum temperature while we were out there for this leg was 5 degrees Celsius. Like I said, I saw 0 degrees Celsius during the pilot cruise. And then pretty dry, amazingly dry, given that we're out in the middle of the ocean. I think it's hard to see from where I was, but something like 65% humidity, all right? Which means it's dry enough that we're really driving huge moisture fluxes along with the heat fluxes. And so if I could just show a couple of periods, because there's sort of 3 ingredients to the huge fluxes. One is high winds, all right? And so the one that I just showed was a little less than 20 meters per second. Huge delta T, all right? And pretty huge, because you can see it's closer to 55, 60% so it's dry. It's cold and it's dry. This is during one of those outbreaks, but we also have high winds. And the second one is right here. We have even higher winds, similar delta T, a little bit moister. But it turns out that the high winds wins in terms of driving that latent heat flux. And so I did. Let me just do this. So at those two bars, those two occasions, you can see the type of heat fluxes we're getting. Over 600 watts per meter squared for the latent heat flux, of order, 250 here. Similarly, we did, I think this could have been the record here, was was close to 800 watts per meter squared in latent heat fluxes, right? Add the two together, we're typically around 1,000 watts per meter squared, right? That's the amount of solar energy we get in the middle of the summer, right, as a maximum. And we're getting these sort of conditions all the time. Again, amazing. I hope you're getting the point here is what a great place to do field work. This is something I'm just going to show. This is my best example of why you need to measure relative to the ocean current and not relative to Earth, right, for your fluxes. And what I'm showing here is the results relative to Earth. And so the red is when we're in the Gulf Stream by just a crude, I think less than a half a meter per second. There it is down there. And then the blue is when we're outside the Gulf Stream. No, it's not surprising that we get these underestimations of the drag coefficient when we're in the Gulf Stream, but they're still smaller in general, even when you're outside the Gulf Stream. I like to make this point to people. That's because on average, the wind-driven currents are in the direction of the wind, right? And that means that the relative difference is smaller. And so, so you need to take the currents into account, and you get this. So I'm gonna go clearly when I'm relative to water, I collapse the data and get, for no matter where I am, whether I'm in the shelf or in the Gulf Stream, and then prove my flux parameterizations. I don't know if Hyodae is going to be talking something about current a little bit for your mesoscale work, but this is what we got during climate, and I've seen this consistently now of many, many, many data sets. Keep going here. So this is something that I'm extremely proud of. This is a comparison of the bulk and direct covariance measurements during climate, and it's a little hard to see, but there are two lines, bulk and direct covariance for the stress, and there are two lines, but you can see there are differences. Not huge differences, but differences. And those differences, I swear I'm trying, are going to be included in Core 4.0 to get the heat fluxes right as well. So this is, I think Justin is on the line. So this is just a little bit of science here. So it's been commonly observed, especially with the scatterometry community, and Larry's over here, he's the king of scatterometry, that we find higher winds over warmer water and lower winds over cooler water when we look at scatterometry results along with SST from satellites, especially when you average, say, over a month, 30 days, right? You see this very clear picture, right? And so one reason for that, one explanation for that is just surface layer adjustment, MO similarity theory. That would account for some of this, but from our studies, it's something like 30%, right? This is not really thermodynamic, and I've sort of shown already that, we need, or not this one, this one is just kinematics, but it's also pretty clear from, looking at the literature now, both of these explanations remain viable, right? This one here is, just want to make sure I have the right one. Yeah, this one down here is a little bit more like a sea breeze sort of mechanism, but here out over the ocean and using gradients in the SST. And this one is a little more interesting. It's just as you go over the edge, an SST gradient, especially a strong one like the Gulf Stream, you do see the boundary layer adjusting. And we do believe that as part of that adjustment, you're mixing down higher velocity air over the warmer water, right? So both of those are viable in order to, and they have been tested numerically, most certainly, but there's just not a lot of measurements of boundary layer profiles as you cross these big SSTs. Well, we did, here, I'll go to this. We did during climb mode, all right? I want to point out, this is kind of a fun way to plot the soundings before you kill them, right? This is where they are in space, right? And you're going to see, I'm going to focus in on this section, because this was a time when the ship was actually going steaming into the wind, as you can see from the surface winds here. They're going this way, right? And then they get aloft, and I'm sure it's thermal wind adjustment and just synoptic systems in general. And they tend to then start heading, at least during this period, to the northeast. So we're going to focus in on this. I wanted to make the point of this pattern. I actually had some say during the pilot experiment about the pattern that we made. And I said, why don't we just do sawtoothing, right? That would be interesting. You'd get what you want, profiles across the Gulf Stream. And hopefully there's times when I get what I want. Well, during the pilot experiment, this was pretty much the only time when we had the right combination of the ship's direction and the wind direction, and everything kind of came together, and we have, a nice series of profiles for that. And this is what they look like. I don't know if you can see this. So very shallow boundary layer in the stable side of the front. It was quasi-stable. And then this is actually, I believe, the top of the boundary layer here. And then when you get inside the Gulf Stream, this is in the interior, sort of all bets are off. You need some modeling work, I think, to figure out what's going on there. You have sort of that onion look. There's something going on here. That could be advection from south of the Gulf Stream. Who knows? You'd have to look at that more. Now, this is what happens when the oceanographers have control of the deployment. So they were definitely hunting for gradients, right? And unfortunately, we still could have, with the ship, done gradients like that, right? And actually looked to see what the winds were going to do and position the ship the way we wanted to. We were at the mercy of what the oceanographers wanted to sample, and fortunately so we got out of all of that, there's probably 3 or 4 test cases, this being one, where we crossed the front here and the winds were cooperating, the direction of the winds. And so now it's actually even clearer because I've zoomed in now. We're at 1,200 meters. So here's and we're going from the colder water here. This actually shows the temperature, the sea temperature, right? So you can imagine these things, if you were able to get closer, they would go to that value. But as you go into the Gulf Stream, very clearly the boundary layer is growing from down here, 550 to closer to 1,100 feet. Okay, so this is definitely a reaction of the boundary layer to the Gulf Stream gradient, but there's very few of these sorts of measurements. There would be a lot more if the meteorologists had control of the ship. Right? So we need that sort of experiment. And then these are just some things that we've been working on. I did want to make this point. So this is, as we steamed across that feature, you can see that the temperature was pretty cool, right? Down around 5 degrees Celsius, warmed up substantially during that transect. And the air temperature is the red. And anyone that tells you that air temperature and SST are lockstep is full of it. The air temperature it is responding quite clearly, but it's not like they're just, it's 1 degree difference all the way during this. So that's an important thing to know, because there are a lot of people that assume that it's a constant delta T, for example. It's not, right? And this is where numerical modeling really can play a role. And you can also see here that we wanted to see how quickly the surface layer adjusted to the surface fluxes, the new value. It's pretty quick. It's of order 10 kilometers, right? So it doesn't take long for the atmosphere to adjust to this drastically different SST. That was another take home. I'm not quite sure what's going on with here, but we could really use more data and more transects to do that. How am I doing? Okay, because I am getting there. So a couple of other observational assets I wanted to bring to the group. This one is this is near and dear to our heart. This is a spar that we developed at WHOI. It puts sensors at about 7 meters above the ocean surface. That sonic anemometer, you cannot develop, I can't imagine a different platform that has less flow distortion. So we really worked hard to get as little flow distortion as possible. We're very good at motion correcting now. And this was able to give us in near real time, so we were actually computing the fluxes on the fly, which is no mean feat. That's 10 different time series you have to merge together to get a flux. But we were getting these nice time series of the surface heat budget, wind stress and waves, and these are waves, that's 10 meters, and I think that's accurate, 10-meter waves. And you can see a lot of this region where we deployed this was a ton of variability. I don't know if you could ever guess where that region was, but it was here in the Erminger Sea. This is kind of a fun plot. So I'm gonna run this forward. Here's where ACES was. This is gonna move, right? And this is gonna move. This is where the WHOI Erminger Sea buoy was, and it's a raise. And I'm only realizing now that I can do a really cool comparison study between that buoy and the ACE and the X-bar. Did I call it ACES? Sorry, X-bar, expendable spar buoy, expendable because all that data is being telemetered in near real time. And you'll see it was a good thing on this particular deployment because we put it in probably the worst place in the world to do a beta test. And it lasted for 3 months and finally a storm took it out, right? But all the data came back. So all the data that I showed in the previous slide was telemetered. I'm gonna see if this will go. There we go. So follow the buoy, all right? Here it is. It actually, no kidding, it goes through the eye of Epsilon. What was Epsilon? Well, it's not a hurricane here. It's the remnant of a hurricane. It went out extratropical. You can see there's fronts and stuff on this plot. Nonetheless, we survived that storm. We survived many, many 20-meter per second storms during this deployment until it finally had given up. And we actually recovered this part, or the Norwegian Coast Guard recovered that part of the buoy. So it's very rugged. We need to do something about the mast itself. It needs to be ruggedized somehow. But for places like the Gulf Stream, under normal conditions, this would be a terrific asset for the program. Let me keep going here quick. So this one I'm going to just walk through pretty quick. So there's a lot of activity with offshore wind farms. And actually these colored regions are lease areas for individual companies to build their wind farms, right? As part of this, DOE has funded a group of us to effectively set up an ocean test bed to characterize the coupled marine boundary layers. And so just part of this is we have offshore the Martha's Vineyard Coastal Observatory and its air-sea interaction tower. We're going to do what's become commonplace, which is glider operations, some AUV operations, and then just monitoring buoys wherever we can put them, which could be in terms of the Gulf Stream on either side of the north wall would be one way to use such things. And then balloons, tons of balloons, but also remote sensing, right? More and more we're able to utilize the remote sensing elements at sea. This is an awesome platform. It's a standalone platform. You can see ACID in the back, which also has a LiDAR on it. And so we're using the tower to certify these LiDAR buoys. And these LiDAR buoys are great. They get up to, say, 300 meters typically, right? They're trying to get up above hub height when you have these LiDAR buoys. So I expect those sorts of moorings to be a big part of field programs going forward for your sea. This is the most fun, though, thing, is that in order to get further offshore to make measurements that get the ACID, we're either going to buy or lease a barge, a big old barge. And there's a picture of a barge down here. We're going to add an ACID-like tower of at least 20 meters on the front of it. We're hoping it vanes a certain way. We'll deal with that. But also the other thing is it's going to have a ton of power for remote sensing devices. So it's a really cool platform to sort of extend our array out into the middle of the shelf, at least. But here's the big thing that we all hope is coming down the pipe, is a number of people are working on not only this type of, where we've actually driven piles into the ocean surface. Problem with that, of course, is you're limited to like 60 meters is about as deep as they want to go with that technology. But it works very well. The other thing, of course, is you got to get rid of it at some point, and it ain't moving. So what we've been talking to people about are some of these other approaches where we have either a floating or a hybrid tower using the technology that's coming out of the wind energy sector. This one is particularly cool, I think, because you can set this thing up in port, attach it to a tug, pull it out to where you want it, drop the legs, and you've got your platform. And when you're done with the experiment, after, maybe it could be a whole year, 2 years, you pull up the legs, you float it back to port, and you fix things. So this is a very attractive way to do these sorts of measurements in shallow water. If you're on the West Coast or in deeper water off our shelves, there are other technologies that are purely floating technologies, also very cool. Why are we into this? Well, Carolina is one of the first to talk about this idea of supersites. Okay, very good. So these are ocean laboratories. These are ocean test beds that I think the community is desperate for. And this sort of takes all those different elements I've been talking about and pulls them together. And again, we're not doing this ourselves. There's a lot of smart engineers that are floating turbines on these floating platforms. And if they can do that, they can put a 100-meter or 200-meter met mast for these measurements. Because we've got to get up. We got to get into the boundary layer. Last thing, I don't know if people have heard, we've had a very successful run with the Pioneer array up here on the shelf break front, right? A lot of papers are now being published. That data is going to be readily available forever for the life of the program, which is 30 years. But part of Pioneer, the name, was that it was going to go someplace, right, after X years. In this case, turned out after about 6, 7 years, we're moving it down here to where Peach was, very close to where Peach was. In fact, this figure comes from Dana Savage, who's a participant in the Peach project, showing some of the complexity of the currents in this region, because sometimes you see a lot, we have freshwater effects from the Chesapeake Bay. The Gulf Stream itself comes very close. Now, this is, I think the Gulf Stream would do that. But does the Gulf Stream always do that? Of course not. There's going to be meanders. There's going to be interesting things. So the Pioneer array as proposed here, and we should have that out there in, I think, the spring of 2024, would be a terrific asset as sort of a downwind boundary condition for our Gulf Stream project. So I just want to make that point. And so this is the last slide. I've talked about a bunch of these assets. I expect to hear more, and in particular, some really important assets like UAVs. I think I stole that from Chris Zappa, who's here in the audience. Sail drones, Jamie's going to be talking about that, I'm quite sure, about how to keep sail drones operating in the Gulf Stream. And here's a wave glider. So all these have been shown to be excellent platforms, but they have to meet those challenges, because trying to operate these things in strong currents can be difficult, right? So leave it at that, and I don't know if there's time for questions, but thank you.
Yes, if there are any questions, we'll be passing out.
Oh, Megan. Yeah, hi, Megan.
So you were talking about the assets with the barge and the LiDAR, all of that. Is that going to be happening for the purpose of the offshore wind energy, or would that be just incumbent upon us research community to make that happen?
So it is going to be built, and DOE is paying for it. We'd like to use it as a prototype for an ocean test bed that we can keep running, because it's going to be, it's going to be a year and a half, I think, out there collecting data. We would love to keep it out there longer, but better yet, we'd like to think about how can we do something like that in the Gulf Stream, right? Or have assets like that in and outside of the Gulf Stream. But the good news for now is it is being funded, and we could keep it going, yes.
And is the data going to be publicly available?
Yes, absolutely. We have to.
Yeah, the question was, will the data be publicly available for those online? Yeah. And it will be, yes.
Yeah. We may have a couple of years first whack at it, but it's the data management plan says this is going to be made available.
We have an online question from Elizabeth Thompson from our Scientific Organizing Committee. An observational obstacle I see is deconvolving space and time variability. How best can that be accounted for or addressed regarding your time series?
Right. Ingesting it in numerical models is one way. So data assimilation is one way to deal with those sorts of things. It is a challenge. I mean, we're challenged right now with all the glider data that we have that you're trying to, how do you relate that to an Eulerian measurement? Because we have plenty of Eulerian measurements and a bunch of Lagrangian measurements now. And there's, people make a living out of trying to combine these sorts of things. But I do feel that good models are a great way to combine those sorts of data. Okay.
Any other questions from the audience here or online? Okay, thank you very much, Jim. That was great.
Who's next?
Arnaud.
Okay.
Okay, our next speaker will be an online speaker, Arnaud Czaja. Am I mispronouncing that? Okay. I apologize, Arnaud, if I've mispronounced your name.
No problem. Shall I share my screen or?
Yes, you can share your screen. We see your slides if you want to throw it into presenter mode.
And can you hear me okay? Is the sound correct?
Can you put it up a little bit?
Is the sound okay?
Oh, that sounds very good, yeah.
Lovely. I can get started then?
Yes, if you'd like to put your camera on, we could see you in person here.
I'm
If
sorry.
you're not comfortable.
No. Where is the bar now? It's a bit slow, sorry to respond.
It's hard to find the buttons when you are sharing screen, yeah.
Can you see me okay now?
Yep.
And can you still see my slides?
Yep.
Yeah, lovely.
All set to go.
Great. Hello everyone. Greetings from London. And I'm really pleased that I can participate to this workshop remotely. So thank you for that to the organizers. And what I would like to discuss in this talk is quite a big change of gear compared to the previous talk. I'm interested in this question about, we're seeing all these amazing Earth interactions over the Gulf Stream, and it's clear that it affects the marine boundary layer above it. But what is really the impact at upper levels of the atmosphere, the troposphere, in terms of the jet stream, even the structure of the storm tracks? And when you work on this, it becomes quite clear that it's quite perplexing. And I remember a few years ago, I used to work in the US, and I was watching one of Brian Greene's video, and he had this film called The Quantum Cafe. And he wanted to explain, give a feel what it would be if a coffee shop was behaving like in the world of quantum mechanics. And for example, he goes in the cafe and he asks for an orange juice, and the waiter looks at him and says, "I'll try." And I often have the feeling that this is a bit what's going on when you put a sea surface temperature anomaly under an atmospheric GCM and you're trying to get a response. So I'm going to just illustrate this with one particular example. This is a relatively old experiment, but I think they put their finger on some gold there, something really fundamental and really interesting. It's an earlier study from Peng. And in this particular experiment, what Xilin did was to look at the impact or the ensemble mean response of an atmospheric model to a sea surface temperature anomaly, which I'm showing here on the northwest corner on this left panel. Can you see my mouse when I move it?
No.
No? Okay. Let me go to, can put a laser.
Did we just see the slides? Oh, we can see your mouse.
Yep, lovely, great. What was really striking in this experiment is that for the same model, which at that time was pretty much a big state-of-the-art atmospheric GCM, general circulation model. By our standards today might be on the coarse resolution side, but what she found is that if she initializes the model in November, and run the sea surface temperature anomaly and integrate for a couple of months, she obtains a high surface pressure response here shown in the middle panel. Whereas if you do the exactly same experiment, but you start a little bit later, same SST anomaly, same model, just start in January, February, you get completely the opposite. Instead of getting a column of high pressure, you're getting a column of low pressure. And there's many examples like this in the literature. And I think it's really asking a really important key question, because for our forecast and our climate prediction is the forcing of changes in the atmospheric jet stream by the Gulf Stream, is it fundamentally a case-by-case problem in which the details matter? You really need to know exactly how you force, what is the sort of model you're using. Small perturbations in the pattern of SST or the structure of the model will completely lead to different response. Or are there processes within the coupled ocean atmosphere system which are missing in the current modeling framework? And if they were present, they would lead to a more linear state of affair and maybe give us more confidence in our predictions. So I'm going to delve a bit into this in this talk. And I'm going to start by reviewing a bit the literature in terms of observed and simulated response of the jet stream to SST changes. And essentially, I'm going to reiterate the message that there is some sort of quantum cafe behavior going on here. From the literature, we can also work out where is the cause of this, and also propose a sort of framework to understand better how the atmospheric general circulation model respond to SST changes near the Gulf Stream area. So that's what I will do in the second part. And then I will focus at the end on the mesoscale structure in the ocean and the atmosphere, because these are the things that we're starting to resolve better in our numerical models. And they are introducing a lot of really interesting questions. And to be really clear, I'm really focused here. I'm going to focus on upper levels, focus on the winter time essentially, and time scales on weeks to winter to winter, this sort of things. So in terms of response of the atmosphere to SST anomalies, I decided to focus on two types of SST patterns, which are quite discussed extensively in the literature. Probably the most famous one, or the most classic one, is the one on the right here, which is the so-called SST tripole. And this is the sort of sea surface temperature anomalies that you observe when the atmosphere goes into a positive NO state with warmer conditions near the Gulf Stream. The other pattern that has been of a lot of interest, and especially obviously for this workshop, is the sort of SST anomalies that are observed following a shift, forward shift of the Gulf Stream. So I took this from the work by Yong-Ho and Terry Joyce. And this is an example of the sort of changes that they are arguing is going on with a warming slightly to the north and along the current in the Western Atlantic. So I'm going to look at these SST anomalies and look a bit in the observation as well as in numerical experiment. What is our what is our evidence that the atmosphere cares and what is the actual response. So I'm going to do this by plotting things in this diagram where I'm putting on the x-axis the SST anomaly near the Gulf Stream. So positive, say +1 would be warmer condition near the Gulf Stream, and -1 would be colder condition near the Gulf Stream of -1 Kelvin. And I'm going to put on the y-axis the response in sea level pressure. And essentially because sea level pressure is, I found was the easiest because most studies give the signal in sea level pressure. But I want to emphasize that all the responses I'm talking about here actually have this vertical structure such that you essentially see the same response all the way to the tropopause. So these are really characterizing jet stream changes. And the sign of the anomaly for the pressure, I just chose a convention that whenever I say it's positive in response to a warm Gulf Stream, it's the convention that you have something that looks a bit like a positive NAO circulation. So it would be with low pressure in the high latitudes and positive pressure anomalies in the mid latitudes, like a positive NAO type. So in terms of the we first look at the SST tripole experiment. So we got quite a few experiments that were done in the early part of this century, and they are shown here. They were done with relatively low resolution general circulation model. And you can see that the responses that people tend to show are always the difference between warm anomaly and cold anomaly. So there's a sort of symmetry here. So that's why I put the same values for either a positive anomaly or a negative anomaly, just symmetrize it. And I also put an estimate of the response of the atmosphere to the SST tripole that Claude Franquinul and I worked out a while back, which is shown in this open square. In all these slides, I'm going to show the color will always be some AGCM, and the open symbol will be observations. And so what is interesting here is we don't seem to see much of quantum café type behavior. These models were all quite different, and they all seem to agree with the observation also in terms of amplitude. I put this line here about 2 hectopascal per Kelvin, which gives you an order of the sense of the forcing. And they're all consistent with deciding that there's a positive feedback of the SST tripole on DNAO. So via air-sea fluxes, DNAO is driving changes in the upper ocean and creating the tripole, and the response of the tripole is to reinforce the state of DNAO. Now, it's a very, very different situation when you actually look in the literature at the response to a Gulf Stream shift. I have put here a couple of observational estimates. So we have Claude tried to estimate the response in reanalysis to Gulf Stream shift measured by top exposure ion altimetry and was unable to find any. So that's why I put 0 here for the study by Claude. And Yongo and Terry Joyce also tried to estimate. And they, interestingly, they found a response that would correspond to, for warmer condition near the Gulf Stream, they would tend to have more blocking type situation to the high latitude, so which in my convention is like a negative NAO type signal. But you see that in terms of modeling, I put here the modeling by Hyodae, which was really trying to explore the whole range of parameters of response to a Gulf Stream shift. And you see here another example of sort of quantum café behavior, where if you take an SST anomaly of only less than 0.1 degree C, you get the same answer as an anomaly of 3.5 degrees. So something very, very difficult to understand is going on here. I have also added a couple of other studies which didn't specifically look at a measure of shift of the Gulf Stream based on subsurface data or altimetry, but try to track shift of the Gulf Stream using sea surface temperature gradient. And that's a lovely paper that's now in press in Journal of Climate by Luca Famos Paolini. I think he's on the call, and the Bologna group there. So I also added an observed response from Wills et al., which is quite close to the sort of analysis that Luca did in his work. And what you see is that essentially it's a bit of a mess, really. We can't really say, if we know the state of the Gulf Stream, do we know the sort of structure we're going to generate? There was indication from the study, the famous Paolini, that maybe the high resolution model, which are shown here, you see the 50-kilometer model and 25-kilometer model, that they're definitely behaving differently than the low resolution model in this high resmi series of model. But it's difficult to argue that that's necessarily always the case. You see the model by Hyodae is a 40-kilometer model, and it's closer to the 100-kilometer run for warm conditions, for example. And obviously, if you put everything together, I defy anyone to sort of find a general trend here. So this is, to me, saying we really need to understand what is causing the spread of this model. And I don't think it's an artifact of our modeling. I think there's really something fundamental in the way the atmosphere and the ocean interact, which is leading to that. And I want to now try to address what that is. So I think the key starting point is that the anomalies in jet stream that we're looking, whether we're looking on weekly time scale or year to year or decade to decade, they have a well-defined spatial scale. I'm showing this here, looking at those fields of upper level vorticity. And if you look at just a relative vorticity in color, you see there's well-defined structure with about a scale of about a few thousands of kilometers. And this is the atmospheric deformation radius. And this imprints itself on the ocean. Obviously, when the anomalies in the ocean are created by air sea fluxes, you tend to get similarly scales of 1,000-kilometer anomalies. But also, I think the shift in Gulf Stream also leads to this sort of scale because of the length of the current. Even though the scales might be quite small across the stream, downstream of the current, this introduces, again, this sort of length scale. This is quite a technical result here, but I think that it's really important just to get the idea of that. It's basically that if you have, on the scale of the atmospheric deformation radius, the dynamic is quasi-geostrophic. And it has been now shown and repeatedly demonstrated that this captures really the zero-order behavior of the jet stream storm track interaction. And there is a really lovely paper by Jeff Whitaker and Prashant Sardeshmukh a while back, which really showed how you can understand the variability in the jet stream and the storm track using very simple linear arguments. And you can essentially understand that there is an approximate balance between the generation, the transient growth of meanders of the jet stream, their dissipation, and their excitation by noise. So this sort of equation I'm going to use a bit just to put terms into, to be clear about what I mean in different things. So this will be the eddy statistics in this case, with the sort of eddy covariance matrix. This D is a damping, this is a transient growth of system, and this is the stochastic forcing. So in terms of the Gulf Stream's role, we can understand quite a lot of studies which have been discussed in the literature. And I think most of the sort of sensitivity and the root cause for this perplex result, this quantum café behavior, comes from the L term. That was one of the key results from the studies by Shilin Peng and Jeff Whitaker, is that there is a huge sensitivity of this L term to the particular background flow that you are considering. So the Gulf Stream, for example, would have a strong impact in changing the mean bioclinicity, for example, in the Western Atlantic, and would lead to favoring transient growth in certain preferred locations. This is the sort of key source of quantum café behavior in essentially low resolution model, because they don't have much sort of noise, this forcing term here, which would refer to everything that's smaller than the atmospheric deformation radius. The role of the ocean that's rarely discussed, though, and that's probably the main role of the ocean, is actually to damp the storm track. It's a big, when you run an atmospheric model with a shallow, small thermal inertia or a more realistic thermal inertia, you see very quickly you're damping your weather systems. So a big source of the damping is actually the air-sea interaction, but I'm not going to talk too much about that. The term that is really going to be really important to understand and focus is this forcing term here. So anything that's below the deformation radius scale, so think on scales of tens of kilometers or even hundreds of kilometers, and how this is affected by the Gulf Stream. So this is what I'm going to develop a bit, building really on the really nice work that Shoshio Minobe did a few years ago now. So I think the key idea is in terms of understanding how the noise in the atmosphere, the small scale structure in the atmosphere, can be affected by the Gulf Stream. Is that goes back to an initial idea by John Green et al. At Imperial College in the 60s, where they really envisioned the weather systems as open systems, in the sense that you cannot balance the strong ascent that is going on along the fronts embedded in a cyclone as being balanced locally within the cyclone. The air is ascending in narrow updraft and is being spread out at upper level, flows with the westerlies and sinks slowly on time scale governed by radiation. And this is very important because there's a lot of arguments, and I'm showing just one example here, which are showing how the Gulf Stream is very likely to favor strong ascent. And this is the argument that I particularly like, which has to do with not so much strong air sea flux. I think the previous talk emphasized a lot the strong air sea flux, but I think for a lot of problems, actually having very weak heat flux, which is the more important. And this particular situation here, what is going on, the reason that you see a lot of fraction of the time in winter where there is ascent from low level to the tropopause is because the air parcels which are ascending in a warm conveyor belt of cyclones, they are flowing along the warm waters of the Gulf Stream. So there's very little sensible heat flux. They still gain a little bit of moisture. That gives them a very high moist potential temperature, which compares well with that at the tropopause. And so in terms of buoyancy, they're able to reach to high levels. So the key thing is that essentially you're having an ascent which is preferred, especially in certain locations by the Gulf Stream. And this happens all the time, but it's not like a clock. So it is really something that's quite random with some sort of time mean structure, with a time variability and a well-defined spatial structure here. So this is this sort of F term that I introduce here, and which I'm going to argue as some good and some bad for the climate models. I think on the good side, I think it explains how and why the models start to getting an improvement in their biases in the jet stream position. I show here some results from these experiments where you take an atmospheric GCM and you force with the observed SST or a smoothed version of the sea surface temperature field. In those experiments where you compare the difference between the realistic SST and the smooth SST, so this is the sort of anomalies, you're generating big anomalies of several degrees. But I think systematically you start to see this sort of anticyclonic circulation at upper level downstream of the Gulf Stream. This is shown here in this study by Piazza et al. And this is our own analysis of some of the experiments of the paper by Minobe 2008, where when we compare the geopotential height difference at upper level between the control and smooth, you see this development of this high pressure at upper levels. And I think this is completely consistent with this view of the organization of the convection that starts to be resolved in model of about 50 kilometers. That's when you start seeing this. This is just to illustrate the idea where if you put a line source of vorticity mimicking the location of the Gulf Stream separation and extension in the Atlantic, and this acts as a negative source of vorticity because the Gulf Stream is favoring these upward motions, and they don't balance locally, they balance somewhere else. So the net effect is to squeeze the upper levels, so the vortex squeezing, so it acts as a negative sort of vorticity. And this is the response in a sort of linear barotropic model you get, and you very easily generate this sort of forward shift of the jets and anticyclonic structure at upper levels. That's the good news. I think could improve the model biases, and that's a sort of response to the time in presence of the Gulf Stream. But where things get quite new and maybe even more challenging is in terms of look on shorter timescales. And I'm showing here some experiments that were run at ECMWF and that were analyzed by Alison Cobb in a PhD thesis. And the idea was if you just focus on these red dots for the moment, so these were an ensemble of forecasts on a given day. And this red group here is analyzed about 3.5 days after the initial state. So this ensemble of forecasts has already had a bit of time to develop its own spread. But as you see in this diagram, which is focusing on the small scale, so on the sort of noise, anything that's smaller than 300 kilometers. And this is a sort of a source term for this mesoscale activity. We see that the red ensemble is in some sort in the left-hand corner. And that was when the cyclone was approaching the Gulf Stream. It wasn't yet crossing the Gulf Stream. It crossed the Gulf Stream by 12 hours later, which is shown in the blue ensemble. And you can see that the blue ensemble starts to have spread quite a lot in this diagram. And to give us a sense of how big is the spread or how small is the spread, we've indicated here in green simulation with the Met Office model at 12 kilometer resolution, where we did this realistic SST in the control and the smooth SST near the Gulf Stream. And you see that the red ensemble has a sort of level of variability, which is comparable to that you don't get when there's no Gulf Stream. As soon as you put the warm core of the Gulf Stream and you allow this ascent and the development of updrafts, shear instability, and you're getting a lot of variability spread of the ensemble, and the level is comparable to the sort of level that we observe indeed when we impose the presence of a Gulf Stream in our SST. So just to finish on this mesoscale, another source of interesting ideas that have been floating now for a few years has to do with not so much the atmospheric noise and the Gulf Stream, but more the ocean noise and the jet stream. And the idea that in the boundary layer there is an organization of the specific humidity, air temperature, and updrafts and downdrafts at the top of the marine boundary layer by the oceanic mesoscale eddy field. That started some really nice work by Justin and the papers by Xiaohui Ma, Ping Chang, and Saravanan in Texas. And I just want to emphasize that this is a mechanism that you indeed start to see in model with a resolution of 20 to 50 kilometers. But I want to emphasize that this is not associated with a sort of external forcing by the ocean currents. It's a mechanism that you can bring back to this sort of old ideas. It has to do with favoring the development of weather system in certain locations. So in their study, people emphasize the fact that the warmer and moisture environment is conducive to more baroclinic growth of the weather system. So in a way, this is still in the world of quantum cafe, because we are inherently having this problem of the fact that the eddies are very sensitive to a background flow, and that will not change. But it's quite different for this sort of forcing here, where the forcing here has a sort of timing response which is well structured and which imposes a more robust response, as we've seen here, but introduces some stochasticity. So I'll just finish with a very open question, which I think is very interesting when you think actually about the mesoscale circulation in the atmosphere themselves. If you think about fronts, the idealized model of fronts are inviscid, and they develop a front as singularity in the vorticity field. But they haven't addressed what actually set the scale of the atmospheric front. And I've always been very surprised that if you compare the mesoscale in the atmosphere, which is when the Rossby number goes to unity, it is on the other 100 kilometers, which is on the other of the oceanic mesoscale, which controls the sort of scale of across the currents. And so is that a coincidence that these two are, and some of the ideas that Rhys Parfitt has been analyzing at FSU are really maybe helping to argue that it's not by chance, and that there is a preferred sort of interaction between the front which sets their scale. And that's something that would be really interesting to look further. So in summary, I think the first main message I wanted to convey was that when it comes to the forcing of the jet stream by the Gulf Stream, details matter. It would be lovely if we could just use some old ideas, say the type of Hoskin scouring, you know, warmer Gulf Stream, diabatic heating of the atmosphere, low pressure at the surface downstream. Well, that's not like that, unfortunately. There is fundamentally the response of the atmosphere is very sensitive to the background, the sort of background flow which is there, and the Gulf Stream contributes to that. So it's very difficult to get confidence in the prediction you have. You can always understand why the model is doing something, but that's what is really perplexing, is that it's not always the same thing for different models. So in the framework of the linear storm track modeling, this sensitivity is really reflecting the impact of the Gulf Stream on the background flow, this dynamic operator L, in this sort of equation I put there at the bottom. And my sense is that there might be a more robust forcing associated with the organization of the atmospheric mesoscale activity by the Gulf Stream. You start to see that in AGCM on scales of a few tens of kilometers. So that is this process F, is forcing F, but this is a stochastic process. And so as we are going to increase the resolution, we might see more robust timing responses, maybe improvement in the biases because of the timing nature of this F term. But this F term is stochastic, and that means that we are going also to look at ensemble. So it's not only the high resolution, but it's also the ensemble that we're going to need to be able to characterize the impact of the Gulf Stream on this structure. So that takes me to, I think, two outstanding questions. I only decided to put two, which are for me the really important one. The first is, we're still not clear what are the emerging mechanisms of Gulf Stream forcing of the jet stream in high resolution model. What are the new ones compared to all the stuff that has been going on for decades using low resolution model? Are there new mechanisms of forcing that emerge in this high resolution model? I suggested some with this idea of organization of mesoscale activity, but I might be wrong. Maybe there's some other things which are more important in the models. I think at this stage we don't know. And to come back to my point about the stochastic nature of the forcing by the Gulf Stream, I've never been very popular when every time I speak to people about that, people say, no. But I genuinely believe that we need to parameterize this effect of the ocean on smaller scales in the atmosphere so that we can run a couple simulation with ocean at 10 kilometer resolution on the order, and atmospheric at coarse resolution, maybe 100 kilometers, because we're going to need to do some ensemble, and we're going to need also to sample the natural variability of the Gulf Stream, because the stuff I've been showing about SST tripole Gulf Stream shift, I mean, this is only really a small percentage of the variance of the ocean and the SST field in the Northwest Atlantic. So we really need to do better, and I think this would be one way to help with that. So on this, thank you very much for your attention, and I'll be really happy to take some questions. Thank you.
Thank you very much. That was great. Any questions from the audience or other participants? Yes, Jamie.
Thanks. That was really interesting. I was struck by this idea that the atmospheric mesoscale is somehow set by the oceanic mesoscale. And I'm curious, has anyone done like the simple test of looking at the scales over continents versus over oceans to kind of give that a test?
Yeah, no, I don't know about that. No, and also there is a wide range of scale in the ocean as well. Kuroshio and Gulf Stream do not have the same sort of cross stream scales and deformation radius, but I do not know. No, this sort of kind of really would be really nice and simple and really interesting to do, but I don't know anyone who has done it yet. Yeah.
Thanks.
Oh, yeah, Jimmy.
Hi, Arnaud. It's Jimmy Booth. You talked briefly about this. Could you speak a little more about where you think moisture comes in that storm track model that you're using as proxy for discussion?
Yeah, thanks. I think that's an open question. I think there was a storm track workshop a couple of weeks ago in France. I was lucky I could participate to that one. I think that this sort of Sardesh-Whittaker idea is based on dry dynamics. And so the moisture is not present in there. But I don't think it would change necessarily. It would certainly change the dynamic operator and maybe help the growth in some location. But if you think about simulating the time inflow has to be stable. It is there, we observe it. So I don't think it would change fundamentally the sort of conclusion, in terms of having two really different, there's the transient growth set by the background flow and the Gulf Stream contributes to that. There's the damping and there is the stochastic forcing. I think this framework still remains. Now the details of the L operator or the damping or the F might be different. And I think the moisture is very important for the F. So this argument about, setting the Gulf Stream favoring the location of updrafts and the strength of the updraft, that's really completely dependent on moisture. Without moisture, you would never get this.
Okay, thanks.
Yeah.
And we have one online from Young Kwan. And let me pull that back up. What would be a high enough model resolution to capture the Gulf Stream impact on the jet stream?
Well, I mean, I guess nobody really knows, but because we don't really know, my outstanding question number one, we haven't really addressed yet what are the new mechanisms which emerge. But certainly from some of the experiments that we did at Imperial College with Benoît Vanière, where we did these simulations, the Met Office at 12 kilometer, 40 kilometer, we definitely saw that at 40 kilometer, we were getting very weak signal compared to 12 kilometer. In terms of updraft, for example, if you're interested in this idea that the upper levels are being squeezed in terms of vorticity, at 40 kilometer, it would be divided by a factor of 2 or 3 already. So it seems, and from other studies, that the 25 kilometer seems to be a bit of some sort of threshold, but I think that's just, word of mouth and what people say at the moment, but we don't know for sure. But yeah, it seems like 25 kilometers, you start to see something that becomes more clear.
Yeah. We have another set of questions online. First from Elizabeth Thompson. You mentioned that there is some preferred scale of interaction and behavior in the fronts. Can models reproduce that? And then Francis Pouloun had a follow-up. Is the preferred scale of interaction the mesoscale, since that's where the Gulf Stream has the most energy? Or is there something else that determines the preferred scales?
Yeah, I think the way I see this is that there is a downstream scale which is on the order of the atmospheric deformation radius, even though this is an ocean current. And there is indeed a cross-stream scale, which is more on the oceanic deformation radius scale. And that is the scale that can efficiently interact with the atmospheric front and the mesoscale structure in the atmosphere. Now, that's quite different from the mesoscale oceanic eddy field, which also has the scale of the oceanic deformation radius. But I think the oceanic mesoscale eddy field, the warm anticyclone, cold cyclone that we see, meandering along the Gulf Stream, crossing sometimes, and these things. It's a bit like an inverted Frankenmuth-Hasselmann thing, where essentially what happens, I think, is that the atmosphere is spatially integrating this structure. And so the sort of ideas, the MA 2015, 2017 papers, the forcing is actually on the scale of the atmospheric deformation radius. So cumulative effect is the fact that spatially there's an asymmetry between the ascent and the specific humidity in the boundary layer of a warm eddy compared to a cold eddy. And it's only when you do the spatial averaging that you see this effect. And so I think, again, it is a forcing on the scale of the atmospheric deformation radius. And as a result, it is a quantum cafe type thing. We're going to find different response from different models, even with the same ocean eddy field forcing. Whereas I think the direct forcing of the mesoscale on the oceanic deformation radius, like this idea of favoring the instability in the atmosphere in certain location, this might be more robust, I think, because that this idea of squeezing the upper level, if you have a negative source of vorticity, you're going to generate an anticyclone. But yeah, I mean, these are my ideas. I might be completely off, but it's really an active area of research, very interesting.
Arnaud, thank you very much. That was very engaging. It is now time for our first break. So,
I just wanted one more thought or question for Arnaud, because I really I appreciate your outstanding questions there. And I think, not saying that this is exactly how we would frame this or structure this, but I think it's worth thinking about, what if we decided that what we really wanted to do was to develop the parameterization that you're talking about, right? What kind of observational campaign and modeling efforts would be needed to actually really make progress on that? So what kinds of measurements, what time and space scales, how long would they be, where would they be, you know, and you know, how much, how spatially, how large would they have to be, what kind of resolution are we talking about? And I'm not expecting you to answer that right now, but hopefully that you've thought about this a little bit and are going to bring this up in our workout groups and so forth.
Yeah, I think that's a great, thanks for that, because that's a great question to think about the actual, how we do implement this thing. And I think we are very lucky. That's the one thing we've got for us, is that we are not here looking at decadal sort of, or multi-decadal. We are really looking at the interaction on the time scale of a few weeks. I think for me, or you know, that's the thing that is really the interesting thing to look at, that is really unexplored, is the coupling between the atmospheric system and the Gulf Stream on these sort of short timescales. And that we can do campaigns on that sort of timescale. We can do it. It's not like you know, sustained observational effort for decades. This is campaigns of measurement. We just need to be learning. There's always some storm coming in the winter over the Gulf Stream. So if we can do it, you know, if people are brave enough, or if there's a way to do this safely, this would be really interesting.
Thank you very much. So, yeah, please give your round of applause for Arnaud. That was wonderful. And we will reconvene for more talks at 10 a.m. Thank you. Okay, thank you. We are going to reconvene. Our first speaker of this segment is Jaime Palter from the University of Rhode Island. Her title is, I'm going to wait for a clearing in the clouds, Opportunities and Challenges in Observing the Gulf Stream for Needed Insights into Weather and Climate.
Okay. Yeah, thanks for having me and for the invitation and for doing something at hybrid workshops so we can all be together and engage people that can't be as well. It's a real pleasure to talk about the Gulf Stream. Like Jim, I really love the Gulf Stream. I'll just say that one of my first cruises was one of those climb mode cruises. And the data that was collected was so good that one of my students has just used some of it in a publication along with some new data as well. So a good field campaign kind of lasts, well archived, lasts forever. And so I kind of took maybe too seriously the assignment that the organizers gave me, and that it was very broad. What are the big questions in weather and climate in the Gulf Stream that can be answered with better observations? And so I really was trying to pull it apart and figure out how to get organized. And I think these are really two separable questions in some ways. How can we understand better weather and also climate? So one thing is, can better Gulf Stream observations lead to better forecasts, weather forecasts? Is that what our goal is, to have better forecasts, and on what time scale? And I think the answer here is probably yes. I mean, that's the reason we're here, and I'll give some evidence, much of which was produced by people in this room, so I hope I do it a little bit of justice. And then on the climate side, I think it's a little trickier. Will better Gulf Stream observations really lead to better climate prediction? And I wanted to take a step back and really examine that question. And I think when we get there, I think we have some questions, like, can we get to better climate prediction, like in the mean that we expect to happen, in the variability on these longer interannual to decadal timescales, what we think of as climate timescales, and even on the signal of anthropogenic warming through physics? And I'll share some reasons why the Gulf Stream is so important to physics, and then we can, I think as a group, we're going to spend the next few days reflecting on what that means. Something that I don't know a lot of people in this room are thinking about, but I've spent a lot of time in the last few years thinking about, is understanding and quantifying carbon dioxide exchange. CO2, of course, the main driver of anthropogenic global warming. And the Gulf Stream, a particular hotspot of CO2 uptake. So thinking about folding in these kinds of gas exchange measurements into any observing system. Because ultimately, if we can think through all these questions, then we will have an observing system that's really versatile and broad and good at answering lots of questions. So with that, I'm going to jump into the weather, and I'm just going to keep that organizational structure throughout. really thinking about what the potential of improved observations of the Gulf Stream is to increase skill in weather forecasts, and particularly at the subseasonal to seasonal timescales, those 2-week to 2-month timescales, which, if my understanding, are very, very challenging because the skill that you get from the initial conditions is largely lost by 2 weeks, but you haven't created any predictability from the boundary conditions in those slower oceanic processes. And so I took a step back. I hope this isn't too basic. I was reading up to get ready for this and found this wonderful paper by Minobi that people have cited here, where he really proposes, and I know this idea has been disrupted since, but proposes that the Gulf Stream provides an anchor for upward atmospheric motion and rainfall in winter, so for basically the storm track, by looking at the visual correspondence between the Laplacian of the SST, and it looks just like the Laplacian of the sea level pressure. We can't deny that there's a strong correlation, which then, of course, creates wind divergence and convergence, or correlates with it at least, with upward winds reaching all the way into the upper troposphere, energizing the storm track and leading to strong rainfall over the Gulf Stream, with the hypothesis that this could influence the entire northern hemisphere weather and climate. And that was really a wintertime mean state view that later we learned obscures the true dynamics at play, that those averages, which are truly correlated, really obscure the dynamics, that the atmosphere-Gulf Stream relationships arise from the aggregated impact of extratropical cyclones crossing the sharp SST gradients for all these hypothesized reasons that Arnaud and others have, and Jim touched on. And so one piece of evidence in this from Reese Parfit and Hyodae Seo in 2018 showed that when you look at the wintertime mean wind divergence, it's a factor of 50 smaller than any given snapshot. And all those like internal dynamics or dynamics at the storm scale of the atmosphere are creating these very strong convergences and divergences. And there is no time mean Gulf Stream anchor, that when you filter out the strong fronts, that time mean anchor goes away. But that's not to say that the Gulf Stream doesn't play a very important role. I don't think that's what any of those papers are trying to say, but that the key air-sea dynamics are at the storm scale, not at the mean scale of the winter. And that creates a really formidable observing challenge to understand things and to see things at the scale of the storm. But I think that's what really, and it seems like everyone here is converging on this idea, really has to happen, because it's at the storm scale that we think we're going to get better predictability, from my understanding. So here's a really recent paper by Roberts et al. From 2022, looking at the hemispheric impact of North Atlantic SSTs in subseasonal forecasts. So what they do is they run the ECMWF forecast model in an ensemble mode, and they run it with the ECMWF ocean model with all of its biases, and the biases are really strong in the Gulf Stream region here. As you can see, the scale here is up to 2 degrees Celsius. I think it saturates, so it might be even larger. And they run it again in an ensemble mode with the bias removed using a satellite SST product, so that they can see, and then they compare the two and look at the forecast scale at 20 to 30, something like about a month after they change the SST and remove that bias. And so at forecast days 26 to 32, after the North Atlantic SST bias is corrected, they have a statistically significant improvement, these red colors, in this continuous rank probability score, a forecasting skill score. And what I think is really notable is that this clearly maps along the storm track as shown in yellow. It's the yellow is showing the Northern Hemisphere subtropical waveguide. And then the patterns of where the improvement happens looks like a propagating feature, like a wave. So I think what we can learn from this is that having better observations assimilated into a forecast model improves the forecast even at these very, very challenging timescales. But it does so, I think this is suggestive that it does so through the the understanding of the storms and getting those storm dynamics correct. But what I think might also create a bottleneck in getting these skills, these forecasting skills ever improved is that even our satellite images of SST can itself, first of all, it's gappy because of clouds, and also could be biased because of those gaps and correlations between the clouds and the SST field. So anyone who's worked with satellite SST understands that the Gulf Stream is an incredibly cloudy region. This is the cloud fraction, and using infrared satellite from Terra 2000 to 2011 in wintertime, and there's a contour here that's almost 100%. So it's really cloudy. We do not get a clear sky view of the ocean almost at any time. So in the winter, when these extratropical cyclones are really ubiquitous. So what observations could we have to improve the SST observations and gradients? And I have been working with uncrewed surface vehicles, particularly sail drone, since about 2019. And we think that these can fill some of the gaps created by days or even weeks without a clear cloud-free view of the Gulf Stream. And so I'm going to talk a little bit about our use of sail drone. So I'm currently part of a project that's funded by Google.org with ECMWF scientists. The lead PI is Phil Brown. And they're assimilating these Gulf Stream observations from the sail drone in real time into their ECMWF models. It's ongoing, so I don't have stunning results to share, but can talk a little bit about the opportunities and challenges there. So this is where we've been, although I'll show you an update from this. In 2019, we kind of tried to create the climb mode path that Jim showed with an autonomous vehicle. We did okay. It wasn't that the meteorologists weren't in charge in this case. It was just that it's harder with using wind power to get these paths. And then in ongoing, we've had 3 or 2 or 1 or 3, again, sail drones in the Gulf Stream since December 9th. And those are shown in magenta through March 31st, but that project is ongoing. And so we've been trying to now, instead of having 1 sail drone, what we did in 2019, have 1 sail drone move down the Gulf Stream. In winter, we had 3, and we were trying to make crossings at 3 different locations along the Gulf Stream path. So where was I going? Okay. So just to illustrate how much variability there is in our beloved Gulf Stream region, I took a sea surface temperature image from the Rutgers Coastal Ocean Observing Lab for April 20th, and I'll show you why I picked that date. Well, first of all, it's one of the very few good views we had in almost all of April of the Gulf Stream. And even still, you can see the challenges with massing clouds. Like, we know there's no water on the subtropical side of the Gulf Stream, but it's very, very difficult to mass clouds. And I love these images because they don't overdo it, right? They leave some of the pixels so you can see the Gulf Stream. And this, on the right-hand side, is the GHRSST, a gridded, interpolated product that always looks cloud-free, but it's not, and it really smears out the variability. This is on a day with this incredible image, so a pretty clear day. There are weeks, and even multiple weeks, where we do not see the Gulf Stream. In fact, this little trace here is a glider that we put in this eddy here, and then we went on a boat to try to find the glider, or try to find the eddy and the glider, but for 2 weeks before we went on the endeavor to find it, we had no view, and we just could not find that eddy. I think it actually broke up after that. So the reason I picked April 20th is because this is a day that we had our 2 sail drones sailing side by side to do kind of a sensor intercomparison. One came from basically the tail of the Grand Banks, one was here near the seamounts. They came together within 8 nautical miles of each other and sailed in formation along this red trace. This is from the Sail Drone Mission Portal. And so even when they are 8 nautical miles apart on a day with clear sky image of the SSTs, you'd say that these are going to be sampling in pretty much the same SST. Well, this is pretty far north of the Gulf Stream. The one on the left, the one on the west, is in 13-degree waters. The one on the right is in 8.7-degree waters, a gradient of over 4 degrees Celsius in 8 nautical miles far from the Gulf Stream. And so those are the kinds of scales that are not getting into our models. I could show you as they progress through, I'll spare you all the details for time, but this one went into water of about 24.5 degrees Celsius. They were trying to sail together. The other one got swept downstream in the Gulf Stream. And the places where those temperatures are met are offset by sometimes tens of kilometers. We have examples of that, tens of kilometers from where they are in reality when we're out there measuring it. So like I said, Phil Brown and others at ECMWF are going to assimilate these data and will study the impacts on their forecasts. The goal is to improve their weather forecasts at all time scales, but particularly those extended range forecasts. So looking at how this influences the storm track and then propagates out to Europe. And of course, we have plenty of motivation for this, but it's ever increasing. As Europe moves more and more to wind and solar, it's good for them to have weeks or longer to anticipate what the supply side of their energy system will be. Okay, so that was a quick tour of my crash course in weather forecasting. And now I want to talk a little bit about climate, which I think is an interesting question to understand if the Gulf Stream, better Gulf Stream observations can lead to better climate prediction. So I don't know the answer to that, and I hope we'll have lots of good conversations about it. But I do know why we might expect that anything that we understand with the Gulf Stream will help us understand climate. So this is from a review paper I wrote in 2015 on the role of the Gulf Stream in European climate. And this is kind of a mean state schematic of the overturning circulation, which of course the shallow limb of the overturning circulation is carried in the Gulf Stream. And so in this overturning circulation, we have this is embedded in the Gulf Stream, and it transports a huge amount of heat to the northern high latitudes. And it's embedded in this whole climate system, right, where there's all these different terms like shortwave radiation, outgoing long rate of radiation, atmospheric heat transport, and then, of course, the huge ocean to atmosphere heat fluxes. So if we think of the Gulf Stream embedded in the system, that's kind of the Oceanography 101 view of the overturning circulation. What we don't always tell our students is that if we were to slow down the AMOC and the Gulf Stream as a result, because it's carrying that piece of the AMOC, so this is now an anomaly plot under a slowed AMOC, Atlantic Meridional Overturning Circulation. If we were to slow that to the anomaly, of course the circulation doesn't reverse, this is meant to show the anomaly of the circulation. What we don't always tell our students is that the atmosphere actually picks up a lot of the slack. That's a very well-documented model result, but also with some observational support, bringing a lot of that lost heat transport, the heat transport that's not being brought to northern high latitudes in the ocean, is carried by the atmosphere. And it accomplishes that heat transport in a lot of ways through latent heat transport, through really water vapor transport, which has to, when it gets to northern high latitudes, condense and form clouds. That's when the heat is given off. But in so doing, we create a change in the shortwave radiation conditions, reflecting more radiation to space, cooling the northern hemisphere, and then also permitting sea ice to grow further, or at least be retained further into the Atlantic, which also has shortwave radiation effects. So work actually by Rong, Zhang, speaking next, and some that I've contributed to, has shown that because the Gulf Stream and its AMOC component are embedded in this whole climate system, that when you change one component of it, you change many components, and that can have real radiative impacts and impact on the entire heat budget of the northern hemisphere. And so we have one paper that was entitled that the large-scale circulation interaction with clouds slows the pace of transient climate change, because it really matters which component of the climate system moves that heat to northern high latitudes. Do we need to understand, is there an observational campaign that can help us predict the future better with this? I don't totally know, and I think that's a question that is definitely worthwhile for discussion at this meeting. If we think about a Gulf Stream observing system in the context of like a STOML diagram, this is from Meg's great 2019 paper, and our space scales of interest are along the x-axis and time scales along the y-axis. We have, from 100 kilometers to 1,000 kilometers, we can do all of those scales, even with USVs, but with a lot of the tools that Jim was talking about. we can also look at processes from 1 hour to many months to years, also with USVs and these other tools. That really doesn't get us into the climate scales. So the question, I think one question for this meeting is, what do we learn on the lower left of this graph that helps us understand the upper right? And so where I've put my focus in the last few years is on carbon dioxide, because as a driver of climate change. So, but I'm really looking forward to the conversations we'll have to see where these questions all meet. So I'm going to do a quick overview of my work on carbon dioxide, really quick, and we can talk more about it in all the breakouts. But the reason, of course, this is important is that the ocean absorbs about 1/4 of anthropogenic CO2 emissions, about 10 out of every 40 billion tons of CO2 we emit to the atmosphere. But the uncertainty is very high in that ocean carbon sink, and data, products, and models are drifting ever further apart. So this is the global carbon budget in 2021. The distance between the average of the global models and the data products is now about the size of the US emissions annually. And so that really shows that we are lacking some key understanding, or something in the models or in the data products are not working. Both have high uncertainties. And on top of that, the Gulf Stream is a particularly nice place to go as a natural laboratory, but also because it's a hot spot for ocean carbon uptake, like all western boundary currents are. To really figure out where we're going wrong in our global carbon sink estimates, we need, as Judith Hawk said in 2020, a game-changing increase in high-quality PCO2 observations. And so here's where we kind of converge in everything. Can an observing system in the Gulf Stream be optimized to help with both? And so I would argue that yes, and actually CLIMO did a great job. They did collect nutrient and carbon observations alongside, and those were folded into this paper by my student Sarah Nickfer that was published this year, where we used that 2019 data to look at the Gulf Stream's influence on, and subtropical middle water's influence on air-sea carbon dioxide exchange, kind of that Climate-esque sail drone path through the ocean, taking CO2 measurements every hour. So there's the NOAA PMEL has designed an ASV CO2 system that takes atmosphere and ocean CO2 measurements up to every hour, which is a really wonderful system and unprecedented. I'd like to say that in our 2 missions, I think we almost did this just in 2019, but definitely in our 2 missions with the Gulf Stream, in the last 2 years, we've collected more wintertime carbon observations in the Gulf Stream than had been ever collected in the history of oceanography over all those years before. So this is really, when we talk about a game-changing increase in observations, it's here. And so this is just the spaghetti of our ongoing missions with all of these different sail drones. But I think it really gives me a backdrop to explain some of the opportunities and challenges of working with these USVs. And I think the opportunities have become obvious during the talk, that they can sample gradients at the time and space scales of interest for many of these problems. They are long duration. A single vehicle can sample for up to 6 months, assuming it survives, which is another thing, and I'll get to in challenges. It has a large sensor payload. It's very highly adaptable. It can carry a lot of different sensors, and you know, they say future-proof because it can change. You can change what's on it as we get more things. The NOAA PMEL ASV CO2 system is really a game changer for PCO2 observations. And it's a zero emissions vehicle once it's in operation. It is wind and solar powered. Okay, so you say, that's perfect, why don't we just use it all the time? Well, it is challenging. The Gulf Stream sea state, as we know, is formidable. So it may not have infinite fetch, but it does have winds that often go up current, and that creates breaking waves. And when you have a 5-meter rigid wing topped by a 12-meter breaking wave, that is not survivable for the sail drones. They do have a shorter winged vehicle that could be used in winter, but that has other problems because, I hope this is my next point. Oh, yeah, this is my last slide. My third point is that you could use a shorter wing, but it's also cloudy there all the time, and the sensors require charging. And they charge either from solar panels on the wing and hull, which are very rarely seeing the sun in winter, or from a hydroturbine under the water that charges batteries as it moves through the water. So if you go to the shorter wing, you sacrifice charge, but if you go to the longer wing, you sacrifice durability. So that's a real challenge, and one I think we're starting to deal with, and that's good. One way to do it is, as Jim said, you're in Nova Scotia weather here, but you're in Bermuda weather here. And you could take an active approach to this with active piloting and go and bask. So bask your solar panels in the sun. And that's what we were doing here, because we couldn't run the sensors without taking a trip to Bermuda, basically. Well, to Bermuda weather. Anyway, so battery charge is a problem, or can be a problem. We have something to think about. Sensors can fail or fatigue, but this is like anything, right? All oceanography we know can fail or fatigue. But we had 2 out of 6 Seabird SDEs 37s fail within a month of deployment. I don't know if that's the Seabird sensor or the integration, a real challenge. The ASD CO2, which is a wonderful system, 1 pump failed in a month. Another 2 lasted many months, but eventually the pump fatigued and stopped operating properly. And then on top of that, like I said, we did have 3 wings damaged between the 2019 and 2022 missions. So out of the 6 sail drones that we operated, 1 lasted the entire winter from December 9th, is still out there now. And almost everything is still working on it. The anemometer is clogged now. But it has done a great job. Some others were damaged. That's why you can see one here in Bermuda taking a rest, another one in the Outer Banks, waiting for repairs. So I think one thing that would really help is optimization studies to understand how to best use these platforms, because it's a big investment in the pilots and the PIs. It's not Argo, right? It's not set it and forget it. You want to really use these in the best possible way. And so figuring that out would be useful. And then I think I finished right in time to say thank you. This is my great group where we met the sail drone out with the boat that's out like near the Gulf Stream, south of the Pioneer Array. And so with that, thanks so much for listening.
Thank you, Jaime, very much. That was awesome. So do we have some questions from the participants? Yes. From Reese.
Hi, Jaime. Thanks. That was a really, really nice overview. Really enjoyed it. I was wondering whether maybe you could say kind of a brief word on kind of how one tends to go about thinking of how to distribute these observing networks. So kind of what I mean is that, like, I think a lot about myself, about sort of weather systems that move over the region. And obviously, it's important to have a critical mass of observing systems in one very specific area to get the small-scale interaction. And then, of course, on a large scale, it's important to have kind of like a network over the entire Gulf Stream to kind of get that whole interaction. So how, like, when thinking about kind of like deploying these kind of observing systems, like what's the kind of way of thought about going about achieving a critical mass? So kind of like if you had like 100, for example, how would you think about deciding how to distribute those? I guess it's kind of an impossible question to answer.
Well, actually, I think this came together really on a timescale that's unfamiliar, I think, to me and many scientists, which was that it was like funded by the Google philanthropy or whatever, the Google.org. So it was like really fast, and the proposal was very slim, let's say. But I think what a beefier proposal and a process like that, I think that you're trying to do in a way here that would lead up to it would use some kind of observing system experiment in the model. So it would have been wonderful to take the ECMWF model for that side of things and pretend that we fixed reality, have a control run, have a bias corrected run, where we pulled where we assimilated virtual data from virtual sail drones and then optimize for some metric like that continuous probability score. I'm a little out of my depth here. That's really the ECMWF thing, but I would like to do the same thing for carbon. Is like what kinds of observations would minimize our error, and can we look at that in a model before we start putting out these expensive and time-consuming systems?
Yeah, I guess this was more like a general topic for the discussion, is that obviously we have limited resources observationally, and I always wonder kind of like what's the best way to think about is it better to have a critical mass in one specific region, or is it better to like spread out globally or across the entire Gulf Stream to get that kind of spread? And yeah, maybe it's more a topic for the like breakout and stuff.
Yeah,
but,
that's a great question.
Okay.
So I know that there's been a lot of work to pair sail drones with gliders, but I haven't, has that been done in the Gulf Stream in a high current regime, or is that going to be possible at all, do you think?
Well, we are trying it. So Allison Gray is the lead PI on this, but we're using a glider that I got as part of my startup package at Rhode Island, and it's here right now, or somewhere near there. And so it's that pink triangle. And so actually but some NOAA AOML folks have been doing it in the hurricane experiments with the short-winged sail drones. We're trying to do it here. So the only thing I would say about that is that you almost have to regard the glider as semi-stationary because it moves very, very slowly. And then you can try to have the sail drones tag up with it, which is what we're trying now. Actually, we have 3 out there now. We want to have an intercomparison with all 3 and have them move over the glider position. I have to log into that portal, you know, the addiction of the mission portal to see where they all are in that process. So I think that's a very promising thing because sail drones, they do have an ADCP that gives you currents over the top 70-ish meters, but below that, the ocean, you know, it's just a surface trace for every other instrument.
Thank you very much.
Yeah,
that was wonderful. Okay, our next speaker will be joining us remotely, Rong Zhang from NOAA Geophysical Fluid Dynamics Laboratory.
Let me share my slides. Can you see that?
Yep, it looks good. Yes.
Okay. So I would like to thank the organizing committee of this exciting workshop for inviting me to give a community overview talk, which is a good opportunity for me to survey the literature. So in this talk, I'll first give some background introduction about the Gulf Stream characteristics, and then highlight some key community modeling study about its impact on weather and climate, and with the hope to motivate more active discussions at this workshop. As shown in this schematic diagram, the Gulf Stream separates at Cape Hatteras, where it intersects the deep western boundary current, and the cyclonic northern recirculation gyre appears north of the Gulf Stream pass. And the early observational-based study already noticed that the Gulf Stream transport is much larger than that estimate from the wind-driven sphere drop transport. The observed mean Gulf Stream transport increased from about 30 sphere drop at the Florida Strait to about 93 sphere drop south of the Grand Banks. And the observed synoptic Gulf Stream transport can reach 150 sphere drop south of the Grand Banks. And the North Atlantic has the thickest subtropical meltwater in the world ocean, which is related to the fact that the Gulf Stream has the largest western boundary transport, as also shown in this scatter plot, the thickness of the meltwater versus the western boundary transport in different ocean basins. And so this very strong Gulf Stream transport of nearly 90 sphere drop is closely related to the existence of the Atlantic meridian overturning circulation in the Atlantic basin. So as shown in this previous study, from a pure wind-driven gyre circulation without any role of the AMOC, the Gulf Stream will move along the North American East Coast as a western boundary current without a separation, and there is no northern recirculation gyre as observed. However, if the effect of the bottom vertical velocity induced by the interaction of the deep AMOC branch with bottom topography is included, the Gulf Stream separates from the US East Coast near Cape Hatteras, and a cyclonic northern recirculation gyre appears north of the Gulf Stream, and the Gulf Stream transport is much stronger. And as shown in this schematic diagram, the deep western boundary current associated with the AMOC moves downslope near the Cape Hatteras and also south of Grand Banks. And it induced a negative bottom vertical velocity and thus positive bottom vortex stretching, resulting in the cyclonic northern recirculation gyre and the separation of the Gulf Stream path from the US East Coast. And because of this mechanism, the meridional shift of the Gulf Stream paths are anti-correlated with the AMOC strengths at the multi-decadal timescales, as found in both observations and climate model simulations. And here, this schematic diagram shows that a positive AMOC anomaly can lead to this typical dipole anomaly pattern with a southward shift of the Gulf Stream and cooling over the Gulf Stream region, and a warming over the subpolar North Atlantic and a weakened subpolar gyre. And this dipole pattern is also taken as AMOC fingerprint to infer AMOC changes. And similarly, in this earlier modeling study, the southward propagation of the anomaly of the AMOC and associated meridional heat transport from the northern high latitude can lead to the temperature anomaly along the Gulf Stream path, which can be predictable at the decadal timescale because the AMOC anomalies propagate with the slow oceanic advection speed at mid-latitude. And the AMOC also has important impact on the modeling biases of the Gulf Stream path. Showing here the upper panel are the deep ocean current and passive dye tracer in the control simulation with very weak AMOC and associated deep western boundary current, and the perturbed experiment with more realistic AMOC and deep western boundary current simulated in the GFDL CM 2.5. A couple model with a quarter-degree ocean resolution. So more realistic, stronger, deeper AMOC and deep western boundary current can lead to more realistic Gulf Stream and North Atlantic current pathways, stronger Gulf Stream transport, and larger SST contrast across the Gulf Stream paths compared to the control run with very weak deep western boundary current and weak Gulf Stream separation. The Gulf Stream separation can be improved by increasing ocean model resolutions. For example, here, this simulation from a half degree to a 1/8 degree, which simulate a stronger deep western boundary current and stronger Gulf Stream separated from the coast across the section of line W, which compares better with observation than the low resolution model. And the SST biases in this high resolution experiment is much smaller compared to the substantial SST dipole-like SST bias, warm bias in the Gulf Stream region and cold bias east of Newfoundland in the coarse resolution model simulations. And the modeling bias of the Gulf Stream separation are not just due to the lower ocean model resolutions. With the same quarter-degree ocean resolution, the latest GFDL couple model CM4 with improved momentum advection ski and hybrid vertical coordinate has a much stronger deep western boundary current, and thus improved Gulf Stream separation compared to the previous quarter-degree model CM 2.5, which has a very weak deep western boundary current and very strong bias in the Gulf Stream separation. And in this very recent study, when the CM 2.5 ocean temperature and salinity are restored to the observed hydrographic data through robust diagnostic calculation, there's also realistic Gulf Stream separation compared well to that reviewed from the satellite observation. And the Gulf Stream transport in this diagnostic calculation can reach nearly 90 sphere drop, which compare well with observation, while in the control simulation without good Gulf Stream separation, the Gulf Stream transport is only about 30 sphere drop. So next, I'll highlight some key modeling study on the impacts of Gulf Stream on weather and climate. I'll start with the impacts on climate. As Jaime mentioned earlier, this well-known paper found that the observed climatological mean surface wind convergence and sea level pressure Laplacian and SST Laplacian over the Gulf Stream front support a local linkage among them, which are consistent with the marine atmosphere boundary layer model. A follow-up study shows that the AGCM simulated correlations of the surface wind convergence with the SST Laplacian is much weaker than that with the sea level pressure Laplacian, especially when the SST front is smoothed, there's almost no correlation, while there's still some correlation with the sea level pressure Laplacian. And this pioneer study also shows that a narrow ring band along the Gulf Stream is observed and well simulated, but disappears when SST front is smoothed in the AGCM simulations. And the simulated extratropical cyclone number density over the Gulf Stream path is reduced when with the smoothed SST front. And the observed upward motion over the open ocean Gulf Stream pathway after its separation is proposed as an indicator that the local Gulf Stream front affects the entire troposphere. However, in a follow-up study, they found that the upward motion at the upper troposphere, in the case with smoothed SST, there's remains upward motion there, and the impact of the open ocean Gulf Stream pathway in winter is limited to the lower troposphere, as shown here in the difference between the control experiment with realistic SST front and the experiment with smoothed SST front. And the simulated annual mean impact is mainly on the convective precipitation, and there's not much impact on the large-scale precipitation, as also shown the difference between these two experiments. And more recently, this study investigates the atmospheric response to a warm SST biases, a typical biases over the Gulf Stream pathway related to this deficiency in the Gulf Stream separation. And they found that the the simulated response of vertical velocity over the Gulf Stream path is also shallow, mainly in the lower troposphere. And they also found the simulated stationary Rossby wave response, which is more zonal and can be seen over the Eastern Asia and the Pacific, which is different from the less zonal response obtained through the simple linear barotropical wave model forced over the Gulf Stream bias region. The observed North Atlantic winter storm track is centered along the Gulf Stream pathway, which is also simulated in the atmosphere models. And this AGCM studies shows that the SST gradient across the Gulf Stream strengthens the storm track. In the simulation with the smoothed SST front, the storm track is much weaker compared to the control case with realistic SST gradient. And as discussed earlier, in the all-weather mean state, the surface wind convergence and sea level pressure Laplacian Laplacian has very good correlation. However, in this recent study, when they decompose the mean state in terms of the rain-free and the rain-only conditions, the connection disappears. Although the SST Laplacian are almost very similar in all cases, the rain-free case is dominated by the divergence, surface wind divergence over the entire domain, while the rain-only case is dominated by the convergence, surface wind convergence, due to the synoptic storm events. So the long-term mean surface convergence over the Gulf Stream path is a residual of the divergence over the rain-free days plus the convergence over the extreme rare rain-only days. And here is a snapshot of simulated surface wind convergence during a storm, which is associated with sea level pressure Laplacian, but not with SST Laplacian. So the linkage with SST Laplacian does not hold instantaneously, suggesting the importance of synoptic storms in causing the instantaneous surface wind convergence and the sea level pressure Laplacian. An interesting follow-up study shows that the idealized simulation falls by a prescribed zonally symmetric SST front had similar results. There's a divergence for the ring-free days and convergence for the ring-only days due to the synoptic storms. But the zonal average in each case shows the imprint of the marine atmosphere boundary layer associated with the SST front for both the ring-free case and the ring-only case. So a follow-up exchange commented that the community is still searching for a robust diagnostic and contaminated by storm track variability that demonstrates the coupled air-sea response in western boundary currents. Here is a schematic diagram from an AGCM study, which shows that in a single extratropical cycle falls with a realistic or smoothed SST front, suggests that the precipitation response to the SST gradient across the open ocean Gulf Stream pathway is dominated by the convective precipitation in the cold sector of the storm. And the strong differential convection across the SST gradient sets a pressure anomaly over the boundary layer that drives the surface wind convergence, where in the case with the smoothed SST front, the differential convection is much weaker. So next, I'll talk about the impact of Gulf Stream on weather, especially the winter bomb storms. The Gulf Stream is a key development region for winter bomb storms in the North Atlantic, and early studies have found that the storm intensification rates are related to the distance of the Gulf Stream from the coast, especially near the Gulf Stream separation point around Cape Hatteras. And here is an example shows that the simulated storm strength and accumulated precipitation are much weaker in the experiment with no sensible or latent heat flux, which indicate the important role of the surface sensible and latent heat flux released over the Gulf Stream of the US East Coast for the early development and rapid intensification of explosive winter storms. A similar result has been found in the more recent cloud resolving simulations, which shows that the surface sensible and latent heat flux released along the Gulf Stream front plays a crucial role in the rapid intensification of the super bomb cyclone on January 1st, 2018. And the experiment without the surface sensible latent heat flux failed to predict the track and the intensity of the storm. And this earlier study also found that there's a need for the high-resolution SST data over the Gulf Stream region for accurate storm predictions. The high-resolution initial SST data, which reveal a much larger SST gradient and warm-cold filament over the Gulf Stream, improves the model forecast of the track and intensity of the East Coast winter storm in January 2000. And the improved forecast of the stronger storm initialized with the high-resolution SST data is associated with simulated stronger surface sensible heat flux and stronger surface wind convergence along the Gulf Stream front. Again, pointing to the important role of surface heat flux in the rapid intensification of storms. The Gulf Stream SST also has impact at the storm developed stage, as shown in this previous AGCM study. The simulated storm strength at developed stage increases with the SST perturbation over the Gulf Stream region, and surface fluxes enter the storm warm sector has a dominant role through the regulation of the heat and moisture in the air that enters the warm conveyor belt. And the SST front over the Gulf Stream region is important for the simulated enhanced ascending motion associated with the warm conveyor belt in the cyclones, which is an effect not well represented in coarse resolution models, AGCMs. And the experiment with smooth SST front shows much less ascending motion in the storms. And consistently, this recent study shows higher horizontal resolution in HGCMs substantially increase the density of simulated bound cycles near the western boundary current regions, and suggesting the importance of high atmospheric resolution in simulating the extreme extratropical cyclone events. The Gulf Stream is characterized by meandering and eddies. Ocean model simulations with refined grid resolutions exhibit increased and more realistic amount of some mesoscale eddy. As shown here, the snapshot of the relative vorticity divided by the Coriolis parameter in the Gulf Stream region at the end of winter, simulated by ROMs with nested grids. There's a 6 kilometer over the broad domain and 2.5 kilometer in the Gulf Stream region and 750 meters along the US East Coast. So you can see the increase of the submesoscale activity with the increased resolution.
5 minutes.
Sorry, yeah, okay, I'll finish soon. Okay, so this is a very recent fully coupled high resolution simulation with 3 kilometers in the ocean, 6 kilometers in the atmosphere, which shows the simulated submesoscale eddy bordered by a sharp submesoscale SST front, and a huge amount of surface turbulence heat flux are released over the warm submesoscale SST during the cold air outbreaks events. And the same model also shows the relationship between the surface wind stress divergence and the downwind SST gradient and the wind stress curve versus the crosswind SST gradient in the high wind speed regime, consistent with previous studies, and the magnitude is much larger due to the much sharper the submesoscale SST front. So in summary, the Gulf Stream separation and associated transport is closely linked to the AMOC. Climate models need to simulate realistic AMOC associated deep flow near the western boundary to achieve a more realistic Gulf Stream separation, transport, and associated strong SST gradient. The temperature anomalies along the open ocean Gulf Stream pathway are predictable on decadal timescales with initialized AMOC anomaly at northern high latitude. The impact of the open ocean Gulf Stream pathway is limited to the lower troposphere in winter and is mainly on the convective precipitation. The upward motion at the upper troposphere across the Gulf Stream pathway is likely induced by synoptic storms from a remote origin not forced directly by open ocean Gulf Stream pathways. The Gulf Stream may affect the upper troposphere indirectly through its impact on synoptic tropical cyclones. The Gulf Stream is important for the early development and rapid intensification of the US East Coast winter bomb cycles, and also affect the storm at the developed stage through the latent heat moisture release into the warm conveyor belt. The simulated donor structure of the stationary rose-by wave response to the Gulf Stream SST bias is not well understood, inconsistent with the response from linear but tropical wave model. The linkage between the surface wind convergence and SST Laplacian does not hold instantaneously. Creative diagnostics are needed to clearly separate the impact of Gulf Stream marine atmospheric boundary layer and the impact of synoptic storms on the atmosphere circulation. Let's relate to the following question: what caused the long-term mean surface wind convergence along the Gulf Stream front? Could it be forced by the vertical convection related to the turbulence heat flux moisture released along the Gulf Stream pathway? And high resolution needed for both atmosphere model and Gulf Stream front conditions for accurate prediction of the US East Coast winter bomb cycles. And the air-sea interaction associated with mesoscale, some mesoscale activity over the Gulf Stream region need to be resolved and assessed using high resolution coupled models. Okay, I'll stop here. Thank you for the attention.
Thank you very much. That was great. Questions from the participants?
Hi, thank you so much for your talk. This is a question both for you and for Jamie, because Jamie mentioned this also. So there's a lot of discussion about the need for high-resolution SST, and I noticed in some of your examples, it's a difference between a 2.5-degree SST versus a 1.1 kilometer SST, which is a very strong difference. And Jamie, you were talking about ECMWF saying, you know, they're only using like near IR visible SSTs, you know, 1.1 kilometers. Nobody says anything about microwave SSTs at, you know, 20 to 25 kilometers. And since that's not mentioned, I'm going to ask if it's been determined like that scale, that 20, 25 kilometer scale is too coarse for all of the work that you're talking about here. And, you know, is there sort of a scale that if you had something, if you had a 10 kilometer or you had a 5, or, you know, where are we talking about in terms of resolution?
I can comment first, and maybe Jamie can comment later. So you mentioned this 25 kilometer, that intermediate resolution. I think it's, you know, it can resolve mesoscale ID, cannot resolve sub-mesoscale ID. So certainly 25 kilometer is much better than the typical climate model resolution, which only 1 degree, you know, then the impact of some mesoscale ID can be studied in this type of model, but certainly cannot study the impact of sub-mesoscale structure.
I'm holding this microphone, but I don't know the answer to the question. I don't know. Just what we've been using has been the IR stuff. So, but I don't know if people. I don't know. I think that's a really interesting question for the room. Is what scales need to be resolved to get those interactions? I mean, the main reason I ask is because the microwave doesn't have the cloud issue, right? So the fact that it just kind of you don't use that at all and go to the cloudy images says to me someone's thought somewhere that that's not enough, like that's not high enough resolution, or is that just an assumption? Anyway, I don't want to spend long on this because we're just asking a few questions. It's just something I might want to explore later.
Okay, I see a question online for you, Rong, from Francis. You showed an anti-correlation between the observed and modeled Gulf Stream path. Is this typical, and do you have any ideas as to why this occurs?
Sorry, which one? The anti-correlation between the Gulf Stream
between the observed and modeled Gulf Stream paths.
You mean the anti-correlation between the Gulf Stream paths and actually that's the AMOC fingerprint? Is that the one you mentioned?
Yes, getting confirmation in the chat.
Sorry. Let's see. I'm gonna go back. Oh, that's one?
Yeah.
Yeah, so this is observation, but also found in climate models. Yeah, couple models. Sorry.
I guess the second part of the question was, do you know why this occurs?
Oh, okay. So, you know, a stronger AMOC associated with stronger deep Western boundary current. So that gives you a stronger bottom downwelling and a stronger vortex stretching effect, which push the stronger northern recirculation gyre and push the Gulf Stream pathway southward. So that's the mechanism I talked about earlier, this kind of mechanism, you know. So that's why the AMOC strength is anti-correlated with the Gulf Stream position, the shift.
Okay, I think we have time for one more question if anybody has one. Oh, I think, yeah, Elizabeth actually had one in the chat. Elizabeth asks if you could please elaborate more on your mention of the community need for robust diagnostics related to storm track.
Okay, it's really about this exchange I mentioned here. The, right, I'm sorry. Okay, so no, if I can go back. So the this exchange I was talking about, we need the diagnostic to separate the impact of the synoptic event and the impact of marine atmosphere boundary layer on this surface wind convergence. Because so this exchange shows that in the rain-free day or rain-only day, the connection disappears, but there's a small residue in the zonal mean. And actually, you can also see that along the Gulf Stream path, there's small residue here along the Gulf Stream path. So if you remove the mean over the entire region, there's still a small residue. That's what I mean. We need a clear diagnostic to separate the impact of the marine boundary layer and the impact of the synoptic storm on the convergence.
Thank you very much. That's great. Please put your hands together for Rong.
Thank you. I'll stop here.
Okay, so over the next hour of time, we will be splitting into lightning presentations for the first half hour, and then the latter half hour will be a discussion of the content that we see in the lightning presentations.
So,
and this morning.
For those online and those in person, the lightning talks, the way we're going to do this is we're going to front load with the recordings from the virtual participants. So we're going to play those through. And if you're interested, feel free to reach out to anybody. Everybody should have their emails on their slides. And then for the in-person people who are going to, during this session, let me pull up the list. Following the video, we'll have Jacob, then Evan, then Andrea, and then Reese. So we'll pull you up and we'll pull your slides up after.
I think so.
This is a study on air-sea interactions of This is a study on air-sea interactions of the Gulf Stream in an ensemble of high-resmic models. And it is an assessment which was conducted in the context of the Primavera project. And I would like to acknowledge the co-authors of this work, which are listed below. In this analysis, we applied a methodology which is outlined in the paper by Stuart Bishop and co-workers, where they use lag covariance patterns between sea surface temperature and turbulent heat fluxes in order to identify different regimes of ocean and atmosphere interaction. In particular, this methodology allows us to distinguish between regions where the surface ocean variability is more determined by the atmospheric weather or by the oceanic intrinsic mesoscale variability. We want to assess through this analysis whether state-of-the-art models are able to reproduce the observed and theoretical air-sea covariance patterns in the Gulf Stream region and in the near subtropical region. And also we want to establish what is the role of the model resolution. For this reason, we apply this method to 6 different high-resmic models, which were run under different horizontal resolution. We found that by and large the models are able to reproduce the observed patterns of variability at the air-sea interaction, and but there is a clear improvement when moving from eddy parameterized models towards eddy permitting models. In particular, the degree of the realism of the lead lag covariability clearly improves when we have eddy permitting models as compared to laminar oceanic models. And also we found that the role of the atmospheric resolution is relatively lower. We also look at the spatial scale dependency of the lead lag covariability in the Gulf Stream region, and we diagnose transition length moving from a more oceanic driven to a more atmospheric driven by progressively removing the effects of the smaller scale, again following the methodology outlined in the Stuart Bishop work. We found that in general, the models tend to overestimate the observed transition length scale, and also the impact of the resolution is relatively uncertain. If you want to find more details, you can look at the paper and at the poster. Thank you.
Good morning, everyone. Today, I'd like to present some work done in collaboration with Jinsong von Storch and with Johann Jungklaus. It is on the temporal and spatial scale dependency of air-sea interactions over the Gulf Stream, particularly looking at coupling associated with SSTs and winds, as well as the scale separation of air-sea coupling related to the vertical mixing mechanism and the pressure adjustment mechanism. So to start off, let's take a look at coupling between SST and surface wind speeds. On the left side, we have a bunch of lead-lag correlation maps, with the top row where we have SST leading the wind speeds by a day. On the second row is the normal time correlation, and on bottom row, we have wind speeds leading SST by a day. And what we see is that when we analyze the full field, so the leftmost column, is that when you have high winds, this is associated with cool SSTs, as suggested by the negative correlation at zero lag, and when winds lead SST by about a day. In this sense, it seems that this is more of an atmospheric-driven coupling. However, when we decompose them into small and large spatial scales, say using 2 degrees as a dividing scale, what we get that is for the large scale, so the smooth fields on the rightmost column here, we see the same pattern as the full fields, indicating that it is atmospheric-driven variability on large scales. But on smaller scales, a different correlation pattern is revealed, that namely of a positive correlation that indicates warm SSTs are associated with higher winds, thereby suggesting an ocean-driven coupling. So to provide a more nuanced spatial scale separation, we computed the spatial cross spectra of SST and wind speed coupling for each latitude band over the North Atlantic. First, using monthly fields, which is the bottom left figure here, that reveals that the power of the coupling is actually on scales between about 100 to about 900 kilometers. However, if we use daily fields, the power of this coupling greatly diminishes. So to give a keener distinction on the timescale separation, we therefore look into the frequency wave number cross spectra for SST and wind speed coupling over the Gulf Stream, so that's between 40 to about 50 degrees north. And we do see that at scales between about 100 to 900 kilometers, we have in-phase SST wind speed coupling that suggests ocean-driven variability on time scales of about 30 to 60 days. But this coupling diminishes as you go to shorter time scales and almost extinguishing on time scales less than 20 days. As for the large scale, so scales larger than about 5,000 kilometers, we have this 90-degree out of phase that suggests atmospheric-driven variability. So if you'd like to see and discuss about how the timescale and spatial scale separation would look like for the vertical mixing mechanism and the pressure adjustment mechanism, please check out my poster, and I will be available during the poster sessions for discussion, or you can email me at dian.putrasahan@mpi-met.npg.de. Thank you very much, and looking forward to some fruitful discussions.
Hello, my name is Marta Venta, and I would like to present a case study of European blocking from February 2019 and its association to air interactions over the Gulf Stream. This blocking was associated with a very strong heat wave that occurred in February 2019 in Western Europe with temperature anomalies above 20 degrees. In this study, I'm using Lagrangian trajectories run 10-day backward from negative PV anomalies forming the blocking and 10-day forward from the area associated with the Gulf Stream SST front. What we see is that on average, more than 30% of trajectories run from negative PV anomalies, backward ones, pass over the Gulf Stream in the lower troposphere, and more than 60% of those run from the Gulf Stream SST front end up in the negative PV anomaly in the upper troposphere. What is actually happening over the Gulf Stream? Trajectory air parcels pick up moisture there, what we see on picture C. Because we have one cyclone after another passing over the Gulf Stream, and the first cyclone creates conditions which cause cold air outbreak, and thanks to that trajectories, air parcels pick up moisture. As we see here, we have high latent heat fluxes, and then with the second cyclone, they are picked up and they are sent into the negative PV anomaly in the upper troposphere. What is more, that first we have small negative PV anomaly, which will later form the blocking. But the moment we have a contribution of trajectories that passed over the Gulf Stream, what we see below, we have much bigger negative PV anomaly in the upper troposphere, which is formed by those trajectories, which indicates that the interactions over the Gulf Stream play an important role in the formation of the blocking. To summarize, this case study indicates that there is a mechanistic link between Earth's interactions over the Gulf Stream and the formation of the blocking in the Western Europe. And in our further research, we are going to run similar setup of trajectories, both from negative PV anomalies and from the Gulf Stream for the whole ERA 5 period. And we are also going to study the clustering of the cyclones from the APE budget framework perspective. Thank you for your attention.
This presentation summarizes results from a recent study to understand the impact of North Atlantic sea surface temperature errors in ECMWF coupled forecasts. The plot on the left of this slide shows that our subseasonal forecast system, which uses an eddy permitting ocean model, suffers from errors in the position of the Gulf Stream. When we artificially correct these errors in sea surface temperature using an online bias correction algorithm, which is shown in the center, we improve the atmospheric mean state and also the simulation of atmospheric circulation anomalies. This improves forecast skill in the North Atlantic and surrounding regions, but also downstream along the Northern Hemisphere tropospheric waveguide. The results from this study highlight the potential benefits to initialized coupled predictions from higher resolution ocean models that can better resolve the position of the Gulf Stream. This slide shows an example of the impact that Gulf Stream errors can have on atmospheric forecast skill at subseasonal lead times. The bias-corrected forecasts, shown in blue, have higher NAO correlation skill than the original forecasts shown in red, at lead times of up to 3 to 4 weeks. We also see similar positive impacts for other deterministic and probabilistic measures of forecast skill. However, it's important to note that the atmospheric response to the reduced SST biases is not limited to the North Atlantic or its immediate surroundings. The response in the upper atmosphere is characterized by zonally propagating stationary wave activity that follows the Northern Hemisphere tropospheric waveguide. We interpret these remote impacts as a response to the southward shift of the Gulf Stream when we reduce the SST biases. And this changes then the location and magnitude and timing of convection and vertical motion associated with extratropical storms propagating through the North Atlantic storm track. And this is then modifying the forcing of planetary waves in this region in the upper troposphere. So finally, the results from this study provide important evidence for the potential benefits to coupled forecast systems from ocean models that can better resolve the position and the dynamics of the Gulf Stream front. Further details are available in my virtual poster presentation and also in the GRL paper that was published last year. And lastly, for anyone that's interested in these data for their own research, you can access this through the ECMWF website under an open access license.
the first thing we do is calculate ocean atmosphere feedbacks. So in the top panel, I'm showing the sea surface temperature to turbulent surface heat flux feedback with units watts per meter squared per degree Celsius. And on the bottom, the feedback between sea level anomaly and surface heat flux. We use the ratio of those feedbacks scaled by a regression coefficient of sea level anomaly to mixed layer heat content to calculate what we call the effective depth of air-sea interaction, which I'm showing here. And this describes the volume of water per square meter of the ocean surface that is participating in air-sea heat exchange. And it includes contributions from heat stored in a column of the mixed layer, as well as heat being brought in by ocean processes such as advection and mixing. And to isolate those ocean processes, we take this effective depth and divide it by the maximum climatological mixed layer depth to get this, this depth ratio. And a large effective depth and a large depth ratio indicate that ocean processes are dominating air-sea interaction in that region, and it is primarily happening in the North Atlantic along the Gulf Stream and its extension. We also look at these quantities and their seasonal variations. So here I'm showing just the winter effective depth and depth ratio, and we can see that their spatial patterns pretty closely match the year-round case. In the summer, however, the effective depth is smaller everywhere, mostly due to the smaller and shallower mixed layers, and the depth ratio is no longer large primarily in the Gulf Stream, and some of those larger values have shifted towards the interior of the basin. So from this, we conclude that ocean processes play an important role in renewing upper ocean heat content variations and driving air-sea interaction in the Gulf Stream, and this role of these ocean dynamics relative to atmospheric variability is enhanced during the winter. Thank you.
Okay, next up, Evan Jones.
Go on. Yeah. Alrighty. Thank you. Morning. My name is Evan Jones, and I'm presenting some work as a PhD student at Florida State that I've done with my advisors, Reese Parfit and Allison Wing. And what I'm looking at is sort of evidence for a possible influence of the Gulf Stream on the extratropical transition of tropical cyclones. And of course, in the North Atlantic, a lot of TCs undergo this extratropical transition process near the Gulf Stream. And, you know, we've had some talks that have touched on the fact that the Gulf Stream does influence the climatology of atmospheric fronts at the surface and also winter cyclones. There's, you know, plenty of studies that look at that. But the sort of mechanisms for how that interaction is exactly happening is, you know, pretty heavily debated still. You know, is it a direct impact for some of those things, or is it this idea of like a preconditioning influence where the lower atmosphere is being conditioned at times when there's no fronts present or only weak fronts there? And then are sensible or latent heat fluxes more important, and is it absolute SST or SST gradients that are having more of an impact? But since extratropical transition itself involves the development of fronts, the main question I'm trying to answer is, does the Gulf Stream play a role in this ET process in the region? And if so, how might that occur? So just real quick, there's at least, you know, anecdotal evidence for surface-based frontal development during ET near the Gulf Stream. So these are a few plots of kinematic frontogenesis associated with Hurricane Teddy, which transitioned near the Gulf Stream during the 2020 Atlantic hurricane season. And you'll see as Teddy moved northward, it approached a quasi-stationary front, and beneath the boundary layer shown in magenta, there's a enhanced surface-based frontogenesis that's occurring. So at least on a storm-by-storm basis, there's, you know, evidence for that happening. But if we expand to a few more cases and look at a few more storms at transition, what I'm showing in the bottom here are composites of climatological daily mean SST gradient anomalies based on whether storms successfully transition on the left or do not successfully undergo ET on the right. And that's only within this box region for the topographically bound Gulf Stream. And so what we see is that there is a difference between whether or not a storm successfully or not successfully transitions in the days leading up to the times when the storms are in that area. So I'm only showing -7 days, but in the days and weeks leading up to it, there's some persistence there. So diminished SST gradient anomalies for unsuccessful ET appear to be correlated, and then vice versa. And so this persistent signal indicates that there's maybe this idea of preconditioning of the area for favorable ET or vice versa as well happening. But how might that exactly impact ET? Well, we define just a simple index based on the strength of the topographically bound Gulf Stream at 4 different points shown in kind of the green X's on the plots on the right. And so if we take the extremes of that index, the time series on the left, and look at the 95th minus 5th percentile and look at a couple different quantities, we first see the sensible heat flux gradient for those different times, the 95th minus 5th percentiles. There's an enhanced sensible heat flux gradient in the region, which is can be a proxy for the baroclinicity in the area. And then if we go from that over to the right for the 900 hectopascal diabatic frontogenesis, it's a bit more noisy and maybe not as clear of a signal, but there's still enhanced near surface diabatic frontogenesis occurring. And so there's evidence for when the Gulf Stream SST gradient is stronger for enhanced surface baroclinicity and that sensible heat flux gradient scaling with the diabatic frontogenesis. And then we also show that the large-scale atmospheric setup associated with the extrema of the Gulf Stream strength is not the same as the setup for these different phases of extratropical transition, whether it does successfully or not successfully transition. So I'd really like to argue that the Gulf Stream is important for ET and likely from this idea of the regional preconditioning. So I invite you to come to my poster and happy to talk more about it. Thank you.
Oh, you snuck up on me. Here, Andrea Malode.
Hi. So this slide here is by way of a teaser for the poster that I have set up in the corner there. And so these are results from a rather unique atmospheric ocean coupled simulation. Rong Zhang very nicely pointed out some results from the paper that just came out about it at the end of her talk. So I thank her for that. But the results here, here's a schematic of what we're seeing. The poster shows the model results that we found. But this simulation now ran out for a year and a half. So it's 6-kilometer atmosphere, 4-kilometer ocean global simulation that ran out for a year and a half. But basically, we've isolated the conditions under which secondary circulation gets set up related to the mesoscale and submesoscale SST and strong wind conditions. So the top part of the schematics sort of shows a little bit the cold. Here, let me stand here. Think of the cold water to the right, the warm water to the left, where wind is blowing from this direction. We cross an SST front. On the top situation, we've got like a cold air outbreak, but we're not running into strong SST gradients. And so you see what you would expect. SST, the cold air enhances the mixing and things like that. The middle one is the situation where you really don't have that strong of a wind. There's no cold air outbreak, but we run into an SST front, and so the sensible latent heat fluxes go up. On the bottom, you've got a situation where you've got the cold air outbreak, the strong winds, and a strong SST front, and you set up this little secondary circulation. The momentum mixing essentially has time to kind of kick in and enhance the fluxes even more. And under those conditions at the bottom, we're enhancing the sensible latent heat flux gradients substantially. So model results from this, come see my poster.
And next up is Reese Parfit. I got worried that nothing loaded up.
Okay, I'll keep this short. So this is just an advert for the poster. So I'm actually going to talk for 3 minutes about something not really related to the poster, but more, so the poster itself is about what drives variability in the SST gradient. I'm going to talk mostly about why we care. So those of you who know my work know that I'm obsessed with the SST gradient. just basically, why do we care about the SST gradient? Well, so this is the average cross-frontal sensible heat flux gradient. And so what you see is that the average condition over the Gulf Stream is really one of strengthening the temperature gradients in the lower atmosphere. And so the SST gradient plays a really crucial role in restoring the sort of lower atmosphere baroclinicity when a storm comes and destroys it. And actually, excuse me, this effect is actually strong enough that you can actually generate systems in the lower atmosphere that are seen as, you can actually detect with algorithms as atmospheric fronts. And there's a lot of work that's come out in the last couple of years that has shown that actually you have different frontal structures in weather systems in different ocean basins because of this effect. And actually the thing that Rong was talking about earlier about the surface convergence and the deep motion, which was kind of presented as an open question, I'm pretty certain that this is the answer to it as well. But what's important about this is that a lot of people don't appreciate the importance of the SST gradient because this is mostly a preconditioning effect. Generate some fronts and then you wait for a large-scale circulation to come along and develop it into another system, into like a weather system that Evan really nicely talked about. And I really suggest you go and see his poster. And so if you run a model experiment and you just change the SST gradient when the storm passes over, you don't see it because it's a preconditioning effect and you're not looking at that. So a lot of people don't appreciate that. But anyway, this is set by the ocean, this permanent sort of on average heat flux gradient. So anyway, so we were kind of curious. We looked in the literature and we kind of wanted to know what could potentially drive variability in this SST gradient. And we realized that an index doesn't actually exist. So we thought, oh, we'll just take a look and see what happens. So basically we just looked monthly and we created a monthly index of the SST gradient. This just defined it as a 5 centimeter isoline for the Gulf Stream path and had a look at, okay, well, what drives it then? So we came up with this index. And turns out that actually the large-scale SST gradient, at least on a monthly timescale, seems to be mostly driven by the SSTs to the north. And I can talk about that a little bit more, but it's mostly the SSTs to the north that seem to be driving the SST gradient. What's interesting about it is that if you have a look at the monthly SST gradient index, that there's some autocorrelation at 2 years, which we wonder whether that's related to El Nino, because actually if you look at where ENSO has a remote impact on the North Atlantic, it's mostly to the north of the Gulf Stream. But anyway, we also had a little look at how it relates to the atmosphere, and it turns out that even though the average SST sort of gradient imprint is kind of mostly ocean-driven, that variability in the index itself seems to come from what's happening in the atmosphere. And I can talk about this a bit more, but really you have atmospheric variability and it drives changes in the heat fluxes, and that changes the SST gradient. If you look throughout the year, there doesn't actually seem, so this is a lag correlation, it seems to be atmospheric driven, and then there doesn't seem to be much ocean to atmosphere feedback. But actually, if you look in the winter, there's some persistence. So if you look just in December, January, February, the atmosphere is driving a strong SST gradient variability. And actually, you can look a couple of months into the future, but the SST gradient seems to present some sort of mechanism for ocean atmosphere feedback, and we think it's through this preconditioning that I was talking about. But come and talk to me. Thanks.
So we have about a half hour before lunch, and we've had a number of very interesting talks, and including both the overview talks and then the talks regarding the poster sessions. And so we'll have time, obviously, for further discussion, but we thought this might be a nice moment for us just to step back and think about some of the questions and ideas that we've heard this morning. And then to realize after lunch, we'll have 2 more invited talks. And then we will go into the first of our breakout sessions. And really the first of the breakout sessions we're talking about, what are the testable hypotheses and what kinds of observations, and modeling efforts to sort of address those. So I've heard a number of different ideas and thoughts from the speakers this morning. And this is really our chance to sort of maybe delve into those just a little bit during this time period. And I think we've got it so that anybody online can raise a hand, and we can see, and we'll call on you and you can unmute, and then people here in the room as well. So let's see if we can make this kind of hybrid thing work out for us. So, I guess I'm not sure what the direction is that we want to go yet with the discussion, but I heard like Arnaud actually put out this is a kind of a possible thing, looking at the parameterization, right, at these kinds of space and time scales. We've talked about the impact of, or the importance of sort of the storms into this whole scenario, and then we've talked a little bit about the boundary layer and the impact back into the troposphere and so forth. So there's kind of all these threads, and I think that's one of the difficulties about trying to think about designing something like this, is sort of this, are we going to go really finely detailed into something? Is it more spread out? What kind of time scales are we doing? And if we're talking about time scales, so let's say we're talking about storms, and we say what we really need is, high resolution data, because we're looking at sort of the storm scale. But obviously you don't want just one storm, right? That's not really very helpful in terms of what we see with about the stochastic forcing and so forth, right? So we need an ensemble of storms, for instance, right? So that then leads us down to sort of what types of observations might we need to make, and do we have enough answers on the modeling side to do this? So this is all the chat. So Justin's got his hand up. Great. Go ahead, Justin. Go ahead and unmute.
Thank you. Can you hear me?
Yes, we can hear you.
I wanted to make a comment on Rong Zhang's talk, which is very nice. And there was a question raised of what diagnostics to use for separating boundary layer and storm influence. And a few of us have been working on that, with myself, with Reese and Larry O'Neill, Nicholas Schneider and others. And I think there might be a way, if you can somehow, what we do actually is remove the extremes, which are mainly attributable to storms, use some filter to remove the extremes, and then use a separate spatial filter to look at smallish scale features versus large scale. So once you remove the extremes, then it's possible to get a clearer view of small scale stuff, which looks like boundary layer forcing because it matches the SST to some extent. So I think that there may be a way to do that. And the other comment I was going to make regarding how many storms to measure and what we need is, in our analysis, we eventually looked at a reanalysis, ERA 5, because I started by looking at a high resolution climate model, but that may have bias. So I then looked at satellite observations, but that can have sampling issues that we know about. And I ended up looking at ERA 5, which I thought was a very, very good data set. And that maybe my point here is to tie in any observational modeling campaigns with reanalysis, because this got the best, potentially has the best of both worlds, has the observations and the modeling. And has a longer record. So that was my comments.
Okay, thanks, Justin. Does anybody want to follow up on that? Yeah, Jim's got a.
Yeah. So quickly, now I'm forgetting what I was going to ask you. To be honest with you. Yeah. Oh, what we're talking about. Gulf Stream, storms, air-sea interaction, boundary layers. Yeah, I've lost it.
Well, he's thinking, Nathan, do you have a comment? Is that what you're raising your hand for?
Well, so the microphone going to Jim reminded me that there's been all this conversation about spatial resolution, and we're only ever talking about horizontal spatial resolution. But his observations of the atmospheric boundary layer show that there's a profound effect on scales of tens of meters, hundreds of meters. And maybe that's obviously this isn't a bolt from heaven, but the vertical resolution is probably an important variable to think about as well for modeling and observations.
And it's a real quick question because I was sort of asked it over here. How well does reanalysis do with like Lagrangian data? Are they ingesting that to improve the reanalysis, or is that just it's not something that's done right now? Because we're going to have a lot of mobile assets. And to make use of them in reanalysis, you have to figure out how to pull it in.
So Jamie's asking, do you mean like gliders and Argo? And yes. Yeah.
My collaborator Phil Brown at UCMWF just tweeted like yesterday, I can't believe we're pulling in glider and Argo. I mean, he already knew Argo data was in there, but they're pulling in glider data. They're just labeled as Argo. So he was just surprised, but so it is in there. So I think the sky's probably the limit. If it can get to the GTS, they can get into the forecast and reanalysis.
How do you use that type of data?
Yeah. Yeah, so Jim's just saying it sounds like reanalysis is the way to use that variable data. And just is Robert in here? Not yet. I'm just remembering the time that Robert did his Gulfstream glider. So his very first one to go from up the Gulfstream from Florida to off the coast here. And another colleague here was actually at Fleet, and they were talking about their modeling of the Gulfstream, and they're like, all of a sudden these data points popped up and we have no idea where they came from, and they totally changed our modeling of the Gulfstream system. And it was just because he was making it available to GTS, right? So they appear to be quite capable at those types of scales.
Roger's online.
Oh, Roger's online. Roger's online and has a question?
Yes.
Okay. Justin, did you have, before we click off of you, Justin, is there anything else that you wanted to add there?
No, that was my point for the moment.
Okay. All right, Roger, do you want to take it away?
Sure, thanks. I guess looking at this, one of the questions that I had coming into this workshop is sort of generally, what's the community perspective on how deep the effects of the Gulf Stream penetrate into the atmosphere, and how does that work? And it seems to me there have been two perspectives, at least, that have come up in several of the talks and the posters. One, say, in Arnaud's talk, but with the linear operator there that can be viewed as another version of sort of mean baroclinicity and how the instability systems work, which sort of points towards the mean states. And some other things, say, in I think some of Rong Zhang's perspectives, and maybe Chris Roberts' talk as well, I think there were more storm-based individual events with the effect of sort of the lower boundary condition and how the moisture gets up in a specific storm system. And maybe Reese Parfit's and some of these other ideas about preconditioning are sort of in between. And I wonder if there is a consensus there on what's important, or whether we can identify that here, or if not, whether there's a way we can identify how to distinguish those two, or what observations would be needed to decide what's happening.
So I can, I think I tried to make some point in my presentation in the afternoon, but I guess one of the problems is going back to these diagnostic metrics that we have. I think that to identify the SST impact on the boundary layers, we all use this linear regression-based method or analytical model where we don't have any baroclinicity in the atmosphere. There's no baroclinic instability, storm variability in our diagnostic framework. So I guess something that we need to think about to come up with a better diagnostic metric to take into account the stochastic process in the atmosphere, as well as slow, probably lower amplitude SST impact on the boundary layer. I think that's one comment I'd like to make. Another is that storms are important, and storms are not noise here. Storms are in our signals.
So those convergence that we see in the Gulf Stream, which is the point that I like to make in my presentation, is that diabatic forcing from the ocean is what drives the convergence in the large magnitude on the synaptic time scale. So I guess the SSC gradient and sense of heat flux gradient that Reese is talking about is the signal. I think that is what drives the convergence on the climate telescope mean sense. And then there's a boundary contribution that happens all the time, regardless of the weather conditions. And if you sum all those up, then you see this near surface convergence climatology of the Gulf Stream. So I guess, yeah.
I'm just going to slip it back to Larry, who's been waiting patiently, but I'm also thinking it was your quote about the diagnostics needed, right, that was mentioned too, so I don't know what you want to
It sounds like Hyodae is probably going to cover the diagnostic metrics question. So that, and you know, basically why I meant that was because there's a real need, for instance, in the modeling community to evaluate their models of air sea interaction and how the boundary layer and atmosphere responds to it. And so there have been various metrics that are observationally based, and that can also be derived from analytical models or things like that that can help guide us to thinking about what kind of observations we need to test models, and then what kind of processes are important to model in the Gulf Stream region, things like that. But the second comment I want to make is that basically the ocean influence on the atmosphere must pass through the boundary layer. And so, you know, all these ideas about how the storm track is influenced and how deep convection is influenced and things like that has to go through all the boundary layer processes. So turbulent mixing, you know, boundary layer height and things like that are all very important. You know, cumulus parameterizations and how, you know, convection couples with the boundary layer is really important, and how the meridional heat transport and, you know, the SST gradients and preconditioning, it all must come through the boundary layer. So I think it's a really important thing to not consider as a separate idea from the Gulf Stream influence on the, you know, free troposphere. But we have, you know, and so I think boundary layer observations are really important in consideration of whatever long-term monitoring activity we need to do.
Yeah.
Hi, sorry, I was muted. Following up from Roger's question, I was thinking maybe it depends on where we're looking, or maybe the idea of anchoring the storm track entrance region is a distraction. Kathy Kelly was telling me once that maybe we want to think of it as a baton pass, and what happens locally with the Gulf Stream matters more for what happens downstream. And in the Roberts et al. Result, where you're seeing this Rossby wave train almost, you know, all the way around the globe, suggests this idea, okay, so what happens locally gets into a storm, and then it affects things much farther downstream. In the, was it Winta et al., that was about blocking downstream? Same idea, right? So it was moisture from the Gulf Stream affecting the storm, affecting something farther away from the Gulf Stream. So locally, we can see an influence, and maybe that influence doesn't always extend above the PBL, or maybe it gets in above the PBL through the storms, but then where we see a signature of that impact doesn't necessarily have to be right where the Gulf Stream is located.
Sam, is Roger have another hand up, or Arnaud? Oh, good. Yeah, go ahead, please.
Oh, took his hand down.
Oh, he took his hand down.
Oh, sorry, I took my hand down instead of unmuting. I'm sorry. It's very, very interesting discussion. I'm wondering about this idea that things have to punch through the marine boundary layer or go through the marine boundary layer. I mean, that's one of the intriguing things about geostrophic dynamics. You know, if you think about the storms and the jet stream, and is that actually anytime you have a sea surface temperature anomaly which has a 1,000-kilometer scale, it will affect all the way to the tropopause. That's just the nature of quasi-geostrophic dynamics. So, it's just to say that, you know, I think that you can make both cases about the role of the boundary layer, and I don't think it's super clear exactly for me, there seems to be a bit two groups of work. There is a lot of work on the boundary layer and the surface wind convergence and all that. And then there is the effect, the other group of research, which is more about upper level circulation, blocking, jet stream shifts and all that. And these two don't seem to be really connected. So yeah, just to flag this, but yeah.
Thank you. So just to follow on with that, you know, is there some way of thinking about linking those two together? And I guess I'm going to pull a little bit on just when I was on the study team for the NASA PBL satellite. So it's kind of a different group of people than are sitting in this particular room. But that sort of the global planetary boundary layer atmospheric community is very, very focused on the boundary layer height. In the same way that somewhat in the ocean, we do focus on the mixed layer depth, okay, because understanding the variability of the PBL height tells you something about interactions between the PBL and the atmosphere, you know, the free atmosphere above it. Anyway, it's just, and I've seen a little bit here talking about the PBL height, but I just feel like, you know, when we're talking about air-sea interaction, sometimes we tend to talk a lot more about the mixed layer depth because we understand sort of that, the importance of that in the oceanic response, but we don't talk quite as much about the PBL height. I'm just curious if, you know, because to that community, sort of the PBL community, that was like a zeroth order thing that would be great to have across the globe. Would be the people, like if you asked that group and said vote on one variable that you want to get from satellite about the PBL, that's the variable they would vote for, right? So I'm just curious if anybody has any thoughts on that, because, you know, getting measurements of PBL height, you know, is that of any value in sort of linking as an observation that would link some of these pieces together? But I'm just throwing that out there. So, Reese.
I think it's interesting to mention that, or remind ourselves that during, I mean, I always plug the front. The front is what's important because that's where you get deep motion. That's where you get really high up in the troposphere. And a huge amount of the interaction that takes place when you impact the front is within the planetary boundary layer. And I think it's worth pointing out that what a lot of people don't realize is that when a front and a storm passes through, the free troposphere shrinks. And you can actually look right over the extreme heat flux and you can composite the top extreme events. And what you find is that the tropopause is actually down at like 400. And the planetary boundary layer is up at 600. So actually, you can go up like an isentrope when you're already almost at the tropopause. And actually, one of the things that Rong Zhang mentioned was that the convergence effect seems to be somewhat limited in the winter. But I actually think that what's actually happening is that it looks like it's going less high in the troposphere in the winter. But that's because it actually doesn't need to go as high to get to the tropopause because it's a lot lower. So to kind of think about it, I think measuring the planetary boundary layer height is really, really important because, you know, a lot of the time if you get to the top of the planetary boundary layer, you're actually quite close to the tropopause a lot of the time, which is maybe an important point. But
a follow on. I think another reason the PBL height can be really relevant is because in the colder outbreak, all the cloud dynamics setup is related to PBL height. And over the Gulf Stream, if you say how much of the time are you in a colder outbreak, it would be the majority in winter because the cold sector of storms is larger than the warm sector. And so if we think about it from radiative forcing point of view, then that's another reason PBL height would be a really nice thing to know about. Yeah,
and of course PBL height comes from, well, as we could argue about how many different definitions are there of PBL height, but let's not get tied up into that. But I would say that, you know, that's part of that just comes from having high resolution vertical profiles of key parameters in the planetary boundary layer, right? You know, if you want to do temperature and humidity and aerosols and, you know, I mean, we can, like that's, making those measurements then gets us different ways to calculate the PBL height too. So, but anyway, so Jimmy, yeah, go ahead.
Sorry, I'm going to shift gears a little bit in the interest of definition of terms, and maybe we're all on the same page here, but for Gulfstream and what we've seen here, for me, it's mostly been all the discussion of the Gulf Stream extension. And the Gulf Stream itself has a component that's along the coast and flows northward. And I just wonder if everyone in the room is thinking just about the Gulf Stream extension, and that's really where we're going to develop our thoughts, or if we need to step back and make sure we all have the same definition of Gulf Stream in mind.
Yeah, I don't know if this, yeah, it is. That's a super good point, right? I actually was a little taken aback that there was so much emphasis on where it was diverging at Hatteras, for example, how important that region is for some of the, you know, the storm track propagation. So it's a great question. I don't know what the answer is, I guess is my thing. The other thing I just wanted to talk about with regards to boundary layer depth, we're often looking at situations here where let's say it's blowing from the cold continent over, well, it's actually more interesting when we're looking at situations where the air is moving over cold enough water that it's stratified in the atmosphere to now warm water where clearly convection is taking over. And so we have to deal with that nagging stratified boundary layer on many of these studies, and how we so you could have complete different definitions of what the boundary layer height is from here to here over, say, you know, 20 kilometers. And one's the inversion height, and one is just the, you know, depth of turbulent mixing or something. So it's tricky as well being in this region. I just wanted to point that out.
Yeah, and just to follow on with that, it is true. Like there, you know, where if we kind of thought of here's some testable hypotheses, here's some things that we want to focus on, where in the Gulf Stream would we want to do that? And where in the Gulf Stream could be, you know, the decision could be we've got to have stuff going in at, you know, Miami and coming out, you know, half across the Atlantic, or it could be it's got to be right in the extension, or it has to be right off Cape Hatteras. We do have to. Even if in this workshop we don't decide that, we have to say that's a key thing that we need to determine, and what keeps us from making a decision about that. So, Megan.
Kate, not knowing very much about this, could someone tell me, maybe Evan can tell me, when you do a tropical, extratropical transition, does that then say this is going to be a storm that might affect Europe?
Yeah, I mean, if the you know, track eventually takes it down. I mean, for my analysis that I presented in the poster, I was mainly just focusing on the region that was brought up, like kind of near the separation and stuff. But yeah, I mean, I think in theory you could say then, you know, if your path through the transition is affected by some property of the Gulf Stream, then it's you know, post transition evolution might be different then, and then that could have a different impact for where it eventually ends up.
Just to add a quick comment on what Jimmy said, we've looked at that if you look at the SST gradient over the Gulf Stream, there's two distinct maxima. One is off the coast, and then one is further down in the separation. The impacts on SE interaction are massively different for those two SST gradient regions. They're not the same. And so it's a very good point that the separated versus unseparated effect is really quite different. And it's also different for all sorts of other reasons other than the SST gradient too. for example, when we think about the impact of the moisture, if you look at where the moisture gets put in, huge amount of the latent heat flux, or vast amount area averaged is over the separated Gulf Stream. Obviously, that's where the moisture sticks around, and then the next storm comes through and takes it up. The types of mechanisms, as far as the ocean weather interactions go, that also plays a role. Moisture input and like the frontal systems that develop that come off the coast versus a bit higher up, and it's yeah. I just wanted to emphasize what you said, that I think that there needs to be a very good, clear distinction between those two things because they're very, very different. Yeah.
Right. So that may be, you know, that may come back to what science questions do we want to address, right? And they're, you know, and then which area. So Elizabeth is online and has a question. So go ahead and unmute, Elizabeth.
Hi.
Hi.
I was wondering, how do we reconcile Rong's recommendation for high resolution modeling with Arnaud's thoughts about maybe a coarse atmosphere, a high resolution ocean, and parameterization? I was just wondering, are those two different modeling approaches for two different purposes? Like, are they both valuable for maybe different experiments? Or I was wondering, maybe that's a question for them to just elaborate on how we reconcile those or use those approaches.
Yeah, Andrea Molad here. I do have an answer, at least some thoughts. This high-resolution simulation, the long high-resolution simulation that we talked about, we're actually talking about trying to use that to develop a parameterization so that things could be run at coarser resolution. There are some precedents for this out there. So I think we've been thinking about this a bit. So I think the connection between the need for the high-res is partly to develop the parameterizations that the climate models or the coarser resolution things can use.
And we're just about out of time. Although I don't remember it was during the poster time, and there was the discussion of the increasing the resolution of the models, and 3 of the models showed one thing and 3 showed something entirely different. And I think that's sort of at the heart of this, right? If we felt like just by increasing the resolution, you know, the physics are set, everything is good, all we really need to do is increase the resolution and then figure out the parameterization and then go backwards. But I can see Andrea's also shaking her head like that's, you know, that's not where we are. We're you know, knowing when we've increased that resolution that we're actually representing something like the, you know, the actual physics, dynamics, and chemistry of the system is, you know, something still to be done. So we're at about noon. Is that lunch out? Here, oh, we've got Arnaud's got his hand up again, so let's go ahead and take that.
Thank you so much. Just to go back to Elizabeth's question, I think for me the really interesting aspect of the coarse atmosphere and high resolution ocean is to understand the mechanisms, because in a model like that you'd be able to turn things on and off, the parameterization on and off, and so you can get an understanding of what are the key mechanisms which are leading to some signals that you would see in a fully coupled high resolution model. So I think that's for me the really attractive aspect to gain confidence in the mechanisms. Yeah.
Justin has his hand up.
I was just wondering if you had a 10-kilometer ocean and 100-kilometer atmosphere, will you be over smoothing the ocean when you do the coupling? Even though you'll have a high resolution ocean model, your atmosphere is only going to see 100-kilometer scales.
Yeah, well, that's the parameterization. So, for example, you can parameterize the rectified effects, say, on the net surface heat fluxes from the presence of, you know, warm and cold ocean eddies. You can estimate that, and that could be one parameterization to say I've got, a range of SST anomalies of, 3, 4, 5 degree Kelvin, and average over a scale of 100 kilometers. That's going to give me a rectified flux of 5 or 10 watt per meter square. So it's this sort of thing that, it's not, we can't let the coupler do that because they're going to smooth everything. And so it's really to have really a parametrization. I think it's super important for the ocean models, obviously, because all the boundary layer physics in the atmosphere and the coupling with the wind stress, and this is super important. So I think that people already are tackling that, but I'm more thinking on the atmospheric side of the problem. Yeah.
Okay, thank you.
Okay, I think they've brought up most of the warm food by now. I will note Sam's point to all the people online. Please stay online for another couple of minutes so he can take a virtual photo of everyone, as opposed to just taking it when people aren't aware and then showing it later as they've caught you in mid.
It looks better when there's some faces and less.
Yeah, and so if you could turn, I guess the other part of that is if you could turn your camera on, if you don't mind, those of you who are online, that would be very nice. Meanwhile, so we're going to break now, and we've got an hour for lunch, so that's time to walk around a little bit, go outside, and then we will meet back, and then we have 2 more talks and then breakout sessions this afternoon. So thank you, everyone, and thank you to everyone online, too, for tuning in.
Okay, well, thank you for coming back from lunch. We're going to get right into the rest of our program. Kicking us off, Ocean Mesoscale Air-Sea Interaction over Gulf Stream, Drivers, Physics, and Influence by Hyodae. Thank you.
So thank you, everyone. My name is Hyodae. I work at WHOI, so I welcome you to Seoul in the nice time of the year, though I haven't done anything to invite you guys. But I was asked to talk about air-sea. Can you guys hear me okay? It's too loud or it's okay? Okay. Air-sea interaction of the Gulf Stream, more focused on the oceanic mesoscale. So this is kind of I'm pretty sure many of you are already familiar with this idea. The ocean mesoscale eddies are influence the atmospheric boundary layer and then presumably deeper troposphere and downstream circulations. And that is very strong in the Gulf Stream. So I think this is one area that we should be looking at in terms of spatial scale dependence of air-sea interaction. So here, the ocean mesoscale, I just lump whole thing together, whatever the small scale, maybe smaller than deformation radius in the ocean, in the mid-latitude, maybe hundreds of kilometers in tropics, maybe 1,000 kilometers. They include semi-permanent temperature front, like Gulf Stream, or transient mesoscale eddies, which has lifetime of maybe 8 to 10 weeks. And then maybe if you go to near the coastal ocean, there's still mesoscale features for filaments and sea-subtemperature filament. Those are all mesoscale variability in the literature that we look at in terms of atmospheric forcing of the ocean. And then I'm going to be looking at the 3 quantities here. Sea-subtemperature, which we are more familiar with, and surface current does play a role in terms of influencing air fluxes. So here I had this bulk formula, very simple bulk formula. Wind stress is parameterized based on wind speed, surface current, and also drag coefficient. And sea state goes into drag coefficient, right? So I'm trying to make the case that all the 3 components are important. They interact with each other to influence the total air-sea momentum and as well as heat flux. I'd like to thank Czaja, who's my postdoc working here, working on the sea state impact on the air fluxes, and then US CLIVA, and especially working group on this very topic, mesoscale air interaction working group, that Larry and I are co-chairing, and this is an amazing group of people who try to better understand this mesoscale air interaction process of all over the world, not just Gulf Stream. So, okay, so many of you already seen this kind of map. Air-sea interaction is a spatial scale dependent. In the large scale, atmosphere may be driving the ocean. On the oceanic mesoscale, ocean might be the one that drives the atmosphere. And one way to diagnose this kind of process is just look at the very simple correlation between wind speed and sea-subtemperature, which is shown here on the left. It's a full field daily sea-subtemperature and wind speed. Just simply correlate to calculate correlation coefficient at each grid point, you get this kind of negative correlation about 0.6, 0.7, much higher in this region of western boundary crowns, tropical Pacific Ocean, and anywhere in an area where we know that intrinsic variability in the atmosphere is very strong and drive the ocean variability. So negative correlation, again, higher wind speed, strong ocean cooling, so they give you sort of sign and magnitude of the atmospheric forcing of the ocean. So this is just one example, right? And then if you spatially high-pass filter to remove this large-scale pattern before calculating correlation, then you get this kind of correlation map, which is a completely opposite sign, right? And you get this very strong positive correlation of the Gulf Stream, Crucial, vast region of Southern Ocean, tropical instability wave, Somali current, all this region where ocean eddies transport heat contribute to seaside temperature variability, and that anomalous SST can drive the wind speed. So there's a positive correlation. So again, sign and magnitude of this local SST wind coupling provides some indication about those mesoscale or sign the direction of the oceanic direction of the forcing. In the literature, we also use correlation between SS tendency with the heat flux or seaside temperature and precipitation as a way to decipher the direction of forcing and hopefully magnitude. So these are the references that I found in the literature, but I'm pretty sure there are a lot more. So this is a very classical way of looking at this boundary layer air coupling where ocean provides the forcing of the atmosphere. This is a lattice paper of the Gulf Stream, where this is monthly means spatially high-pass filter seaside temperature in contours, and the surface wind, seaside temperature in shade contours and seaside wind speed in contours. So the whole point here is that warm water, if you band-pass filter, high-pass filter, warm water coincide with a higher wind speed, and cold water coincide with a low wind speed. And coupling coefficient, which is basically scatter plot of the wind speed and SST over this grid box over all this monthly average, especially high-pass filter data, you get this very nice positive correlation, linear correlation. So this is sort of a kind of very simple but very powerful metric to use to diagnose your model, how good your air coupling is at the smaller spatial scale. So it has been widely used to validate model and in some cases improve the model physics, the surface scheme of the atmospheric model. There's some problem here in this diagnostic here that is because high-pass filtering has to be applied prior to this calculation. So it gives you some, other than just some gross interpretation of the sign of forcing, it's really hard to tease apart the scale dependence of air coupling, right? So what scale ocean is really forcing and how much this amplitude changes as a function of chosen spatial filtering scales. So for that, there are a number of studies. We saw a few from the poster this morning, which I didn't know, but Diane's work is also very interesting. Lucas Laurindo has very nice paper that diagnosed SST wind relationship with a spectral wave number frequency analysis, which is very, very nice. And then there's a Schneider 2 2018 analytical model, which also takes into account this SST boundary layer response to SST forcing, but it gives you a little bit more idea about the spatial scale dependence and downstream circulation, downstream boundary layer response to SST forcing. So these are the state-of-the-art analytical model that we have to diagnose the air interaction problem. This is the third time I show this plot. We saw this from two other speakers today. This is one way to, again, diagnose air interaction is using linearized, quasi-steady, Ekman-based boundary layer dynamics, where this is momentum equation. We ignore stochastic process in the atmosphere, so there's no time variability. And you also linearize friction with here. And then you get this three-way balance between Coriolis force and the pressure gradient and then linear damping. And if you calculate the divergence from this, you get this nice sort of a linear relationship between divergence of the surface winds with the Laplacian of sea level pressure with a minus sign. And then also vertical velocity can be also linearly scalable with a Laplacian sea level pressure. So people use this for divergence pressure, Laplacian sea level pressure and rain rate, all seems to be consistent with each other in this kind of linearized framework of the way of looking at the atmospheric response to SST forcing. Problem here is that this model doesn't consider any stochastic process in the atmosphere. In the Gulf Stream, we know that there's a storm. It's not steady state, so this model needs revision in order for this to be applied to Gulf Stream problem. So, of course, people also say that climatological mean sense western boundary current is important for anchoring storm tracks. This is a very simple way of showing that. This is a V prime T prime at 850 millibars. So this is a meridional temperature advection, temperature flux by the atmosphere. Deep green means stronger storm variability, and the sea-sub temperature contours are shown here and on this map. So you can sort of see that they are occurring same place, same time. And this can be explained very simply by this the baroclinicity vector. So in the mid-latitude, growth rate of the extratropical cyclones is proportional to sort of a baroclinic variability in the low troposphere, where sigma, baroclinicity vector, is a function of gradient of temperature in the troposphere, and then inversely proportional to the stability of the atmosphere. Of the Gulf Stream and Crocio, these conditions are both met, right? There's stronger temperature gradient in the SST. They're large enough to imprint on the low troposphere, even 2 kilometers from the surface. And there's a warm portion of the Gulf Stream Crocio, you have this 1/n. So there's a stability is weaker, and so there's a stronger synaptic variability in this happening over the Gulf Stream and Crocio. So people argue that Gulf Stream and Crocio anchor this front, the synaptic variability, and then the synaptic eddies tend to dissipate this kind of the meridional temperature gradient that is maintained by oceanic forcing. So ocean is the one that provides continuous forcing of the storm track. So subsequent study, of course, they try to remove this SST impact in the atmospheric model, and then try to look at the local and downstream circulation response. So I'm showing here one from Pacific and one from Atlantic Ocean. This is Yoshida and Riley. They're doing exactly the same thing. This is control system temperature, and then these are the SST difference between control and sort of artificially smooth systems of temperature simulations. So we are talking about SST amplitude about plus minus 3 degrees Celsius in the Gulf Stream, for example. And they try to find the atmospheric circulation response in terms of storm track variability. So this is again B prime T prime at the low troposphere. So the difference between this control minus and smooth. So whenever you see the red, means storm tracks are stronger, and that's happening over a region of the strong temperature gradients by western boundary current. So that happens both in the Gulf Stream, upstream, the near coast, western North Atlantic, western Pacific. But then there also, because storm tracks are continuous stream of the storm along the storm track, upstream perturbation can be propagated down to the western coast of the continents here. So you can see the storms by the exit region of the storm track, you see this sort of a anomalous storm track variability in downstream. So in this case, both studies tend to suggest that sharper SST front in the western boundary current tend to shift the storm track a little bit to the north, and then compared to climatological storm track where SST front is not that strong. So studies show that there's a quasi-stationary circulation response in downstream, so it leads to sort of terrestrial precipitation response and then extreme temperature response in the Western Europe and Western US. So this is kind of implication of the western boundary current impact on the weather pattern. Robust characterization of this kind of circulation response is very difficult for the reason that we just discussed in the morning. Its internal variability is really strong, and the response in the circulation to SST normally tend to project onto internal variability in the model itself, which varies across the model. So there are different climatology means different response. Different methods to define SST impact, right? This study focuses on sharpness of this front, but we also know that SST front shift north and south. And there are studies that focus on warm core eddy versus cold core eddy. This all, by removing each of these effects, it all affects as absolute subtension anomaly. So it's really hard to know what are the aspects of SST variability we are interested in, and how do they impact on the downstream circulation response. And the atmospheric frontal scale, so we're going away from climatological sense, frontal scale. this stuff we talked about, the atmospheric front, are the key here. So this is a schematic representation of western boundary current and low pressure system passing over it. That happens 30–40% of the winter time in the Gulf Stream. So these are relatively infrequent events. When they pass, especially around the cold front, the backside of the cold front air temperature is much cooler, and they coincide with the warmer SST of the Gulf Stream. This is the area where heat flux is out of the ocean and very, very large magnitude. And the idea is that atmospheric front is a major alpha scale in the atmosphere. Cross-frontal scale is about 10 to 100 kilometers. Maybe you can argue that it's comparable to oceanic cross-frontal scale. So this enables sort of direct air interaction, not just indirect coupling between ocean atmosphere, direct heat exchange between atmospheric frontal system and oceanic current system. So research is very simple diagnostic framework to look at this process, right? So if you look at cross-section here, north and south, and plot the cold front passing over from left to right, so both are cold front here, but encounter different types of SST, different orientation with the western boundary current. So cold to warm, warm to cold. Because you can imagine atmospheric front pass over around the Gulf Stream over time scale of hour, this orientation changes all the time, warm to cold, cold to warm. In this case, sensible heat flux gradient is negative, cold to warm, and this case, sensible heat flux gradient is positive. So in this kind of idealized situation where warm air is over warm water, cold air is cold water, and because the ocean is generally warmer, so there's a net heat flux out of the ocean, but there's also very strong cross-frontal contrast in diabatic heating. So warm air is preferentially warmed by ocean front, and cold air is preferentially cooled by cold water. So this leads to diabatic frontogenesis, or in other terms, there's a potential energy budget in the atmosphere. This leads to Q prime, T prime, where Q is a apparent heat source. So there's a positive covariance between Q prime, T prime, will lead to increased potential energy in the atmosphere that leads to kinetic energy of the storm. So in this case, this is positive. So this leads to genesis of the fronts in the atmosphere and then generation of potential energy. And then opposite is true here. There's a frontal losses and dissipation of potential energy in this particular case. And this happens again over time scale of hours. And then this area is about, the atmospheric area is about 1,000 kilometers. This is a very large system. And someone mentioned this atmospheric cold front is bigger chunk of the ocean, the atmospheric front storm. So this actually, area-wise, this is quite a large area we are talking about, behind the cold front and warm water of the Gulf Stream. So by looking at this sense of heat flux gradient, you can actually say something about whether the ocean is actually intensifying or dissipating atmospheric variability. So same simulation, AGCM control and smooth simulation. Here, look at this sense of heat flux gradient, simply in the climatological sense. So the Gulf Stream, there's a positive, is positive everywhere. So this corresponds to this case. This is what meteorologists usually think is the ocean is actually dissipate the potential energy in the atmosphere. So it's generally it's sort of negative in some sense. But over the Gulf Stream is generally negative, and you take the difference, there's a negative sense of heat flux gradient, which indicates that in this narrow region of the Gulf Stream is the forcing side of the storm track, storm variability through the diabatic heat exchange. So diabatic heat exchange that leads to frontogenesis is important factor. So this is again indicates that there's a direct coupling between storms and ocean at this narrow space-time scale, which we need to be resolved. Complications of western boundary current. We talked about this convergence that we see in the Gulf Stream here. Climatologically, we tend to associate this with the boundary layer forcing from Minow-Beirar's model with a quasi-stationary linear model, right? But Larry showed this, right? So when you remove these storms, these 2 sigma filter or rain flag data, you remove much of this convergence, actually end up leaving a weak divergence. So this does indicate that storms are actually contributing to this convergence, but it doesn't mean that storms are noise. Storms are signal. As you showed in the previous slide, storms are influenced by Gulf Stream, right? So Reese, look at this with me. This is weighted convergence of the Gulf Stream intertime by the atmospheric front. So he has this very nice frontal diagnostics in the atmosphere. So you can just sum all the convergence when the atmospheric fronts are present in this grid point. You get this about this magnitude, which is very comparable to what you see in the climatology. And then you can do the same thing, weighted convergence in a non-frontal atmospheric, non-atmospheric frontal situation. You end up having very weak divergence, and you have very little Gulf Stream imprints. So this again indicates that the front is what drives the convergence, and front, the way the front drives convergence is through this diabatic heating from the ocean. So this is a diabatic contribution at the oceanic frontal scale. There's a very strong, deep vertical motion that couples the low troposphere to upper troposphere and drives a very strong convergence, and this drives the near surface observed precipitation of the Gulf Stream. In the non-frontal situation, there's some that may not be really related to oceanic front. There's a past upper level PV anomaly that propagate eastward, and there's this system usually has a two component, isentropic downglide, which leads to divergence, and isentropic upglide, which is convergence. And this leads, if you average it over time scale, these two offer very strong cancellation, so you end up having very weak divergence or weak convergence. Its magnitude is very weak, so it doesn't really matter. But the idea is that what drives convergence is this diabatic heat exchange at the oceanic frontal regime. So I'm going to talk a little bit about the ocean feedback. So here, this is a kind of easy plot sense of latent turbulent heat flux climatology from Whither et al. So of course, we have a high heat flux out of the ocean. So warm SST, in the snapshot case, this experienced stronger turbulent heating out of the ocean. So this damped the ocean energy, right? So this is again diabatic heat loss, diabatic loss of energy by ocean through the LC heat flux. And I'm going to talk about the feedback of this to ocean. And this is a wind stress curve climatology from scatterometer. And you can see this, there's an imprint of Gulf Stream in a way that there's a positive wind stress curve east of the current axis, and then negative wind stress curve west of the axis. And that's because current has the negative and positive vorticity, which are reversely impressed on the wind stress, right? So there's a positive wind stress curve over negative vorticity, negative wind stress curve over positive vorticity. So this basically indicates the wind surface current is what drives the wind stress curve. And this indicates the surface current is the important term at the oceanic mesoscale determining wind stress. So, yeah. The idea is that this thermal feedback and ocean feedback does provide oceanic dissipation of the potential and kinetic energy. So this is a Seuss paper, very nice paper, the Q prime, T prime, Q prime theta prime, so temperature and heat flux covariance at ocean eddy scale, you have a very strong damping. And this is one of the terms that determines the potential energy of the ocean. So we call it eddy-induced diabatic dissipation. And this effect is not parameterized in any coarse resolution model, so it somehow needs to be parameterized. Wind work is important. Wind stress is affected by the surface current. So if you calculate the total wind work, it's generally positive going to ocean, but eddy scale is all negative. So this is Lyonnais' paper that suggests that if you take into account of ocean currents, wind work is reduced, and that slows down the ocean currents and reduces the kinetic energy. And this is an example where he ran the simulation of the Gulf Stream kinetic energy without the ocean current and with the ocean current, and you can see that energy level is much more reduced, and you can argue that it's much more realistic compared to abyssal satellite observation. I'll skip the bottom part. I want to make some case that waves are important. CD, these are the parameterized process. It's really up to us how we represent this process. Fabry's paper discussed about spatial variability of the wave quantities are determined by spatial variability of the ocean current, especially at smaller scale. So this is one example from my run where we picked a very quiet case here. The wind is ocean current is here, very strong 2 meters per second going up north, and the waves are coming from south, from the north. There's a storm further away from us. This is kind of swell wave coming to the domain and directly interacting with the Gulf Stream. So this is schematic here. Current is going north, wave is coming south. The current wave interaction leads to rougher sea state. Wave height is increasing. So you can see that this impact on the momentum flux is shown here as a This is difference of roughness length without ocean current impact on wave. You see the clear imprint of the Gulf Stream on the wave roughness length and drag coefficient and perhaps wind stress. Response is a little bit small, 1%, but roughness length and drag coefficient can be about 10% modulation of the, depends on whether you include the ocean current in the wave model. So this effect needs to be also parameterized if you were to estimate the momentum flux accurately. So summarize, these are the diagrams. Everything is all coupled to each other, right? So atmosphere coupled with the PBL, PBL coupled with the wave, wave coupled with the ocean. So, so I think this is most important slide, I guess. The mesoscale extraction is important for circulation of ocean boundary layer process and some high weather impact events. But this represents a significant challenge for the observation, of course, right? Because it resolves storms now and spatial scale that is very, very small. But these are all very important for Earth system predictability. Satellite has been mostly limited to wind-SST relationship, which is not really the way the ocean forces the atmosphere directly. It is a heat flux, but we don't have a satellite observation that measures heat flux out of the ocean at the spatial scale that are needed. The butterfly mission is supposed to address this kind of problem. And then there are some other pending or ongoing missions that measure surface current and wind and surface current and wave that I mentioned. In situ measurement is extremely sparse. I saw some new measurement, the sail drones and XPAR, that kind of thing is really great, but still very, very limited. We need more discrete array of the drag covariance flux measurement. In order to improve bulk formula, for example, we need drag measurement, not the bulk parameters estimate of meteorology. We need the wave measurement and PBL boundary layer profile measurement. This is the only way to improve bulk formula. And this is one of the, I think, the way that maybe DOE offshore wind energy project can address this issue too. There's a strong interest, OASIS or US CLIVAR initiative. They are all very, very strong, keen to improve the observational system to measure this kind of processes. In the meantime, model has been leading the research. Everything has been model studies, right? But these models, again, air flux in marine boundary process has been very, very poorly validated because we don't have many data. So cross-frontal structure of the boundary layer in the model, how realistic are they compared to actual climate data? It's been very, very poorly validated. Bulk formula, it's been very, very old, never been updated, many models. So it doesn't accurately represent this recent observation of a wave wind, wave current interaction. So this needs to be improved too. I talked about the feedback to the ocean. The coupled feedback of ocean eddy with the atmosphere has to be parameterized in terms of potential energy or kinetic energy budget. And high-res maybe is one framework to provide some sort of robust diagnostics and robust estimation of the circulation response if you're given a coherent forcing in the ocean. So this is something that can be done through this coordinated modeling framework. And then the types of modeling simulation that I do, regional model, LES modeling, could be very, very useful to look at this scale, small scale process that cannot be really resolved by global models. So we all need this kind of process to capture all these arrows in this diagram. So I'll stop here and get some questions. I put some review papers here, so you can, if you're interested, you can go down and click the link and you can get it.
Great, thank you very much. So I'm going to ask that you introduce yourself for our remote attendees.
Thanks. John Toole from Woods Hole. So a couple of people have talked about the surface wave effect due to ocean currents, and when the wind and the current oppose each other, you get big waves. Isn't it more a fact that it's the gradient of the surface current in the direction of the wind?
Yeah.
Because whether it's 10 meters a second or 11 meters per second in the velocity difference doesn't make a lot of difference. But if your surface waves are propagating in a meter per second and you run into a current opposing you at a meter per second, then the velocity over the ground is zero.
Yeah.
And you get this buildup, right?
Yeah, that's right. So people talk about the vorticity gradient associated with the currents. That is actually what reflects the incoming wave and then generate the sort of directional difference in the wave pattern that is different from wind. So I think sub-mesoscale, you can argue sub-mesoscale eddies are important, gradients. Yeah, so that's actually a good point, yeah.
Yeah, okay, we have time for one more question in the room. Oh. Okay, well, great. Thank you again, Hyodae. That was wonderful. Love the summary on your last slide. Really, hammered that home. Okay, our next speaker is Stuart Bishop from NC State. I'm not going to read the whole title.
It has changed.
Oh, okay. Hello? Okay. There we go. And should be good.
Just a pointer. Cool. All right. Well, it's a pleasure to be here. And the talk I'm going to talk about today is the observational needs for air-sea interaction in the Gulf Stream. And I'm going to focus mainly on the thermocoupling. And it's a little different from my title that was on the agenda. So I'd like to pose it like this. I'm going to give a brief outline on what do we know about coupling of the sea surface temperature and turbulent heat fluxes at mainly monthly and longer timescales. And I think in emerging areas going into much shorter timescales. And where and when do we need to observe this? And I think that's probably obvious. Where is the Gulf Stream? When? Winter time. And what time and space scales are needed? I produce. Maybe I gotta click on something.
Yeah, click in here, I think. Yeah.
Okay. So what am I going to define here? How do we diagnose air-sea interaction? So I'm going to focus on the relationship between sea surface temperature and turbulent heat fluxes, but largely what I'm going to be looking at is the latent. The sensible heat flux gives you a similar story, which is kind of different from what we see in the atmosphere. I'm going to be calling theta prime as the sea surface temperature anomaly. And so what I define as an anomaly is something that's different from a climatological average. So this is looking at the climate reanalysis. This was back in February showing the strong La Nina event that we've experienced. So what I'm trying to do here is remove an effective seasonal cycle as well as the long-term average. So anything that I call an eddy is going to be anything that incorporates all of the stuff that's not in the seasonal cycle. And I'm going to do the same thing for the latent heat flux. And if you just simply multiply the anomalies together and take a time average, that's largely what I'm going to be looking at today. This is not working. There we go. I'll just have to click on the arrow there. Okay, so we've learned a lot from these stochastic energy balance models. So going back to the late 90s, as well as before this with Frank and Gould, if you introduce a set of coupled equations, so the top would be the near surface atmospheric temperature tendency. This is your effective heat exchange modulated by alpha here for the atmosphere. So the temperature of the ocean minus the atmospheric temperature. We have a damping term, and then we introduce a stochastic noise term. In this case, this is going to represent the atmospheric weather. And we do something similar for the ocean. We have the ocean tendency equals the heat flux exchange and a damping, but no noise term. And when you do this, you can do a lagged covariance between the temperature in blue here and the latent heat flux. And you get a near zero simultaneous covariance, but you get an asymmetric lag structure. And so when you look at the tendency, you get at simultaneous lag, you get this cooling effect. So it's basically saying that the atmosphere is forcing the ocean in this case. When you have a lot of heat exchange, the ocean cools. And so we can use this to diagnose where in the ocean things are being forced by the atmosphere. when we introduce, instead we take away the atmospheric noise and we introduce oceanic noise, you get a very different lag structure. So for the simultaneous temperature covariance with the turbulent heat fluxes, it's very large and positive. This is if you have positive heat fluxes out of the ocean. And you get an asymmetric tendency covariance curve. And so when you introduce, in both equations, you have an atmospheric forcing term and an oceanic forcing term. And something that would be really cool to explore would be varying the atmospheric forcing term. But for this study in 2017, we didn't vary the NA term, we kept it constant. And we varied the oceanic noise term. So I have what I'm calling the stochastic ocean forcing on the y-axis, and it's in a log scale, and I reversed the order. So we have very large ocean forcing and very low ocean forcing at the minus 9.5. And so when you look at the sea surface temperature and turbulent heat flux covariance, it's large and positive, and then it transitions to an asymmetric structure, which we call the atmosphere driven, and you get a similar type covariance structure when you look at the tendency. And we can use this to look in the ocean. Where can we say is the ocean being basically, its internal variability is driving the SST variability. So using this as a guide, we can see at simultaneous lag, we have a very large positive covariance along the Gulf Stream SST front. And when you look at the previous month and then following month, you have a diminished covariance, but still the same sign. So then we can look at where is the atmosphere driven. Pretty much everywhere else, according to this diagnostic, we can say that at simultaneous lag, it's near zero. Keep missing the arrow. There we go. Okay. So then you can look at somewhere in the subtropical gyre, you have it near zero, and then it changes sign slightly negative. So we're calling this an atmospheric driven regime. Okay, like Hyodae brought up, we can also think of this SST covariance with the latent heat flux or the turbulent heat fluxes. It's also a dissipation term. So if you change the sign so that negative is the heat flux out of the ocean, and you scale it by these terms and integrate. In this case, this is not integrated over the surface area, but if you integrate over the surface area, that would give you what the total generation or dissipation of eddy potential energy is. And so what I want to point out is when you look at this and on top of the sea surface temperature, that really the SST gradient is where everything is located. And if you pinpoint the sea surface height gradient, it's really a little bit further to the south. There's a bit of a spatial offset. So a lot of our sea surface temperature gradient to the north coincides with a lot of where we see the air-sea interaction between at least transient anomalies and turbulent heat fluxes. So I think the spatial offset is important, that really the SST front, which is a very different front than what we think of the thermocline variability, is what's driving all of the air-sea interaction. So I then, picked out a figure from the Climate paper that John Marshall led. And if you look at where the front is, so this has been in stream coordinates, so the peak of the Gulf Stream is here in the center. And just on the north wall and to the north, you can look at the 20-degree isotherm. It's roughly in the middle of this area. It's really the northern side of the front where we're seeing a lot of the air-sea interaction. And so one of the things I did with my graduate student is we're trying to understand, there's been a lot of debate over how strong is this dissipative term in terms of a global. There's been, by the MOG group, something like 70% of the eddy potential energy is dissipated by air-sea interaction. And I've always thought that was a little bit high. So we did this in a global model where we can actually figure out how to close the eddy potential energy budget in a high resolution model. So this, we're working with POP, and this is at 10th degree. And so we have a tendency term plus equals advection. We do a Helmholtz decomposition of the eddy heat flux field into the Barrett-Clint conversion term. There's two terms associated with that. We're calling our PKC is the potential to kinetic energy conversion. Then we have a vertical mixing, horizontal diffusion, and the residual. And so we're lumping a lot of stuff into this vertical mixing term. We're saying the air-sea interaction plus vertical mixing is included in that term, and we get a beautiful three-way balance, mostly. There's a lot of cancellation between the advection and the rotational part of the eddy heat flux that acts on this. So this is a lot like what Marshall and Schutz in 1981 proposed, but this actually includes everything in the advection term. This is not just the mean advection, but also the transient eddy advection. So if you take a closer look, what we're seeing is that largely the ocean, we see the baroclinic pathway. It's largely unstable in our mid-latitude fronts like the Gulf Stream and the Kuroshio in the northern hemisphere and the ACC and the other, the Agulhas return current and such in the Southern Ocean. We've got this really nice three-way balance between baroclinic conversion, so the mean potential energy is converted to eddy potential energy through down gradient eddy heat fluxes in the horizontal. That's largely balanced by vertical eddy heat fluxes. And the dissipation term that's including vertical mixing is really confined to the upper couple hundred meters of the ocean. If you look at this as a zonal interval here, so this is depth, the upper 1,200 kilometers or 1,200 meters, and this is latitude. So we have this beautiful three-way balance that baroclinic instability is largely in control, at least in the 10th degree model. And the vertical mixing, which includes air-sea interaction, it's only really modulating the baroclinic instability pathway by about 60% of the mean potential energy is converted to eddy kinetic energy is what we find. And we looked a little closer at the vertical mixing term, so the air-sea interaction versus interior mixing. So plotting each of these different terms for the vertical mixing is the black curve over the globe in latitude. You've got air-sea interaction in blue, diffusion and KPP are the other terms. And we can see in the mid-latitudes, there are contributions from diffusion and KPP, but largely the air-sea interaction terms tend to dominate and very little contribution in the tropics. So it's safe to say that air-sea interaction is a strong contributor to modulating global EPE budgets. So I'm going to switch gears here. So I want to look at that was telling us where to look and when. So some of the time and space scales, we see a big change when we do any sort of spatial filtering or we look at low res versus high res. So the spatial dimension is a big factor in our air-sea interaction. So looking at that temperature with latent heat flux covariance, there's a cool new data set out that Hisashi Nakamura has produced with his group, a version of JRA 55. So in this set of reanalysis, it's from 1985 to 2012, and they don't include satellites, so it gives you a little bit more of a coherent signal. And on the left, they're calling this JRA 55C, where they have a low resolution 1 degree SST product. They're including in their, what's forcing their turbulent fluxes. And on the right, we have a 1/4 degree SST product that's being used as your surface boundary condition. And here, looking at monthly average data, there's a big difference between the low res, you basically see no covariance in your mid latitudes, and then in the high res SST, we see a big enhancement of this covariance. We can also see that there's also a time dimension to this. So what I did looking at the global dissipation of eddy potential energy, so this is just looking at that temperature and turbulent heat flux covariance. If you integrate over the whole ocean after spatially and temporally filtering, and so this, if you divide through by the unfiltered would be here at 0, and then you said, so you have close to 1 would be unfiltered. And then as you filter out in time and in space, you can see that about half the signal is located within about a year and about 2 degrees. So a lot of the energy is really in the shorter time scales, but based on the definition I've used for a transient eddy, you can see that there is still a bit of signal that bleeds out into the interannual timescales. So now I want to focus on each of the individual quantities, like sea surface temperature first, and then latent heat flux. So here, looking at the time and space scales of sea surface temperature, this is a yearly movie from I think it's from this website for the Nowcast. And what we can see from the SST, there's a large seasonal cycle. It's one thing you can see satellite hurricane tracks go through and cool down the upper ocean. But we have a lot of filamentary structure and small scale features that are associated with the sea surface temperature. And similar to what Hyodae showed, you can calculate, based on the lateral gradients, you can calculate an ED growth rate for the mixed layer. So I used this basic definition for the ED growth rate, and you can show that this is approximately equal to the sea surface temperature gradient magnitude, and then the square root of the mixed layer depth. So what we can say is that the stronger the temperature gradient and the deeper the mixed layers, the higher the ED growth rates are. And when you do this by season using the OI SST and the MIMOT climatology, we can see that the JFM, the January through March, and the October, November, December timeframes, you have larger peaks. And you can kind of see the structure that Reese picked out. You have this SST front right at separation, and then you kind of have a northern shelf front that picks out a lot of that. And these wintertime ED growth rates are much, much faster than I would have expected to see. So we're getting about 2.8 per day. And so I looked into Schaefer-Smith's nice paper from 2007. So if you compare the ED growth rates that we get from this mixed layer approximation with what I would call the thermocline and the inverse growth rate in days here, we see that these ED growth rates for the mixed layer are less than a day. And when we look at the thermocline instabilities, they peak in the 5 to 10 day period along the front of the Gulf Stream. So these are much faster features that are happening at the surface. And a lot of it can probably be attributed to mixed layer instabilities. So these are the relaxation of a front you can look at in time from Buccaletti 2007, where you have a temperature front in the mixed layer and the lateral. Over time, this evolves, and you can have filamentary structures that are produced from this. And this is a process that can transfer energy from the mean state to the eddies. It's parameterized currently. Baylor-Fox-Kemper has a parameterization for this. And then for the thermocline variabilities, we use the Gent-McWilliams parameterization. But what I want to stress out here or stress is that the GM parameterization is not at all playing a role in air-sea feedbacks. So we're losing any sort of feedback that's going on. It's essentially an energy sink in the current state. So I've gotten really interested in, I've focused a lot on the monthly time scales, and I wanted to really start to think about what can we do with daily time scales. And you come up with a lot of challenges. So I've been using the JO403 as sort of my proxy. And looking at sub-monthly observations, you can use this product. It's at a 1/4 degree spatial resolution. And you have daily data from 1988 to 2018. But really what I've found is it seems like post-2000 we have a bit better coverage. But I'm going to show another movie that even in the last year of the data within this, you still have a lot of interesting splotches that show up. So the upper is 2006. It's shown that we get pretty good coverage. This is surface latent heat fluxes in the color, and the arrows are the wind stress. And in 1999, you see a lot of the satellite tracks are showing up. And I'm not quite sure what they do for hurricanes or lack of hurricanes, but the wintertime storms can get hurricane force. And I'm not sure what they're doing, because when I show you a whole movie, I want to show you a couple things to take away from. So it's 2017. It was a very active year for hurricanes. We had, Maria, who demolished Puerto Rico. We had, I think it was Teddy or Jose, might have been Jose, but there were several storms. Irma came up through here. So there's a big seasonal cycle in these latent heat fluxes, and all these winter storms seem to be pretty well covered. But when there are hurricanes, later on in the summer, all of a sudden they're splotched out. So it makes me question some of the wintertime observations, considering these systems can get hurricane force. So now we're getting into April. Season's kind of winding down a little bit. The fluxes are still there. They're getting a little bit weaker. Now we're in May. Still some late season variability. So even in 2017, since the last year that GFDL has a current product, still lots of splotches show up. So now we're in July. I think we get our first storm in August. There's a little blip that comes over here, the no-name storm. I don't think it was officially a tropical. There's one. Here comes a storm. So a lot of these hurricanes that form, they don't really give you any information about what's going on during their passage. There's another one. But the wintertime storms seem to be somehow well resolved. So I wanted to look at the spectral analysis. I'm convinced that the sea surface temperature should see a lot more of a signal in the shorter timescales that would be associated with these mixed layer instabilities, but you really don't see it in this product. I'm going to have to get over here and do a lot of clicking. 5 minutes. Okay. I'll speed it up. So the latent heat flux, when we look at the power spectrum, you see there's a peak in the 5 to 8 days in this location within the Gulf Stream front, and this is the climatology of each of the SST and the latent heat flux. We looked at sea surface temperature, and like I said, there's really a lack of energy in the shorter time scales. It's really in the longer, sort of weekly to monthly time scale. But when you look at the cross spectrum and the coherence, a lot of the coherence and cross is showing up in that synoptic time band. So it's really important that we somehow figure out how to get better observations. And what I wanted to point out is these hurricane force lows are probably the culprit of a lot of the weather systems that are driving all of the strong heat fluxes. And I'm going to move on, but there's a standard definition there. And a lot of the heat flux that comes from these storms, there's a lot of spatial variability. If this is an altimeter track that went over one of these storms, this is the National Weather Service has been putting out some nice articles each year updating on the number of these storms that they track. So you can see we have the synoptic band, about 1,000 kilometer scale. Then we get down to order 10 meters, so these are the waves that can form. And then we get into likely ocean submesoscales are playing an important role at the surface, and we also get Langmuir mixing and these surface gravity waves. So there's a lot of stuff going on when these storms pass. So what I've been working with Reese Parfit and Phil Sura, and we're doing a bit of analysis looking at this daily data, same GFDL. I've done nothing with time, and I just filter out with the spatial cutoff of 500 kilometers, and I think that's pretty reasonable. So anything longer than 500, I'm going to call large scale or synoptic, and anything less than 500 kilometers, I'm calling ocean mesoscale, and I think that's okay because a lot of the meanders that form along the Gulf Stream can be several hundred kilometers, and even though they're not exactly a vortex. So I'm including in this definition meanders and cutoff rings. And when you look at a time series within the Gulf Stream front with this decomposition, so I got the total in blue, the mesoscale in red, and synoptic in green. And it's not a perfect Fourier decomposition, but when you look at the cumulative sum, first thing you see, it looks like it's all the mesoscale. It really does sort of pinpoint when you do a cumulative sum, the synoptic spatial scale largely filters out. And the whole signal comes from the accumulation of a couple events. We have this big event here in January 15th, and then we had another big event so the beginning of February, and then another big event in the beginning of March. So the accumulation of a few events drove the whole time series that you would look at from a monthly time series. And so we can see during this first big event, using the frontal diagnostic, really when you're getting these really large peaks in the covariance, it's corresponding with the passage of one of these strong fronts, and it's really in the cold sector of the front. Here's the front itself in the atmosphere, and this is latent and insensible heat flux. And also, like Reese has pointed out, that there's very different spatial scales even associated with these different fluxes. So then I decided to make a movie because I didn't really know what I was looking at with the time series at one location. And what's really cool is with the mesoscale, so anything less than 500 kilometers, looking at daily snapshots, and this is 2009, and the synoptic scale, you see very big signals in the synoptic larger scale, lots of blues and reds. But what you see along the Gulf Stream SST front is this persistent covariance that's positive. And when you do an ensemble average, the synoptic scale largely vanishes. So we see from 2005 to 2017, the total signal and the mesoscale signal are very close. Even though it's not a perfect Fourier decomposition, there's some cross terms that are important still. But really, the synoptic spatial scale appears to be canceling out, and it kind of goes back to what Arnaud was talking about. You know, maybe the atmospheric interaction is closer to the ocean mesoscale. So in conclusion, I brought it back to the first 3 points. So what we've learned at monthly and longer time scales is that the ocean is really the dominant player when you're in the vicinity of strong sea surface temperature fronts. Where and when, basically the north wall, the Gulf Stream, where the SST gradients are highest, and the wintertime is favored for large turbulent heat flux events. What other time and space scale is needed? We really need something to resolve the submesoscale to mesoscale. We seem to be missing the influence of submesoscale in our temperature fields. There are long-term repeat measurements are always going to be needed and useful, such as the oleander. And there was a really good article recently, this FluxStat by Gentman, saying that we need simultaneous measurements in order to get at these heat flux measurements, and that we should be targeting process studies on how the submesoscale to mesoscale interacts with wintertime synoptic systems. And that's it. Thank you.
Okay, thank you very much. Any questions from our participants? Yeah.
Thanks. This is Jimmy Booth. So from the Barsugli and Battisti, I felt like what they were concluding was that for that region, the variability of the SST could not be explained by the atmosphere. So it's saying you could get predictability. I missed how with your analysis, you can now get to a conclusion where you're saying that the variability of the coupling is driven by the ocean variability.
Yes.
So
at least at certain points. I mean, the sea surface temperature variability here, where you get covariance is you have to have these anomalous fields that are probably generated by the sea surface temperature fronts. And so,
sorry, so are you saying, do you think you can build a prediction of the fluxes given just what the ocean is doing?
Possible, maybe. I don't know.
Okay, thanks.
I think what I'm starting to conclude or start to think about it, you know, maybe the SST front itself is really important for the atmospheric preconditioning that Reese talks about. But on the ocean side, you know, the SST gradient probably isn't that important, except that it's driving the variability that's actually coupling in a region that wouldn't have much going on. If you look at a coarse resolution model, the gradients are very weak. You're not generating any anomalies. It's basically laminar flow model. And so that, in a sense, is really goes back to the older papers. It's just whatever the atmosphere is doing, it's really driving all the variability in the SST. But when you introduce these anomalous fronts that can drive anomalies, that they can play a role as well, where it's really their variability is linking up with what's going on with turbulent heat fluxes. Thank you.
Yeah, thanks. This is Jaime Palter again. I just had a quick question, and then maybe a follow-up if no one else is going to grab the mic away, which is that I thought you mentioned that the heat fluxes are greatest to the north side of the Gulf Stream. And
the anomalous flux, so obviously in the mean, everything to the south is where all of the dominant fluxes are. So if you were to look at the average, I got a figure going back. Right here, I mean, you can see the core of the Gulf Stream. I mean, that's really, in the mean, everything's further to the south. But when you're looking at the transient coupling between anomalous features, they could be meanders, they could be warm core rings. That seems to be preferential to the northern side. We don't see any of that same coupling on the south.
Okay, I get it. That's very interesting. And actually, it leads to my other question, which actually is to repeat a question Carol and posed to us. And maybe, do you feel like maybe it's answer between Hyodae and your talk is what scale do we need to observe the atmosphere? Is 25 kilometers, which is that microwave SST, cloud-free, but at 25 kilometers enough? And I think maybe the answer is no, because that would barely throw a couple points across some of the features that, I shouldn't be putting words in your mouth. I guess I wanted to ask, do you feel that that would be high enough resolution, 25 kilometers, given all the things that you both have showed?
25-kilometer atmosphere?
No, the SST.
I don't think so for the SST, because at least from a frontal analysis, if we're resolving the fronts and they are unstable to some mesoscale instabilities, I mean, we're not going to get that with a 25-kilometer product. And that's, I think, missing in all of this is I don't really know what that contribution is.
Thank you. Sure. Thank you. I actually do have a question. You mentioned several times turbulent heat flux from these products. Is that a parameterized product for sensible latent heat flux? Do you know?
Yeah, they're using the core.
Okay.
For sure.
So it's a combination of satellite-derived winds, SST, and then core 3.0 or 3.5 or something. Okay.
Yes.
Thank you.
I have one more question online. So from Francis, if you had strong variability in the atmosphere, but weak variability in the oceans, then presumably that could cause strong interactions in the other direction from what you were showing.
Yeah, you could think of hurricanes probably are really forcing, those cold wakes, and that's a direct influence of the atmosphere forcing the ocean. But it's quite possible that some of these hurricane force lows could be, dominant enough that they are reversing.
Okay. We're going to get started here again with the lightning talks. Again, we're going to start with the virtual recording. So the first talk is Mark Bourassa.
Hello, I'm Mark Bourassa. I'd like to talk about work I've done with Jackie May. We'd like to thank ONR for funding her PhD work and NASA and NOAA for funding my time. We'll be talking about the coupling of winds to stress and currents. This poster focuses on the atmospheric response. Jackie's poster focuses on the ocean response. Jackie used the Navy's coupled ocean atmosphere model at 2 and 6 kilometer grid spacing with and without kinematic coupling. Here we see the average curl of the stress for February 2015 from the uncoupled model, and the signature of the Gulf Stream is not very evident because the winds are Earth relative. When the winds are current relative, we see a much stronger signal. It's been found by many people in the past. But when we have a two-way coupled model, where the ocean responds to the atmosphere and it feeds back then to the atmosphere, we see a much stronger impact as both fluids adjust. This kinematic coupling is very important. We think we understand the key processes in this coupling. Anywhere there's a current, there'll be a current shear, and Because of that, there'll be an anomalous rotation in the surface. In an uncoupled model, that's not felt. In the coupled model, it is. Above that, there'll be a curl of the stress in the opposite direction, and these work against each other to get a curl of the wind. Usually the stress dominates, so it's in the same direction as the curl of the stress. And Ekman processes then are related to the vertical motions. In the atmospheric boundary layer, there's a curl of the stress going up through the whole boundary layer. So we have a fairly large layer over which the acceleration can act on the wind. So we get substantially larger vertical velocities and vertical mixing. Here I'll show an example of the impact on the mean atmospheric state for February. We have changes in specific humidity, wind speed, and potential temperature. You can see there's a lot of extra momentum being transferred down from aloft through this process, so that transports temperature and humidity upward. This is further complicated by changes in the surface temperature from the two-way coupling, and presumably from changes in latent heat release. In conclusion, you can see that kinematic coupling is important, and we understand the key physical processes. There's a substantial impact on the state of the atmosphere. The poster also shows the impacts on a frontal system, an atmospheric front passing over the Gulf Stream. And it also addresses the importance of resolution. In summary, these are important processes for both weather and climate. Thank you.
Hi, my name is Jackie May, and this is my poster on the ocean mixed layer response to kinematic coupling from currents to wind stress over the Gulf Stream region. Now, for this project, we are interested not only in the kinematic coupling, which is that coupling between the ocean currents and the atmospheric wind stress, but also the impact of the horizontal resolution of both the ocean and the atmosphere. So for this project, we ran a coupled ocean atmosphere model simulation over the Gulf Stream region for a total of 8 times. The first set of 4 experiments, we varied the horizontal resolution in the atmosphere and the ocean between 2 kilometers and 6 kilometers. And then the second set of 4 experiments are a repeat of the first 4 with respect to the horizontal resolution. However, we have included that kinematic coupling with those. So a conceptual diagram kind of showing the impacts of this kinematic coupling is shown here. And this is over the Gulf Stream extension. When we include this kinematic coupling, we get primary and secondary circulations that are dependent on which side of the Gulf Stream extension you're on. So to the right of the Gulf Stream extension within the ocean, we get negative vorticity. Associated with this, we get surface divergence and enhanced upward vertical motion. To the left of the Gulf Stream, we get positive ocean vorticity, and associated with this, we get surface convergence and enhanced downward vertical motion. Now, for this presentation, I just want to highlight the results for the mixed layer heat budget and the mesoscale vertical heat flux. And these figures shown here are for the simulations without the kinematic coupling on the left and with the kinematic coupling on the right. So with respect to the mixed layer heat budget, we found that the dominant term is the heat advection, and we do see the more anticipated result that a finer ocean model resolution leads to stronger heat advection. But then we also found that when the kinematic coupling is included, it leads to more consistent model results when the atmospheric model is changed. And this implies that the ocean processes, rather than the atmospheric thermodynamic forcing, is controlling the SST variability on these shorter timescales. Now, moving towards the mesoscale vertical heat flux, we found that when you have a fine ocean model resolution, a fine atmospheric model resolution, and the kinematic coupling is included, we see these anticipated results from the conceptual diagram of enhanced upward vertical motion to the right of the Gulf Stream and enhanced downward vertical motion to the left of the Gulf Stream. And I will stop here. Thank you very much.
and the Gulf Stream SST front at the decadal timescale. This work has been developed with Nureddin Omrani at the University of Bergen, Panos Athanasiadis at CMCC, Alessio Belluzzi at CNR, and Paolo Ruggero at the University of Bologna. Recent observational and modeling studies show that the extratropical atmospheric circulation is affected by the variability of the Gulf Stream SST front position. Therefore, studying the drivers of the Gulf Stream front variability is important for understanding the associated coupled variability and predictability. The variability of the Gulf Stream front position has been mainly linked to the NAO variability, which affects the former through anomalous wind stress curve across the North Atlantic Basin and buoyancy forcing in the Labrador Sea. However, there are some indications of no stationarity in the NAO Gulf Stream front interaction. Furthermore, there is still no consensus on the mechanisms through which the NAO affects the Gulf Stream front position. For this reason, in present work, we have investigated the spectral characteristics of the NAO and Gulf Stream front system, applying a cross-wavelet analysis. Then, we have assessed the mechanism through which the NAO affects the Gulf Stream front position on internal to decadal timescales. To do so, we have used ERA5 and ORAS5 reanalysis dataset. The cross-wavelet spectrum shows that the NAO and the Gulf Stream front co-vary at 6 up to 12 years timescale, but only between 1970 up to 2015. Specifically, the NAO leads the Gulf Stream front position by about 3.5 years, with the positive NAO phase associated with the poleward shift of the front and vice versa. About the mechanisms, the wind-driven oceanic circulation adjusts instantaneously to the NAO, explaining the onset of the Gulf Stream front shifts.
Why do we study the
Adjust instantaneously to the NAO, explaining the
ocean? To put it simply, because the ocean drives our climate. This is a story of discovery, of how we observe the ocean from large scales to small scales, from coarse satellite imagery to ultra-high resolution surface maps. Our team from Columbia University is here aboard the RV Falkor to understand how the ocean is changing on a multitude of spatial and temporal scales, to observe how the ocean's ecosystem adapts and survives in a changing climate. The ocean is a very dynamic environment, and our method for making measurements needs to be equally dynamic, to react at a moment's notice. The Air to Sea story starts and ends with a map. From a low-resolution satellite map with a scale of hundreds of kilometers to a high-resolution map of microturbulence with a scale of millimeters. What's really exciting is how we get from one to the other. This is when the UAVs come into play. Deploying these autonomous aircraft, each equipped with specialized sensors and equipment, we're able to map a very large area efficiently and with considerably greater resolution than the satellite imagery.
A few days ago, we crossed over a very large pumice patch, and it was about 10 miles from the ship. We decided it was interesting enough to go send everything over there, so we picked up all the other scientific equipment, SPIP and Sniffle and the catamaran, and we hightailed it over to the pumice patch where everything got thrown back in the water, and we were able to map that out from the air while all the other scientific equipment on the ship and floating around the ship were able to capture that data as well. You wouldn't have never known that patch was just 10 miles away and a valuable scientific target.
Thanks to our ability to act dynamically using real-time data, we tracked down pumice, which was likely to be the remnants of an underwater eruption near Tonga in August of 2019. The data we collect at times like this, such as thermal imaging and hyperspectral color imagery shown here, allows us to understand the effect of surface material, in this case the pumice, on sea surface temperature.
Hi, my name is Anna, and this is our infrared radiometer. It's one of the instruments we have mounted on the ship, and it gives us very high-resolution imagery of the sea surface temperature. So on the computer, we're able to see a 3 by 3 meter field of view of the sea surface temperature. And in that view, you can see all sorts of processes happening. Convection cells bringing relatively warm subsurface water and disrupting the cool skin. Eddies, waves breaking, sea foam. They all have different temperature signals, and it's all very clear in IR imagery.
Altogether, this data helps us build up a transformational view of the sea surface microlayer in groundbreaking detail, one which will eventually allow us to understand how the ocean and the atmosphere interact and how the ocean's ecosystem adapts and survives in a changing climate.
Here on the momentum fluxes. And so we designed a set of coupled experiments using the core 3.5 to compute the surface fluxes. And so in one experiment, the fluxes are computed using only the wind speed, and on the other experiment, we compute the fluxes using a wave-based parameterization. So here I'm just showing a few results. So this is a snapshot. We have a storm coming by from the west to the east. And so I'm showing the condition of the wind, the wave age, and then the difference of the surface stress, showing the wave impact. So what I want you to look at here is that under the high winds, we found actually two kind of sea states. So we have these young seas locally generated by the wind, which will increase the roughness and then increase the stress. But which is interesting is that we find also under this high wind some all the waves and all the seas that tend to actually decrease the surface roughness and decrease the stress. Another way to look at it is to look at the scatter plot, the distribution of the stress in function of the wind speed. And so we have the mean average of the two different simulations, and especially we have the full scatter of the wave-based formulation with the color is the wave age. And so which is interesting is that we can distinguish all the different sea states in the scatter, and especially this old seas inducing this low stress. So looking at this, you might be wondering, well, great, but is this actually realistic? Well, this is where having some direct observation of the flux is. Okay. So this is where having some direct measurement of the fluxes is really important for us to validate our momentum fluxes. And so this is where the WHOI come into place. So we have some direct measurement to compare with our model in this region. And so we can look at kind of the same distribution of stress against the wind speed, but this time against the WHOI. And so what we conclude looking at those results is that on one hand, we have the wave-based formulation, which does a pretty good job as representing this increase of the roughness in presence of young waves, but actually underestimate significantly the stress in case of old seas, and especially in moderate to high winds. So we can actually do two different things about this to alleviate and mitigate this bias. So one thing is to introduce a bit more physics, which is a directional alignment of wind and waves, because it appears that those type of old seas usually are strongly misaligned with the wind, and so we should actually expect an increase of the roughness and the stress in this case. And the other way to go about it is to use the mean wave period instead of the peak wave period to calculate the wave age into the fluxes calculation, because the peak periods tend to kind of overemphasize the presence of old waves in the domain, and so using the mean wave period allows us to better describe the sea states in the region. And so if you'd like to see a bit more of what it looks like, I'll be happy to chat around the poster. Thanks.
And next up is Eduardo Morano Camaro. Sorry, I completely butchered it.
Yeah, that's totally fine. Thanks. Yeah, my name is Eduardo. I'm a research scientist at the Barcelona Supercomputing Center, and my poster, the second one on the right there, presents some results for using eddy-rich global models from the high-risk MIP activities. So in the first part, in collaboration with Malcolm here from the office, we look at projected changes in the Gulf Stream using the HATGEM3 model, and we compare different resolutions, and we look at changes in the Gulf Stream and precipitation over the North Atlantic and Europe. And what we find is that the projected changes in the Gulf Stream and precipitation are fundamentally different in the eddy-rich model compared to any other lower resolution simulation. So on the left top, sorry, you see the SSD changes in the Gulf Stream. It's much warmer in the eddy-rich model compared to the lower resolution models. And also we see bigger changes in precipitation, both over the Gulf Stream and northwestern Europe. Yeah, and the second part, we present some very preliminary results from our own eddy-rich global model. We have a model that has a 15-kilometer atmosphere and an 8-kilometer ocean, and we have run the model for 70 years already from 1950, and we are running until 2050. And we here just present, for instance, changes in the SSD bias that we see in the low resolution model compared to the high resolution model, and we see a big improvement in the Gulf Stream region, for instance, here on the bottom compared to the top. So if you're interested in to see more results of eddy-rich models, I'll be there later. So thank you.
Sorry?
I use the mask.
Oh, yeah. Hello, my name is Diego. So I am a scientist at the Ocean Modeling Group at the Met Office, and today we are going to present a poster on the impact on the vertical coordinate system on the North Atlantic circulation, the western part. And so let me just, what is our question? So we know that coarse resolution ocean models poorly resolve some important oceanic processes, like, for example, the Gulf Stream separation or the deep western boundary counter strength at depth. We also know that current topography interaction seems to play a key role for simulating the realistic western North Atlantic circulation. And regional modeling studies shows that terrain following vertical coordinates seems to do a better job in representing the flow bathymetry interactions when compared to geopotential Z coordinates. So we want to know what is the impact of using terrain following levels on the western North Atlantic circulation in a global ocean configuration. So, yeah. So what is our method? Using classical terrain following coordinates is challenging in global configuration because it introduces pressure gradient error. So, well, we developed a methodology to employ localized quasi-terrain following model levels along the shelf and the continental slope of the east coast of North America, and while the model uses geopotential Z levels with partial steps elsewhere. We test this new methodology in the Met-Office Nemo Bay's 1/4 degree global ocean configuration. And here I'm just giving you some example, example of the results. So on the Gulf Stream, the first panel is a comparison of the surface geostrophic current from satellite with the results from ZPS. So from a model, we use Z partial steps, the ZPS, a model using the new methods, which is called multi-envelope. The model results are five-year averages. And as we can see, there are differences in the Gulf Stream represented by the two models, and the one using localized terrain following coordinates seems to do a slightly better job, but still we are overshooting Cape Hatteras, which is the main bias that we see in coarse resolution models. And for the due western boundary current, which is the lower row, we see that here I'm showing you the bottom currents, so the currents at the last wet levels of the models. And as we can see, there is a huge difference between the two models. So you can see also in the comparison with the cross sections, where you have observation on the left-hand side and then the two model. So the new method seems to represent a more barotropic current, which is what we see in the observation. If you want to know more, the poster is there and I will be there.
Hi, everyone. I'm Victoria Schoenwald, and this is some work I've been doing with Ben Kurtman at the University of Miami. So we're trying to understand shifting hotspots of sea level rise acceleration along the East Coast. And currently there is a hotspot south of where the Gulf Stream separates from the coast. And previous literature has suggested that it's related to a changing position and strength of the Gulf Stream. So I wanted to dig deeper into this, but sea level rise has a lot of different time scales that you can look at. So we decided to use empirical mode decomposition to look at the different time scales. And I'm looking at lower frequency time scales from 5 years to like a decadal time scale. And what we wanted to do was take tide data from Charleston, South Carolina, and we correlated it with sea surface height anomalies and ocean current speed anomalies. And the top two panels, we correlated that with reanalysis data. And on the left with the blue and red, you can see we have like that tripole pattern, which has been suggested to be related to AMOC. We can also see it highly correlated to the coast, which also suggests some Gulf Stream relation. And then on the right, we have the current speed data, and you can see that separation from the coast and how it's different north and south of that separation. And then the other panels, I correlated the data at Charleston, but instead of using the tide gauge data, I used the closest grid point so we could kind of compare data sets. So the bottom four are reanalysis and satellite data, and between all the panels we can see similarities even though they're a little bit different. So we decided next to look at some higher resolution model data, and we used the IHAS model, and we can see that it's not picking up the same sort of signal in either of the correlations, and the tripole signal is almost opposite. And then we can't really see the Gulf Stream signal as well. The correlation is almost zero. So we want to dig deeper into that. And then the bottom panel is the EMD analysis breakdown. And with the other data sets, we had a sea level rise acceleration early on in the IMFs, which it goes from highest frequency to lowest frequency. But in the IHAS data, we only see that acceleration in the lowest frequency all the way at the end of the data set. So we're also trying to figure out why that is.
Okay, thank you, everybody. Before we move on to the next session, we're going to give it another shot here. Luca's presentation. I'm going to try playing it directly from Google. No middleman. Let's see how this goes.
Good morning, everybody. I'm Luca Famospolini, and today I will present you a work dealing with the interaction between the NO and the Gulf Stream SST front at the decadal timescale. This work has been developed within Urania at the University of Bergen, Panos Athanasiadis at CMCC, Alessio Belluzzi at CNR, and Paolo Ruggero at the University of Bologna. Recent observational modeling studies show that extratropical atmospheric circulation is affected by the variability of the Gulf Stream SST front position. Therefore, studying the drivers of the Gulf Stream front variability is important for understanding the associated coupled variability and predictability. The variability of the Gulf Stream front position has been mainly linked to the NO variability, which affects the former through anomalous wind stress curve across the North Atlantic Basin and buoyancy forcing in the Labrador Sea. However, there are some indications of no stationarity in the NO-Gulf Stream front interaction. Furthermore, there is still no consensus on the mechanisms through which the NO affects the Gulf Stream front position. For this reason, in present work, we have investigated the spectral characteristics of the NO and Gulf Stream front system, applying a cross-wavelet analysis. Then, we have assessed the mechanism through which the NO affects the Gulf Stream front position on interannal to decadal timescales. To do so, we have used ERA5 and ORAS5 reanalysis dataset. The cross-wavelet spectrum shows that the NO and the Gulf Stream front co-vary at 6 up to 12 years timescale, but only between 1970 up to 2015. Specifically, the NO leads the Gulf Stream front position by about 3.5 years, with the positive NO phase associated with the polewall shift of the front and vice versa. About the mechanisms, the wind-driven oceanic circulation adjusts instantaneously to the NO, explaining the onset of the Gulf Stream front shifts in response to the NO. Westward traveling Rossby waves induced by the NO forcing on eastern North Atlantic are important during the maturation phase of the Gulf Stream front shifts. However, this mechanism is not stationary, being present only between 1975 and 1990. Finally, even if not shown here, there are some indications of involvement of the deep western boundary current during the growing phase of the Gulf Stream front shifts. However, these results are still under investigation. If interested, please take a look to our poster and contact me via email for any possible discussions, doubts, and clarification.
Okay, thank you again to all the poster presenters during this lightning session. Now we're going to start with our report outs from the breakout groups. So first up, I'll pull up the slides here, but I see Justin Small's group got the first slide. So you'll be kicking us off, Justin.
All right, thank you. This is very
And just let me know when you want to advance your slides, and I'll advance them for you.
Oh, great. Thank you. And thanks very much to Dan for, Ben for writing this up mainly. And this is just the notes. We started, first question was about integrated components of the coupled system. We focused on talking about model grid scales. And how do we choose the grid scales? And there's differences, obviously, if you're using global versus regional. And I think we probably focused a lot on global for climate, but there was some discussion of regional. And I think we know that for the atmosphere, you need to resolve atmosphere fronts. So a grid scale to resolve atmosphere fronts. I can't say a specific number there, but it's probably much finer than 100 kilometers. And then for the ocean resolution, we talked a lot about this 25 kilometers do well, 10 kilometers, and so on. And there was an example given from COAMS TC where looking at different grid scales, the tendencies, I think in the temperature equation, only converge when you got to scales as fine as 7 kilometers or finer. And the example was given that with 25 kilometers, it was very different to any finer grid. So 25 kilometers, you're just permitting eddies, and you're probably getting some kind of largish errors in the horizontal advection and vertical probably as well. So to resolve some of these, particularly even the mesoscale, to go down to 7 kilometers or less. And then we talked a little bit about nests and how some centers are using, say, a telescoping grid or mesh refined or unstructured. And in the atmosphere, there's some grids are able to follow tropical cyclones, but it's not a commonly used thing. It's using COAMS TC and other in hurricane centers, but not commonly used in other applications. Not really done in the ocean to have a moving nested grid, but there is work happening in the ocean to embed high resolution nests within a global setup. Question 2 was about PBL response and longer time scales, and also what about spatial scales, and with thinking that perhaps the boundary layer response is on relatively fine spatial scales similar to those of SST gradients and Laplacians and so on, and the scale of the fine scale structure and the heat fluxes. But it seems like there's another scale where the kind of aggregate effective atmosphere fronts to the Gulf Stream is operating. That seems to be a larger scale of quite a few degrees, but it still seems to be located around the Gulf Stream. So it does seem to be linked to the Gulf Stream and all the work done by Reese and Larry and others. If you move on a slide, please, Sam. And just some short responses here. Again, unless you're going to parameterize in the way that Arnaud is hoping to do, to get the key interactions involving atmosphere fronts and SST gradients, you need reasonably high resolution in both the atmosphere and the ocean. And in terms of the SST gradients, we were asking question, we saw some pictures of large mesoscale eddies in the Gulf Stream system, but right at the boundary of these eddies are extremely sharp fronts, and these may be called submesoscale. I'm not sure about the terminology, but they're extremely fine. And do they need to be resolved? And there's a question of these kind of very sharp fronts on the borders of mesoscale. They may be different to if you have an isolated submesoscale eddy, which might be just happening over a few kilometers either side. Perhaps the atmosphere response might be different to a long length sharp front at the edge of an eddy compared to an isolated, a mesoscale eddy, compared to an isolated submesoscale eddy. You might have different atmosphere responses because the kind of total area is different. I explained that very poorly, but anyway, let's move on. Question 5, the time scales. Let's stay on this slide. Thank you, Sam. We're talking about time scales for experiments, and recommend some longer term aspect is important in addition to just 2 or 3 weeks field campaign. And examples are the long-term moorings or buoys in climb mode and the Pioneer array. And there's some more details on the Pioneer array. And yeah, Sam, if we could move on to the next slide. So Pioneer is an example of getting more information out of short field campaign. The spatial resolution of the dynamics, we talked a little bit about the sub-mesoscale. And there was a question asked in climate centers and other centers, do you typically have higher resolution in the ocean or atmosphere? I think in general, the ocean seems to be higher for the high resolution models to capture ocean fronts, but probably need to be at least 25 kilometers for the atmosphere to get atmosphere fronts permitted. And then some other comments, we talked about what metrics to look at, including things like the surface convergence response to SST, linear regressions between SST and gradients and wind stress, the covariance of SST and heat fluxes that Stu talked about earlier today. Precipitation is another good metric, but it's kind of hard to observe and model, but it's important. So that's something that could be of interest to focus on. And then final comment was, are the current SE flux exchange physics good enough? And there were comments that they may not be good enough in rapidly changing environments. Ben on the team has looked at it in a tropical cyclone environment. Also, there's strong winds and things changing in the Gulf Stream, and improved physics related to waves would be desirable. And we also mentioned that wave models are starting to be incorporated in some climate models, but possibly not in the high resolution global climate models. I'll wrap up there because I think we need to be short.
Okay, thanks, Justin. Next up is Reese, if you want to come up to the podium. No? Would you please? Okay.
I did not do a very good job of leading this breakout session because, yeah, as you'll see. But so we focused on the first three questions. I think the first one was, yeah, we kind of considered the questions more from a philosophical point of view, if you can put it that way. So it was kind of when we started off talking about how can the individual components involved in the Gulf Stream be reconciled in a more integrated way. Again, my fault, but we went down the route of, well, what are the individual components? And then basically talked a little bit initially about how perhaps from a holistic point of view, the actual answer to this question is to just talk more, because it's all very well focusing on the science, but really when we talk about the individual components, there are very specific and dedicated groups that work on, say, the PBL or on ocean waves or on ocean currents. And a lot of the time, at least in my personal experience, and I think most of us agreed, that the metrics for how to integrate those different areas are not actually very well defined. And if we all talked a little bit more and made more of an effort to kind of encourage cross-disciplinary communication, that actually that may be just as important as defining kind of the science for kind of putting these individual components together. Then kind of one of the ways to perhaps do that is to take a sort of process-oriented, feature-based sort of air-sea interaction approach to identify the correct metrics. But those correct metrics are only going to, result from, when communities talk to each other. Because at the moment we all use different ones, and that's actually been mentioned quite a few times today. That how do we reconcile these views? And that's because people work on different things. So that was really where we got to with the first question. The second question about the local PBL response to the Gulf Stream. I think we decided that it's actually very difficult to separate the scales. and that actually as a community we're probably not very well positioned to answer this question, and that it's probably better to question why we can't answer this question more so than actually try and answer the question. So we talked about that more on the next slide. And basically what we also talked about was that we've heard a lot about the PBL influences today, but actually the mechanisms of ventilation outside the PBL are probably just as important for the actual effects. I think Larry mentioned earlier that everything has to go through the planetary boundary layer, but really when we talk about downstream effects, we've seen a lot of talks about these hemispheric impacts of the Gulf Stream. The key is getting, of course, outside of the planetary boundary layer and higher up in the troposphere for a lot of that stuff to happen. So thinking about the mechanisms of how things are ventilated out of the PBL are very important, and I'm pretty certain nobody knows really at the moment. So, and this is kind of where my lack of leadership really showed, because we just stalled on question 3 for about an hour. But that's why I put 3 and 4 and 5 and 6. So why don't climate models capture the influence of the ocean on the atmosphere? And so we talked a little bit about, the obvious answer to that is just, well, we can't resolve the processes, can't resolve fronts, can't resolve mesoscale eddies, can't resolve this, can't resolve that. And for the things that we don't have the resolution for, we don't have the parameterizations for those in those models. But I think we took a slightly different tone, different track, where we actually realized, well, what actually is observed? So we actually questioned the question. We said, what actually is the observed influence of the ocean on the atmosphere? What is the observed atmospheric influence on the ocean? And I think the answer is we actually really have no idea. We don't really have a critical mass of observations to observe much, actually, at least in my opinion. And I think we were all pretty agreed on that a large proportion of the mechanisms that we've heard about today, there is actually no way from observations to know whether the models are right or not. And so some of the examples that we talked about, fluxes, precipitation, these kind of things, in terms of SE fluxes, we really don't have a network of flux measurements over any appreciable region for any appreciable duration of time combined for studying weather and climate, really, where we have simultaneous measurements of everything. And we strongly agreed that reanalysis products cannot be used. They are not observations. And that for a lot of the things that we heard about today, mesoscale, SE interaction, you can probably look at it in 6 or 7 different reanalyses and get 6 or 7 different answers. I mean, they're really, really very different. And we kind of veered onto parts 4, 5, and 6 about like the influence of the SST gradient. And then, of course, one of the examples is really, well, okay. So one of the things that Carol Ann mentioned is, let's try and, if we had a sort of infinite amount of money, where do we start? Where do we go? How do we, if we, in theory, could put a sort of observing network out there, how do we do that to answer some of these questions? And we didn't really know the answer to that either. It's a very difficult question, obviously. Sorry? Okay. Okay, so, so I guess we talked about the SST gradients as well. And so for 4, 5, and 6, and I think one of the examples that was given was if you want to think about the impact of the SST gradient on the atmosphere and you had like 20 buoys or 20 stations or ships to deploy, how do you do that? Do you do it where you put them all in one area so you can really resolve the SST gradient? Well, that's not going to work because the weather feels the SST gradient over the entire length of the Gulf Stream. So in reality, we don't have a critical mass to answer these questions. So it's important to come to an agreement on how to define these various components and what the various questions are. Talk about what is a critical mass that we really need to observe them. So things like what is the ideal placement, et cetera, et cetera, et cetera. We also talked a little bit about expanded LES modeling as an option. And then generally just putting more funding into kind of expanding our observations. And the kind of slightly provocative point that I tried to make at the end personally was just that it's no good just increasing resolution for resolution's sake. When it comes to actually modeling, it's kind of like we can increase and go from 50 to 25 to 10 to 1 to whatever, but actually we have absolutely no idea what's going on at 50. So we can increase all we like. We have no way to validate this stuff. So actually figuring out how to do that is pretty crucial.
Thank you, Reese. Next up, we'll move back to virtual. I think, Elizabeth, is this your room? I think the name got cut off in the bottom. Okay, so you can take it from here.
You can hear me okay?
Yes.
Okay. We sort of combined the questions, or I think we touched on them through kind of other topics. So we said we'd like to set up experiments and hypotheses to learn more about things we don't already know. So how do submesoscale ocean frontal dynamics work in these regions of fast currents? What is the nature of small scale ocean processes that haven't been well observed or modeled? How do they impact the atmospheric boundary layer? How do those small scale processes, particularly in the ocean, feedback or aggregate to larger scales, such as synoptic, S2S, climate? And physically, how does that multi-scale feedback work? And how do atmospheric processes at many scales impact the ocean? This isn't well observed. And like Reese just said, models lack observational validation. Next, please. We talked about the possible quantities for us to quantify or track Gulf Stream processes with an integrated view. So what are the sort of comprehensive or integrated view quantities we could rally behind? And the small scale focused ones are quantities like vertical velocity, divergence, convergence, and vorticity. You could say this in the ocean or atmosphere. Spatial gradients of currents in SST, the energy cascade between small and larger scales, which can be quantified in observations and models. Surface properties in physics that are sort of the battleground of everything happening in either coupled boundary layer. Those are SST and fluxes, with the emphasis that stress needs to include the current relative wind. And the vertical velocity, temperature, and humidity, including the covariances or the fluxes at the top of the boundary layer in the atmosphere. So what are the fluxes out of the boundary layer into the free troposphere? Atmospheric convection, clouds and precip, and diabatic heating seem like good markers. And then on the climate scale focus, meridional heat transport, SST patterns, ocean heat uptake, spatial patterns, a way to quantify how much heat is converged into or out of this region, as well as volume transport. Next, please. We talked about how would we set up a modeling or observational study to actually test hypotheses. Instead of describing hypotheses, I think we knew we were limited in kind of we were limited by what's realistic. And so we spent some time talking about how we would set up, what are the realistic ways in which we could test hypotheses. And talked about the reason for setting up experiments at this point would be to learn more about nature or to learn where models are deficient. And so one idea was multi-model comparisons at high resolution, such as high-res MIP. And like prior studies, prior groups, we thought that at least 10-kilometer resolution was needed in the ocean for the Gulf Stream to even be properly resolved. So the goal here is not to just see, it's not a model bake-off, it's not just to see which model is best, but to learn about each model's biases given its physical representations and to learn how bias moves from, say, SST to the boundary layer to the storm track. We can test for emergent relationships between key quantities, or we can do sensitivity experiments. And it was noted that perhaps regional models could be useful and less computationally expensive. The other rallying point that both observationalists and modelers were excited about were focusing on case studies, since a lot of the mean signal in these longer term analyses might be made up by a few strong events. And so it's worth studying in greater detail. So the idea would be to well observe the ocean on sub-mesoscale to mesoscale ocean and the atmosphere on mesoscale to synoptic, including atmospheric convection, since that's shown to be important. A transect through the Gulf Stream might be nice, but it might not be enough because it's hard to generalize one transect relative to the whole Gulf Stream. And so you could set up a super site of observations, those like towers that have a lot of vertical profiling in the ocean atmosphere. And you could also set up a way to have roaming ocean observations. We thought that would be useful to really get the anatomy of events, small scale events that happen in the Gulf Stream. And then you could model that from a lot of different angles and we could learn a lot about that. And we thought that that would be a good place to start and a place to test hypotheses. And then we thought that these case studies are needed to form databases from which you would even begin to think about analytical models, linear inverse models, machine learning. So like techniques used to support prognostic models. Next, please. And so continuing on this same conversation, if realistic parameterizations could be formed for small scales, you could turn that on or off. It remains to be seen if that's possible or what you'd be parameterizing, but that's a goal. And then I thought it was interesting to talk about what we thought didn't work from a lot of modelers in our group, that testing, say, a high resolution field and a smooth field didn't seem that useful because the fluxes and coupling get, like, it's not really, you can't just apply a high resolution field to a smooth field and vice versa and expect that to be a realistic simulation, particularly with fluxes and the coupling physics. Turning on and off physics to do like, what if I turned off convection, or what if I turned off this in a high resolution model, apparently isn't that feasible because it's already really computationally expensive to run one high resolution model. Budget analysis didn't seem that attractive because in that budget analysis, you do a lot of time accounting for momentum and heat, but you still don't really know which field was really important for, say, the Gulf Stream to influence weather and climate, and we're trying to get a more focused view of the system, I guess. And reanalysis was also deemed to not be a good basis of comparison, particularly for fluxes, precip, diabatic processes, W clouds, and near surface air properties. But we just wanted to end that we thought that there was a lot of hope moving forward because there's a lot of momentum in both the observational and model fields, that coupled model abilities and goals from the coupled model field are very renewed. And we've also had a lot of observing advances in the last couple decades. Thanks.
Next up is Larry. Okay, let's try this again. Oh, there we go. Sweet.
Okay. Yeah, thank you for Nathan for formatting this. So I haven't actually seen the slides, so I'll just wing it here. But so we had a really good discussion. The people in our room were kind of had a wide variety of backgrounds. It actually really informed our conversation. And one of the things that kept coming up was why? What are we doing? Why are we doing it? And so that's what I'll focus on a little bit is, talking a little bit about, what we're actually trying to do. We kind of came up with a few things. One is to kind of better produce seasonal to subseasonal forecasts and to quantify the impact of mesoscale and submesoscale eddies on air-sea interaction. And of course, to do that, it's like, what kind of spatial scales would you like to resolve? Well, all the scales. And what processes do we want to do? We want to do all the processes. But you can't really focus on that we're trying to do this. Mouse, thank you. Okay, so one of the things was talking about the spatial scale was kind of determining whether we want to fully resolve things in the ocean or atmosphere. So in terms of eddies, eddy fluxes, vertical transport and things like that, or if we want to improve existing parameterizations and continue to use coarser resolution ocean models. And so this has implications for, if we want to resolve down to, very tiny, fine spatial scales, computationally it would be easier if we just did a coarser model and then parameterize the subgrid scale effects. But so there's a trade-off there, and that question really wasn't fully answered to us. And it's not clear if we could design a field experiment that would kind of help answer that question, but we thought that was kind of important. And we also thought it was really important to, for a variety of processes, to be able to resolve where the Gulf Stream separates from the coast with sufficient accuracy, and then also to get its downstream extension, the variability in that correctly. And there were and we had a lot of discussion about, if we're going to do this, have an observational campaign that is trying to improve the models, that before we do that, we have the model community really inform us, have just a tight coupling between the modeling and observational community so that the modelers can tell us exactly what, or give us an idea of what kind of observations could be made that would improve the models and improve some sort of processes. And also, when we're talking about like either forecasts, so we're forecasting, out weeks to months in advance, or if we're doing climate model projections, that we have a really good idea of how sensitive there are uncertainties in various processes are to model deficiencies and things like that. So there's a really good figure earlier that showed an ensemble system, and a bunch of different predictions from the different ensembles that were kind of with small perturbations added to them. And we thought that was a really good way of trying to assess what the modeling community will need and what the models are sensitive to. There was a little bit of discussion kind of near the end about, so there was the Toga Core field experiment that was in the early 90s over the West Pacific Warm Pool that kind of gave a, kind of a goal for flux accuracy. I think it was 10 watts per meter squared or something like that. And, that they needed to know the surface heat fluxes to be able to model things associated with ENSO, westerly wind bursts, et cetera. And we thought that, something like that might be a really useful idea to come up with. Is there a number that we can come up with for like surface flux accuracy that we need from an observing system to be able to, get certain processes right? And so that will take basically, modeling studies, maybe some pilot field studies to be able to determine, what do we need to, how accurate do we need to know the surface fluxes? Do we need to know them to 10 watts per meter squared? Is it 5 watts per meter squared? What do we need to know the momentum fluxes with? Is it like a hundredth of a Newton per meter squared or something like that? So we thought that would be a really useful goal. And then also tying that accuracy to certain processes. So for instance, we came up with processes like, if you can't get the Gulf Stream to separate correctly at the coast at the wrong position, that'll have implications for how we predict sea level rise along the coast, or different upwelling processes or intrusions of, water along the coast north of the Gulf Stream, and different upwelling and downwelling along the Gulf Stream front. And we also talked about just that, if we decide to go the parameterization route, where we have a coarse resolution model, but we, ocean model, for instance, and then we parameterize subgrid scale effects, we're still limited by the fact that the Gulf Stream is known to have sensitivity to certain bathymetric features along its path. So if you're not resolving certain canyons or seamounts or things like that, that is known to have implications for that. So that should be a consideration also for knowing that. And was that everything? Okay, cool. I guess one thing I want to say too is we also had a nice table that, it's like what happens if you have an ocean model and you absolutely cannot have it below some grid spacing, like an eighth of a degree or a quarter degree or something like that. What kind of processes would you not be able to do? What kind of things would you not be able to do or predict? Would we not be able to predict the weather in Europe very well, or would we not be able to predict sea level rise very well? And that might be something to, getting at that question of why are we doing this and what is it that we're getting at, I think would be really beneficial for kind of setting the scale for, or setting the stage for what we hope to accomplish. So thank you.
Thank you, Larry. Pardon me for a second while I pull up some notes here. Okay.
Thanks. All right, thanks. So we could say that the groups online really did a great job of answering the questions, and the groups that met in person got a little bit distracted or took a different approach. But as someone who is part of the organization of this, I will say the questions were meant as a guide that could be used optionally. We took that approach and we really just went in and had a discussion motivated somewhat by the testable hypothesis, but mostly motivated by a reflection of what we heard earlier today. And so we heard a lot of interesting modeling and then backed out of the modeling analytic models. And the analytic models oftentimes were based on dry dynamics. And we started to think a little more about, okay, do we need to find a way to put moisture into it? And then we expanded that to think about, well, moisture not just in our analytic models and moisture not just being fluxed out of the ocean, but saying, what about the moisture in the system, its importance in clouds, and the importance of clouds in the climate system. You know, clouds are a problem for certain satellites in terms of understanding what's happening at the ocean surface, but clouds are critical for the climate system, so we want to think about them in that respect as well. We also did a lot of talking about the way that the fluxes are currently parameterized and that there's been advances that have not necessarily propagated through all of the different places where they need. So we could actually have better estimates of the fluxes now if we just kind of apply some of the things we've already learned. And we talked about waves. And we talked about how waves are important to the ocean for setting SST. And when we're thinking about, when we're doing a forward model of an ocean, the degree to which we have the waves in there, the waves interacting with the current, and then that feedback on the SST, since the SST is so critical for the air-sea fluxes. And then we spent time talking about the planetary boundary level, the PBL height. And we thought about how could we take this as a starting point for our hypothesis. We didn't get there completely today, but we definitely feel like this is a nice metric that comes up a lot and could be something that we really want to look into. We talked about different aspects of the PBL height, and then this was one question that came to mind for me, is to say, when a storm arrives in the Gulf Stream, what is the spatial structure of the PBL? And does that have a role in how the ocean interacts with, or how the surface, if you will, interacts with the atmosphere? So a storm encountering a PBL with a very heterogeneous structure might be very different from one encountering a homogeneous structure. And this ties back into resolution of the climate models and thinking about, okay, so at what scales do those structure of the PBL matter? We talked about this, and this kind of gets into what Larry was talking about which processes matter. And we started thinking about actually doing some of the accounting that Elizabeth mentioned for the sake of saying, well, is this a process that we can't ignore? So saying, could we take an analytic solution for sea surface temperature and then break it down into the different pieces and actually have a scale analysis of the different components to get a better idea of which ones we definitely can or cannot ignore. And from that, we kind of backed out to saying, well, we have this idea that local processes definitely do matter for the Gulf Stream. And so we have to think about how we can parameterize the processes, how we can observe them. And so then we started thinking about, can we put something permanent in the Gulf Stream region for the sake of observations? And Megan brought up that you need these continuous maps in time, but you also need them continuous, or you need them over a large spatial region. And so we're talking about a campaign that needs to be vast. And she's going to highlight more of this tomorrow, so I won't go into too much more of those notes. The other one that we came up with was here, which was that the life cycle age of the extratropical cyclone can have an important impact on what kind of influence the Gulf Stream or the Gulf Stream region has on the storm. So we have different
flavors of the extratropical cyclones that we're interested in, but also in their life cycles, they're smaller and then larger, and that scale can have a big impact on whether we see forcing from the Gulf Stream onto them. And then, yeah, we took a little bit of notes on ET transitions. A lot of this discussion that we had ended up being a bit about how do we get to these testable hypotheses, but we were also at this point that Reese mentioned of just talking more and just exchanging ideas, learning more from the modeling side to the observation side, the atmosphere side to the ocean side. So it was very useful for us, but in the end, I would say our feedback for you all is still developing.
All right, now we're going to move into an open discussion. Caroline will moderate for me on the breakout results.
Yeah, we have about 20 minutes before our networking event. For those of you who were asking this question, I do see wine out there. So there was some concern that that may not be available, but I see bottles showing up. So that gives you a goal for the next 20 minutes. Yeah, so thanks again to all the moderators of the the breakout groups. It was a lot of work, so it was kind of like a workout, both in person and online. I think there's a lot of information there, and what's going to happen is Nathan is going to spend tonight collating all of that into a really coherent discussion for tomorrow morning, and we'll trying to look for some of the commonalities. I was trying to observe commonalities as I was listening to these, and there were definitely some commonalities that I saw coming up. But we have, again, about 20 minutes. So if there are things that people would like to discuss at this point, I heard at least 2 different groups have a conversation about reanalysis is not actually data, and maybe we should not use it as a validation for some other model. I'm going to put in a pet peeve here because I'm going to, because I have the mic. So what I know that we know this, and I just feel like sometimes the way we express ourselves doesn't come across that way. But for instance, when you're looking at stress, all right, it isn't a question of whether you should include the currents or not. There is a correct thing to do, which is currents are a part of the Earth system. And so it's fine if you can't put them into the model because you just don't have the information for the currents or you don't have the coupled part of it. But that is the actual correct thing to do. And so I was just thinking that when someone, I think it was Elizabeth's group, and they were talking about running, umpteen, sensitivity studies. It's like you shouldn't run the model and then sort of ask, should we include currents, right? Because the currents are the actual physical thing that are happening, right? We only don't include them because of computational cost, or we don't have enough observations, or we don't understand something, right? Currents are not the only thing, but sometimes the way we talk about some of these extra things that we put in, right? They're not extras. That's actually how the system works, and we're just not including them for whatever, for whatever particular reason, right? Which is legitimate, but I don't know that. I always think of that when, again, it was Elizabeth, I think, comment about not running a lot of high resolution models that, for all kinds of sensitivities studies and so forth. It's like, okay, we've actually put something in that adds some physics in some way. I mean, it's good to know why the model does what it does, but there's some aspect of that. Okay, so since I did that. Oh, Elizabeth, go ahead. Is that Elizabeth's hand or is that Justin's hand?
Oh.
Okay, so Justin, your hand is up. Go ahead and unmute and say something.
I had a question following on from your comment about reanalysis. Also noticed there were 2 criticisms of the reanalysis, and I've been using reanalysis blindly, it seems, based on what's been said. I wanted someone to kind of quantify or give examples of how poor they can be, and or the range of different results you can get from reanalysis. I think Reese was saying there's a wide range, and how just relying on one reanalysis data set, how bad an assumption that is. I wondered if anyone can fill in a bit more about that.
All right, Hyodae, you want to take that?
So yeah, I just like to respond to Caroline. You just comment about current impact. Yeah, I think I agree that the right thing to do is include current in the stress formulation. But I guess it's very insightful and meaningful to look at the processes by which currents modulate the stress and its impact on ocean dynamics. And that's something we didn't know so far very well. And I think recent study begin to show all those very interesting physics that we didn't know about by having this current. And I think you can take the analogy of forcing model with a high resolution SST versus low resolution SST. Right thing to do is use high resolution SST. By having that, by doing that, you can learn about how Mesoscale SST influence that. So I guess you can take that kind of analogy to say ocean current impact is something still worthwhile to look at, in my opinion, and very and I think I find it very interesting to see all those dynamics that pop up from this model by having currents at different scales interact with the atmosphere.
Yes, and I didn't mean we shouldn't understand the impacts of it. It's just in the way that we talk about things, sometimes we make it sound as if it's a question as to whether we should include it or not. And I think we ask ourselves, should we improve our flux parameterization in the model? I mean, that shouldn't be a question, right? That's just not a tunable knob. If we, that should be something that we can do. But I knew it was going to be slightly provocative to throw that out there. But I think Justin's question on the reanalysis. So, Andrea.
Oh, okay. And then Elizabeth will come to you after Andrea.
Yeah.
Yeah, I think I'd like to take a crack at responding to Justin or answering or something. I don't know if it's a matter of that you look at, I've looked at MERA2 surface fluxes quite extensively. And so you can compare it to other estimates out there and say it's biased high, it's biased low. But fundamentally, there's nothing about the near surface stability or the flux that is constrained by data. And so I would believe MERA2's surface flux is the same way that I would believe it out of a free running model. It's a model output. So it's not, I've looked at it, it's crap, but I don't think it's any more credible than the model output. So that would be my response.
Okay. Thank you.
I think Elizabeth has a question online or a comment.
I was going to echo and say it in the same way that Andrea just did, that in our comparisons of field data, even if you account for the different temporal, time step, if you will, in reanalysis, any moisture-related field is going to be dependent on the moist physics in the model, which I think we all know have a lot of problems. And so fields like precip or fluxes, and the way I described it in our group is that what I've seen with comparisons to our field campaign data are that anything that is super well observed already, like wind, surface wind, we have a lot of observations. Like surface wind is really solid in a lot of models and in reanalysis. It's backed by a lot of data, as Andrea said. So anything that we're not directly observing is not really constrained, and anything that we already know that a model struggles with, that's in reanalysis. I don't really trust reanalysis precip. I don't trust reanalysis W. I don't really trust, and it's not that I don't trust it in a large scale sense. It's still that in the model has to balance its own physics, and it does that when its own compensating errors, not in the same way that like nature does. And there are probably scales and applications for which those estimates are good enough, but like, are they good enough to like test a physical process in the Gulf Stream? I think I'd feel like less confident in that. Whereas like, is it a large scale descriptor of is it a pretty good estimate in other cases? Perhaps. Does that make sense? Like, it's not like it's bad all the time. It's total garbage. It's just a matter of how well you trust it in certain applications. And then I was just
Elizabeth,
yeah.
Sorry. This is Megan. I have a question for you though.
If the I totally agree with you for reanalyses that are just using the standard data that is coming in from the Global Ocean Observing System. But if it is enhanced with intensive observations from a field campaign that then get assimilated into the model, would that then be a way to create a dynamically correct gridded field that is a realistic kind of field that we can then use for analyses?
Probably, if the observations were long-term enough and if they were like deemed important and trustworthy and not problematic enough by an operational center to actually pick up. And so just because something gets reported to GTS doesn't mean it's picked up by every model or each model, or that and there's a difference between the model using it operationally and whether it's in the reanalysis. And so I would say like probably, hopefully, but it's really rare for field campaign data to be taken up by operational centers in my experience, because they don't want to use one little data point for a month, and it requires a lot. And I hope that that's one informed. Sorry, what?
Okay, so this is kind of dreaming ahead and putting out the, what if? Right now, yeah, I mean, it's for doing an atmospheric study, we are relying upon like dropsondes from aircraft. And so it's really just very limited in time and it's a little postage stamp. But what if we develop some true profiling capability that could be done on a sustained basis? And when I'm saying profiling, I'm talking about, remotely sensing of the atmosphere. Then I think, then you are talking about larger scale, longer term, and potentially super valuable data for constraining a model. But, there is going to be some development stages to go from, benchtop where we are right now to actually an operational, TRL 8 or whatever it is.
And I would, before I lose the mic, I just want to respond to Caroline's wave influence, and also that, yeah, that could work out. Reanalysis, or I was going to bring up the OA Flux product as an example. That's one where like more data are used. It's a more data informed Flux product, and we find really good, or like a lot better comparisons to our observations. And so it's possible to use even satellite data to make better global flux products. And so OA Flux is one of them. Does that make sense, Justin? For instance, that's another product other than reanalysis that is informed by data in more ways. That's not as model dependent. And then I was just going to say, our group only brought up current relative wind as a means that if there were going to be quantities that a model and observational study targeted on, we just wanted to make sure that it wasn't just the Earth relative wind, because a lot of models only have that. And so it wasn't a question of whether we should do that. It was more of an emphasis that the current relative wind should be the rallying point, period. Thanks.
Thanks, Elizabeth. And first of all, thanks for the shout out for satellite fluxes. As a person who developed satellite fluxes, I'm pretty happy to hear that. I will mention OA Flux does assimilate reanalysis data into it. So that's a point. And then I have another point, but I think Nathan did you have something to say, Nathan?
I do, yes. Yeah. So we do have a framework for incorporating wave and current effects into air-sea interaction, the wave action balance equation. It, explicitly takes into account vorticity effects on wave dynamics, steepening, braking, a number of source functions. It's already used in wave modeling. I think that there should be a look towards some of the explicit coupling of ocean, atmosphere, and wave modeling, rather than relying on the drag coefficient as a catch-all for all physical dynamics associated with air-sea momentum flux or whatever. So I know that that's not the only way to do coupled modeling, but I do think that that approach does sort of close the loop on, should we include this, should we include that? Well, if it's going into growing waves and helping them to break, then it's going to be, it's going to be connected to the surface stress. So I just think that that is a way to kind of make many people happy, is to use fully coupled modeling.
So we have a hand up from Chris Roberts, who's probably got a comment. I'm guessing maybe on reanalysis, but perhaps not. Feel free to comment on anything.
Yeah, I mean, it was on the reanalysis and the fluxes. I understand, the deficiencies in these systems. I've also used them to look at stuff in the absence of anything else. But I mean, the alternative, so observation-only products that are still spatially complete fields, they still use some statistical methodology or optimal interpolation or something, which is arguably less sophisticated than a more another method of sort of fusing data and some technique, either a dynamical model or a statistical model. So do people have the same issues with using spatially complete statistically interpolated fields?
And no one is taking you up on the offer to answer that question. I would say, at least from my group, that the discussion was more about what observation, that I think it was almost all of the results that we talk about and the impact of the Gulf Stream on weather and climate come from models. All right, so question, what do we know from observations about this? And the answer was not very much at all. What kind of observations would we need to help us understand the model, where they're doing well, where they're correct, where it's incorrect, why there are the differences between the models and so forth. And then that, for us, I think, is where we sort of got into the reanalysis, that we can't use reanalysis as a basis for evaluating. People felt uncomfortable using reanalysis as a way to evaluate other models, their impacts, was kind of the way that went. But I just do want to step back and say it did start from the conversation of a lot of the hypotheses we are talking about are based almost solely on modeling results for which we have almost no observations at those scales or of those processes, right? So, and then, so then the question then was what kinds of observations would we need to, that was an open question. Like what are the observations that we feel like we would need to help us sort of navigate through? Do we understand when some of the models, when you increase the resolution, they have this impact, and other ones, when they increase the resolution, they don't have some impact? And as Reese said, we're not even sure at 50 kilometers in the Gulf Stream that they're doing the right thing anyway. So we increase the resolution and we're even less sure because we have even fewer. I guess you can't have fewer than zero, but we don't have the right set of observations. I think that was a kind of the way that we, at least our group, got into sort of the reanalysis discussion. But Reese has got a comment.
I think most people have heard me plug this before, but I'll plug it again anyway. I think if anybody just needs some evidence that you can't trust reanalyses, I would challenge anybody to go and look at the error interim product and compare Gulf Stream air-sea interaction in the first 20 years versus Gulf Stream air-sea interaction in the last 10 years. There is a 30% step change in the precipitation. So if you use that product itself to look at a trend or look at anything like that, it will be wrong, because you just get it's literally like just a massive step change where they're assimilating a better SST at a higher resolution, and you get this huge increase in precipitation. So one of the problems with the reanalyses is that obviously we need to use something, but the reanalyses themselves are not internally consistent. The vast majority of reanalyses change things throughout the 40 years, And those things have real impacts. And the error interim example I gave was the most egregious. So for me personally, when using a reanalysis product, if you're going to use it, obviously it's important to use it. The reanalysis product should stay internally consistent with themselves. And as I said, the problem is that most of them don't. So that adds another layer of complexity to it. But as I said, if anybody, maybe that's to your question, Justin, the extent to which this problem exists in reanalysis, I would encourage you to go and take a look at GulfStream stuff in error interim. And yeah, anyway.
Can I just follow up on that? I know there are biases in older products like NCEP, NCAR reanalysis, and error interim. But I just wondered if there's been improvements with things like ERA 5 and some of the more modern data sets. Although I take the point about mirror and other reanalysis being not constrained, the moisture fields. But Reese, do you think that ERA 5 might be a better data set?
Yeah, I mean, for me, the thing that I think about with the reanalyses, when they're assimilating certain products, certain things, they're adjusting the model to make that right. Anywhere where the model is not right in its physics, it has to adjust there to get what they are seeing and assimilating in there. And they're not running, I hate to tell folks that in my experience, at least, they're not running the reanalysis products to give us the best air-sea fluxes. That's not their goal, right? That's not what they're doing. They're assimilating, let's say, profiles of water vapor, and they're trying to get that right. And that might mean you have to change a little bit in the precip and the evap if your precip is off, So I think that's part of it. It's just that we aren't using them for what they're not there to give us perhaps what we want to have. And there shouldn't be faulted for that. We should just be clear what we can get and can't get from them and where the errors might come in. But I think someone had their hand up, and I will let that person have the last word because I see an actual uncorking going on out there. So I think that's important. Was it Reese? Did you want to have one last? Oh, okay. All right. So nope, Sam says no. So go ahead and we will say thanks to everyone, and then we're going to have just networking. Come take a look at the posters and have some wine and relax and chat. So thank you to all.